going to start this chapter 1, introduction of data structure algorithm made easy by Narasimha Karumanchi. We're going to start the chapter from here. The objective of this chapter.
The objective of this chapter is to explain the importance of the analysis of algorithms, their notations, relationships, and solving as many problems as possible. Let us first focus on understanding the basic elements of algorithms, the importance of algorithm analysis, and then slowly move toward the other topics as mentioned above. After completing this chapter, you should be able to find the complexity of any given algorithm. 1.1 variables.
Okay, that's very good. That's a nice introduction.
Okay, starting it.
Before getting into the definition of variables, let us relate them to an old mathematical equation. Many of us would have solved many mathematical equations since childhood. As an example, consider the equation below. We don't have to worry about the use of this equation. The important thing that we need to understand is that the equation has names which hold values. That means the names are placeholders for representing data. Similarly, in computer science programming, we need something for holding data, and variables is the way to do that. 1.2 data types. In the above-mentioned equation, the variables x and y can take any values such as integral numbers, real numbers, or just 0 and 1. To solve the equation, we need to relate them to the kind of values they can take, and data type is the name used in computer science programming for this purpose. A data type in a programming language is a set of data with predefined values. Examples of data types are integer, floating point, unit number, character, string, etc. Computer memory is all filled with zeros and ones. If we have a problem and we want to code it, it's very difficult to provide the solution in terms of zeros and ones. To help users, programming languages and compilers provide us with data types. For example, integer takes 2 bytes, float takes 4 bytes, etc. This says that in memory, we are combining bytes and calling it an integer. Similarly, combining 4 bytes and calling it a float. A data type reduces the coding effort. At the top level, there are 2 types of data types. System-defined data types. User-defined data types. System-defined data types. Data types that are defined by system are called primitive data types. The primitive data types provided by many programming languages are int, float, char, double, bool, etc. The number of bits allocated for each primitive data type depends on the programming languages, the compiler, and the operating system. For the same primitive data type, different languages may use different sizes. Depending on the size of the data types, the total available values will also change. For example, int may take 2 bytes or 4 bytes. If it takes 2 bytes, then the total possible values are minus 32,768 to plus 32,767. If it takes 4 bytes, then the possible values are between minus 2,147,483,648 and plus 2,147,483,647. The same is the case with other data types. User-defined data types. If the system-defined data types are not enough, then most programming languages allow the users to define their own data types, called user-defined data types. Good examples of
I can decrease the speed so you can focus it very nicely. Okay, fine.
Defined data types are structures in C, C++, and classes in Java. For example, in the snippet below, we are combining many system-defined data types and calling the user-defined data type by the name new type. This gives more flexibility and comfort in dealing with computer memory. Private char data, operations.
You can see here, public class, new type, public int. This is the user-defined data type. This is the integer data type defined by the user, data 1 and data 2, and these are integer, and this is the private float data type, data 3. Okay, the private character data type, data. Now data structure.
1.3 data structure. Based on the discussion above, once we have data in variables, we need some mechanism for manipulating that data to solve problems. Data structure is a particular way of storing and organizing data in a computer so that it can be used efficiently. A data structure is a special format for organizing and storing data. General data structure types include arrays, files, linked lists, stacks, queues, trees, graphs, and so on. Depending on the organization of the elements, data structures are classified into 2 types. 1. Linear data structures. Elements are accessed in a sequential order, but it is not compulsory to store all elements sequentially. Examples: linked lists, stacks, and queues. 2. Non-linear data structures. Elements of this data structure are stored accessed in a non-linear order. Examples: trees and graphs. 1.4 Abstract data types. Before defining abstract data types, let us consider the different view of system-defined data types. We all know that by default, all primitive data types support basic operations, such as addition and subtraction. The system provides the implementations for the primitive data types. For user-defined data types, we also need to define operations. The implementation for these operations can be done when we want to actually use them. That means, in general, user-defined data types are defined along with their operations. To simplify the process of solving problems, we combine the data structures with their operations, and we call this abstract data types. An ADT consists of 2 parts. 1. Declaration of data. 2. Declaration of operations. If yes, put it in the pan. 2.
Oh, it's missed the line. So you can see the abstract data types consists of two parts: declaration of data and declaration of operation. Commonly used ADT includes linked lists, stacks, queues, priority queue, binary trees, dictionaries, disjoint sets, okay, union and find, hash tables, graphs, and many other. For example, stack uses LIFO, last in first out, as you can see, mechanism while storing the data in data structure. The last element inserted into the stack is the first element that gets deleted. Common operations are creating the stack, push an element onto the stack, move an element from the stack, finding the current top of the stack, and finding the number of elements in the stack, etc. While defining the entity, do not worry about the implementation detail. They come into the picture only when we want to use them. Different kind of entities are suited to different kinds of application. Some are highly specialized to specific tasks. And by the end of this book, you will go through many of them and you will be in position to relate the data structure to the kind of problem they solve. Now, what is an algorithm? Let us consider the problem of preparing an omelette. To prepare an omelette, we follow the steps given below. Get the frying pan, get the oil. Do we have oil? Yeah. If yes, put it in the pan. If no, do we want to buy oil? If yes, then go and out and buy it. If no, we can terminate it, okay? And turn on the stove, etc.
If no, do we want to buy oil? 1. If yes, then go out and buy. 2. If no, we can terminate. Commonly used ADs include linked lists, stacks, queues, priority queens, binary trees, dictionaries, disjoint sets, hash tables, graphs, and many others. For example, stack uses a LIFO mechanism while storing the data in data structures. The last element inserted into the stack is the first element that gets deleted. Common operations are creating the stack, push an element onto the stack, pop an element from the stack, finding the current top of the stack, finding the number of elements in the stack, etc. While defining the ADs, do not worry about the implementation details. They come into the picture only when we want to use them. Different kinds of ADs are suited to different kinds of applications, and some are highly specialized to specific tasks. By the end of this book, we will go through many of them, and you will be in a position to relate the data structures to the kind of problems they solve. 1.5. What is an algorithm? Let us consider the problem of preparing an omelet. To prepare an omelet, we follow the steps given below. 1. Get the fry. What we are doing is, for a given problem, we are providing a step-by-step procedure for solving it. The formal definition of an algorithm can be stated as, an algorithm is the step-by-step, unambiguous instructions to solve a given problem. In the traditional study of algorithms, there are two main criteria for judging the merits of algorithmness. Correctness and efficiency does it take to execute the. Note, we do not have to prove each step of the algorithm. 1. The analysis of algorithms. To go from city A to city B, there can be many ways of accomplishing this, by flight, by bus, by train, and also by bicycle. Depending on the availability and convenience, we choose the one that suits us. Similarly, in computer science, multiple algorithms are available for solving the same problem. Algorithm analysis helps us to determine which algorithm is most efficient in terms of time and space consumed. 1.7% goal of the analysis of algorithms. The analysis of an algorithm can help us understand it better and can suggest informed improvements. The main and important role of analysis of algorithm is to predict the performance of different algorithms in order to guide design decisions. The goal of the analysis of algorithms is to compare algorithms mainly in terms of running time, but also in terms of other factors. In theoretical analysis of algorithms, it is common to estimate their complexity in the asymptotic sense, that is, to estimate the complexity function for arbitrarily large input. The term analysis of algorithms was coined by Donald Knuth. Algorithm analysis is an important part of computational complexity theory, which provides theoretical estimation for the required resources of an algorithm to solve a specific computational problem. Most algorithms are designed to work with inputs of arbitrary length. Analysis of algorithms is the determination of the amount of time and space resources required to execute it. Usually, the efficiency or running time of an algorithm is stated as a function relating the input length to the number of steps, known as time complexity, or volume of memory, known as space complexity. 1 is running time and time analysis. It is the process of determining how processing time increases as the size of the problem increases. Input size is the number of elements in the input, and depending on the problem type, the input may be of different types. The following are the common types of inputs: size of an array, polynomial degree, number of elements in a matrix, number of bits in the binary representation of the input, vertices and edges in a graph. 1.9 How to compare algorithms. To compare algorithms, let us define a few objective measures. Execution times. Not a good measure, as execution times are specific to a particular computer. Number of statements executed. Not a good measure, since the number of statements varies with the programming language as well as the style of the individual programmer. Ideal solution. Let us assume that we express the running time of a given algorithm as a function of the input size n, and compare these different functions corresponding to running times. This kind of comparison is independent of machine time, programming style, etc. 1.10. What is rate of growth? The rate at which the running time increases as a function of input is called rate of growth. Let us assume that you go to a shop to buy a car and a bicycle. If your friend sees you there and asks what you are buying, then in general you say buying a car. This is because the cost of the car is high compared to the cost of the bicycle. For the above-mentioned example, we can represent the cost of the car and the cost of the bicycle in terms of function, and for a given function, ignore the low-order terms that are relatively insignificant. As an example, in the case below, n, 2 and 2, 100n and 500, are the individual costs of some function, and approximate to n, since n is the highest rate of growth. n, 2 plus 2, n, 2 plus 100n plus 500 equal to n. 1.11 commonly used rates of growth. Below is the list of growth rates you will come across in the following chapters. The diagram below shows the relationship between different rates of growth. 1.12 types of analysis. To analyze the given algorithm, we need to know with which inputs the algorithm.
This is the decreasing rate of growth to the power 2 to the power 2n, to the power n factorial for the power n to the power n square and log n factorial n to the power log n. Log square n, root log n and 1.
Algorithm takes less time. And to analyze the given algorithm, we need to know with which inputs the algorithm takes less time and with which inputs the algorithm takes a long time. We have already seen that an algorithm can be represented in the form of an expression. That means we represent the algorithm with multiple expressions, one for the case where it takes less time and another for the case where it takes more time. In general, the first case is called the best case and the second case is called the worst case for the algorithm. To analyze an algorithm, we need some kind of syntax, and that forms the base for asymptotic analysis notation. There are three types of analysis. Worst case defines the input for which the algorithm takes a long time. Input is the one for which the algorithm runs the slowest. Best case, these. O defines the input for which the algorithm takes the least time. Input is the one for which the algorithm runs the fastest. O, average case, provides a prediction about the running time of the algorithm. O, run the algorithm many times using many different inputs that come from some distribution that generates. Inputs compute the total running time and divide by the number of trials, assumes that the input is random. Lower bound less than equal to average time less than equal to upper bound. For a given algorithm, we can represent the best, worst, and average cases in the form of expressions. As an example, let f be the function which represents the given algorithm. Fn 2 plus 500 for worst case, Fn plus 100n plus 500 for best case. Similarly, for the average case. The expression defines the inputs with which the algorithm takes the average running time. 1.13 asymptotic notation. Having the expressions for the best, average, and worst cases, for all three cases we need to identify the upper and lower bounds. To represent these upper and lower bounds, we need some kind of syntax, and that is the subject of the following discussion. Let us assume that the given algorithm is represented in the form of function f. 1.14 big O notation. This notation gives the tight upper bound of the given function. Generally, it is represented as f equal to O. That means at larger values of n, the upper bound of f is g. For example, if f equal to n plus 100n, 2 plus 10n plus 50 is the given algorithm, then n is g. That means g gives the maximum rate of growth for f at larger values of n. Let us see the O notation with a little more detail. O notation defined as O equal to f. There exists positive constant c and no such that 0 less than or equal to cg for all n greater than or equal to. G is an asymptotic tight upper bound for f. Our objective is to give the smallest rate of growth g, which is greater than or equal to the given algorithm's rate of growth f. Generally, we discard lower values of n. That means the rate of growth at lower values of n is not important. In the figure, no is the point from which we need to consider the rate of growth for a given algorithm. Below no, the rate of growth could be different, No is called threshold for the given function. Big O visualization. O is the set of functions with smaller or the same order of growth as G. For example, O includes O, 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 etc. O. 100, 1,000, 200,000, 120, etc. O. 3n plus 100, 100n, 200,000, n, 2n to 1, 5, etc. Note, n2, n2, and wide enough grow. No, we do not care about the rate of growth. Big O examples. Example 1, find upper bound for f equal to 3n 8. Solution, 3n plus 8 less than or equal to 4n. O with c minus 4 and no equal to 8. Example 2, find upper bound for f equal to n2 plus 1. Solution, n2 plus 1 less than or equal to 2, and 2 for all n greater than or equal to 1. n plus 1 O with c equal to 2 and no equal to 1. Example 8, find upper bound for f equal to n plus 100 n2 plus 50. Solution, n plus 100 n2 plus 50 less than 2n, for all n greater than or equal to 11. n plus 100 n plus 50, O with c 2 and no equal to 11. Example 4, find upper bound for f equal to n. Solution, 2 less than or equal to 2 and 3, for all n greater than or equal to 1. 2 and 3, 2 and 2, O with c equal to 2 and no equal to 1. Example 5, find upper bound for f equal to n. Solution, nn for all n greater than or equal to 1, 1.13 asymptotic notation, and O with c equal to 1 and no equal to 1. Example 6, find upper bound for f equal to 410. Solution, 410, 410, for all n greater than or equal to 1. No uniqueness, there is no unique set of values for no and c, improving the asymptotic bounds. Let us consider 100n plus 5 equal to O. For this function, there are multiple no and c values possible. Solution, 100n plus 5 less than or equal to 100n plus n equal to 101n less than 101n. For all n greater than or equal to 5, no equal to 5 and c equal to 101n. For all 5 less 5n, 105n less than 105n. For all n greater than or equal to 1, no equal to 1, and c equal to 105n for all in quotation. Similar to the O discussion, this notation gives the tighter lower bound of the given algorithm, and we represent similar to the O discussion, this notation gives the tighter lower bound of the given algorithm, and we represent it as f equal to q. That means at larger values of n, the tighter lower bound of f is g. For example, if f equal to 100n2 plus 10n plus 50, g is size n. The notation can be defined as equal to f. There exists positive constant c and no such that 0 cgf for all n. No, g is an asymptotic tight lower bound for f. Our objective is to give the largest rate of growth g, which is less than or equal to the given algorithm's rate of growth f omega. Examples. Example 1. Find lower bound for f equal to 5n, 2. Solution, c, no such that, 0 c n2, 5n c n2 less than or equal to 5n equal to 5 and nowhere 1, 5n equal to with c equal to 5 and no minus 1. Example 2. Prove f equal to 105 equal to q. Solution, c, no such that, 0 send 2 100n plus 5, 100n plus 5,100n plus 5n equal to 105n, cn, 2 less than or equal to 105n less than or equal to 0. Since n is positive, cn 105 less than or equal to 0 less than or equal to 105. C. Contradiction, n cannot be smaller than a constant. Contradiction n equal to n3 equal to q, ln equal to q. 1.16 theta notation. 1.15 omega q notation. This notation decides whether the upper and lower bounds of a given function are the same. The average running time of an algorithm is always between the lower bound and the upper bound. If the upper bound and lower bound give the same result, then the notation will also have the same rate of growth. As an example, let us assume that f equal to 10n plus n is the expression. Then, its tight upper bound g is O. The rate of growth in the best case is g equal to O. In this case, the rates of growth in the best case and worst case are the same. As a result, the average case will also be the same. For a given function, if the rates of growth for O and Q are not the same, then the rate of growth for the case may not be the same. In this case, we need to consider all possible time complexities and take the average of those. Now consider the definition of notation. It is defined as equal to, there exist positive constants C1, C2, and no such that 0 less than or equal to g of C2g for all n greater than or equal to number. G is an asymptotic type bound for f, is the set of functions with the same order of growth as g. Examples. Example, find plus bound for f equal to n2. N2 solution less than or equal to n2 for all n greater than or equal to 2, n22 equal to 0, with C1 equal to 1/5, C2 equal to 1 and no 2. Example, proven plus O. Solution, C, n2 less than or equal to n less than or equal to Cn2 only holds for n less than or equal to 1. C1n hashtag 0. Example, prove 6n plus O. Solution, C1n2 less than or equal to 6n3c. n2 only holds for nc26. Example, proven plus O. Solution, clon less than or equal to n less than or equal to c2 ln c, 2 greater than or equal to no impossible log n. Important notes. For analysis, we try to give the upper bound and lower bound an average running time. From the above examples, it should also be clear that for a given function, getting the upper bound and lower bound and average running time may not always be possible. For example, if we are discussing the best case of an algorithm, we try to give the upper bound and lower bound and average running time. In the remaining chapters, we generally focus on the upper bound because knowing the lower bound of an algorithm is of no practical importance, and we use the notation if the upper bound and lower bound are the same. 1.17. Why is it called asymptotic analysis? From the discussion above, we can easily understand that in every case for a given function, f, we are trying to find another function, g, which approximates f at higher values of n. That means g is also a curve which approximates f at higher values of n. In mathematics, we call such a curve an asymptotic curve. In other terms, g is the asymptotic curve for f. For this reason, we call algorithm analysis asymptotic analysis. 1.1 8 guidelines for asymptotic analysis. There are some general rules to help us determine the running time of an algorithm. 1. Loops. The running time of a loop is, at most, the running time of the statements inside the loop multiplied by the number of iterations. Executes n times for m plus 2, constant time, c total time. A constant cxn equal to cn equal to O. 2. Nested loops analyzed from the inside out. Total running time is the product of the sizes of all the loops. Outer loop, executed in times for. Inner loop, executed in times for k plus 1. Constant time. 118.7. 7. Why is it called asymptotic analysis? 3. Total time equal to cxnx, n equal to cn, 2 equal to O. Consecutive statements, add the time complexities of each statement, xx plus 1. Constant time, executed in times for my plus 2. Constant time, outer loop executed n times 4. Inner loop executed n times for kk plus 1. Constant time, total time co plus n plus c2 n2 equal to O. 4 if-then-else statements, worst case running time, the test, plus either the then part or the else part. Test, constant if 0 or return false. Then part, constant else part, n4, n plus plus. Another if, constant plus constant if, equals constant return false. Total time equal to q plus n equal to O. 5. Logarithmic complexity. An algorithm is O if it takes a constant time to cut the problem size by a fraction. As an example, let us consider the following program for I2. If we observe carefully, the value of I is doubling every time. Initially, I equal to 1, in next step I equal to 2, and in subsequent steps I equal to 4, 8, and so on. Let us assume that the loop is executing some k times. At kth step 2 equal to n, and at th step we come out of the loop. Taking logarithm on both sides gives log equal to ln. If we assume base minus 2 clog equal to ln k equal to ln total time equal to O. Note similarly, for the case below, the worst case rate of growth is O. The same discussion holds good for the decreasing sequence as well. For I2, another example, binary search. Look at the center point in the dictionary. Is the word towards the left or right of center? Repeat the process with the left or right part of the dictionary until the word is found. 1.20 Simplifying properties of asymptotic notations. Transitivity, f equal to, and g equal to f equal to. Valid for O and Q as well reflexivity, fe. Valid for O and Q. Symmetry, f equal to, if and only if g equal to. Transpose symmetry, f equal to O, if and only if g equal to q. If f is in O for any constant k greater than 0, then f is in O. If phi is in O and f is in O, then is in O G1. If f is in O and f2 is in O, then f1f is in OG1. 1.21 commonly used logarithms and summations. Logarithmus log x equal to y log x ln equal to logo. 1.20 simplifying properties of asymptotic notations. Log xy equal to log x plus logi. Log kn, ln. K equal to 1k equal to 1 plus 2 plus 1p plus 1k equal to 1. Arithmetic series, geometric series, harmonic series, other important formulae. 1.22 master theorem for divide and conquer recurrences. All divide and conquer algorithms divide the problem into subproblems, each of which is part of the original problem, and then perform some additional work to compute the final answer. As an example, a merge sort algorithm operates on two subproblems, each of which is half the size of the original, and then performs additional work for merging. This gives the running time equation. The following theorem can be used to determine the running time of divide and conquer algorithms. For a given program, first we try to find the recurrence relation for the problem. If the recurrence is of the below form, then we can directly give the answer without fully solving it. If the recurrence is of the form t equal to at plus, where greater than or equal to, b greater than 1, k greater than or equal to 0, and p is a real number, then 1 if a bk, then t equal to o, 2 if a equal to bk, c if p minus 1, then t equal to o, 3 if a bk, a if p greater than or equal to 0, if a bk, a if p greater than or equal to 0, then t equal to o, if p less than 0, then t equal to o. 1.23 divide and
So
conquer.
this is very important master theorem. You have to understand this. If a is greater than a, you can see here a is the coefficient of this t n by b. P is true here, or and then we can see here n's power is k and logarithm power is p. Okay. Now if you see a is greater than b the power k, here both are equal. A is not greater than b the power k, and b the power k, what is k? N the power. So both are not equal, so first will be not there. If suppose if a was the coefficient of t the power n by 2 was greater than this one, what I can do, I will take a brush. Okay, so let's say if this b the power k, what I can do, this b the power k was greater than was less than a, then what we can do, then Tn is equal to n the power log a b. Okay, where a is the coefficient of t the power n by 2, t the power b, and b is the denominator of n. Okay, and if a is equal to b the power k, then we can say if p is greater than -1, then Tn is equal to n log a b. log p plus 1 n. Okay, and this is p is greater than minus 1. Here is the p, and p is equal to the minus 1, then we can say p is equal to minus 1, then we can say there's a tn is equal to theta and log a b log n. If p less than minus 1, the tn is equal to theta and log ab. If a less than bk, if p is greater than equal to 0, then tn is equal to theta n the power k log pn. And if p less than 0, then tn is equal to theta big of n the power k.
Master theorem, problems and solutions. For each of the following recurrences, give an expression for the runtime t if the recurrence can be solved with the master theorem. Otherwise, indicate that the master theorem does not apply. Solution. T.
So you can see the power of 1, tn is equal to 3t n by 2 plus n square, where a is 3 and b is 2, and when you see it, and k is n the power k log p, okay, mn n the power k n square 2 square 4. So this is greater than, b is greater than a, and b is, and p is greater than equal to 0 because it is not there, so it will be theta of nk log pn, the n square. P is 0, so it will be n square. Master theorem 3 case a. Okay,
Equal to 3 trillions plus n2 equal to t equal to 0. Problem 2t equal to 4 trillions.
Here you can see here a is 4, b is 2, k is 2. When you calculate b square, b to the power k, 2 to the power 2, 4, both are equal, then it is the case number 2, and the power of p. Then you see the power of the p. The p is greater than minus 1 here because it's 0. The case number 1. If was equal to minus 1, then case number this one, b, second b, and if are less than minus 1, then the case number second c and log ab. So here the power of the p is the power of logarithm is p is equal to 0 here, so it will be the case number 2. You can see the case number 2a, it will be there. And so what I can do, I will have a mouse and then I will tell you what is going on. So here you can see here, so that's why it will be n square log n.
N. Solution. T equal to 4 trillions plus n2 equal to t equal to 0 problem minus 3. Solution. 5.
So here you can see tn is equal to t n by 2 plus n square. So to the power 2 to 4, and b is and a is 1. That's why this is greater than this a. Okay, this is the case 3, and the p is greater than equal to 0. Yeah, p is greater than equal to 0, so it will be n the power k n square and logarithm, okay, n square, okay, log p is the same or less than or the power nk. Now problem 4, tn 2 the power n t n by 2 plus n the power n. So here this a is n, b is 2, and to the power n is the greater than हो गया, ठीक है. So and the p is greater than equal to 0, so it will be n the power n does not apply, a is not constant, so n the power n, oh, a is not constant, it's, oh, nice. So it not apply. It's very important problem.
Problem 4, T2, nt plus n. Solution T equal to 2, T plus n does not apply.
is not
1.2
constant.
two-master theorem for divide and conquer recurrences. Problem. Solution.
So here a lot of problems are there. Total 20 problems are there. I am doing one by one each, and you can yourself also do it. Here again A is 16 and B is 4 and K is 1, so A is greater than B. Okay, now it will be simple. Log n log P plus 1, and P is 0, so n log P, n log n. Okay, but I think so it's not so easy. And so yes, this one. A is greater than B k power k, then n not n log n. This is not will be appear. This is not equal. They are not equals. Okay, they are not equal. It will be greater than B, so it will be n log AB. N log AB. A and B. Then it will be AB. It will be square. N square. Yeah. Correct option is n square. And here Tn 2Tn by 2 n log n. Both are equal. A and B are equal, so A and B are equal, and P is greater than minus 1. This is also true. You can see here. No, it's equal to minus 1. Not greater than minus 1 is equal to minus 1. It means n log AB and log n. N log AB 2 and it will be 1 log n. Master theorem case to be.
T equal to 2 trillions plus n ln equal to T equal to O.
Okay, fine.
Trillion.
I am doing one by one. And problem number 8 now. T n, and this is you done already. And log n 2. This is equal, and this is greater than 1. So it will be n log AB, n log nk, n log AB, log P plus 1, n log AB, and n log AB, n log AB, n log AB is on both cases. A greater than BK and A equal to BK. On all cases, n log AB. For A greater than BK, you can see n log AB only. And if A is equal to BK, then see the P. If P is greater than minus 1, then n log AB will be definitely there. And then it will be log P plus 1 n. Okay, and if P is minus 1, then log n. And P less than minus 1, then n log AB. Say similar like that. If P less than minus 1 and ABK, then n log AB. Okay, simple. And in this exceptional case only, if A less than BK, if we check out if P is greater than or equal to 0, then write Tn is equal to nk log Pn. Okay, nk log Pn. And if P less than 0, then Tn is equal to big of nk. Okay, you can see here nk log Pn. If A less than BK and P is greater than or equal to 0, then Tn is equal to theta nk log Pn. And if P less than 0, then Tn is equal to big of nk. Okay, if P greater than or equal to 0, then Tn is equal to theta nk log Pn. If P less than 0, then Tn is equal to big of nk. You can see Tn is equal to 2t n by 4 and 0 minus 0.51. So you can see 2t n by 4 plus n 0.51 Tn is equal to 3b. Okay, no, simple. 0.51 square of it. Both are equal. And if the equal, it means that This is greater than this one. So it is 3b. Okay, fine.
plus n2 ln equal to t equal to 0. Solution t problem 12 equal to 64.
Function is not positive. Function should be positive, is not apply here.
Trillions n2 ln equal to does not apply. Problem 14 solution t 6.
Problem number 12, you can see 9 n square. Okay. It should be 3b, not 3. It should be 3b because there is no logarithm part now. It should be master case 3b. Log n, no? N square. Okay, fine. Section T, this is for n the power n. For the master sum 3, n the power n. For the power, this is n factorial. Master 3 and 3.
16 trillions plus n equal to t equal to 0. Solution t equal to 4 trillions plus cn equal to t.
Root 2 tn by 2 plus log n. Root 2 tn by 2 plus log n. Tn is equal to theta root n. Okay, fine. And log 3. Fine. Okay, fine. Fine. And log n, yeah. This is 3b, not 3a. It's 3b. You can see, yeah. This is 3. Okay, 3a. Okay, this is 3a.
Equal to O. Problem 19. Problem. Solution t equal to
n by 2, 3t, and 3. Both are equal. Log n. Okay, fine. And log n.
2 trillions plus ln equal to t. Problem. Solution. Problem. Solution. Solution. Problem. Solution. Problem. Solution. Solution. 1.24 Master Theorem for subtract and conquer recurrences. Let t be a function defined on positive n and having the property. For some constants c, a greater than 0, b greater than 0, k greater than or equal to 0, and function f, if f is in O, then. 1.25 variant of subtraction and conquer master theorem. The solution to
Subtract and conquer recurrences. The 1.24 and TS was problem one solution for this positive one. For divide and conquer recurrences and subtract and conquer. Divide and conquer was already, and now subtract and conquer. A, t and minus b subtract and conquer it. Here is a simple case. Check out the A. If L is less than 1, then big O is n the power k. A is equal to 1, big of n the power k plus 1. A is greater than 1, n the power k, a the power n by b. Okay, you can see here.
1.24 master theorem for subtract and conquer recurrences. Let t be a function defined on positive n and having the property. For some constant 0, b greater than 0, k greater than or equal to 0, and function f, if f is in O, then 1.25 variant of subtraction and conquer master theorem. The solution
इसमें देख सकते हैं इसका सिंपल है, उससे थोड़ा सिंपल है. डिवाइड एंड कॉन्कर से इसका थोड़ा इजी है. इसमें सीधे देखना है n लेस देन इक्वल 1 है तो c क्या होगा, ग्रेटर देन 1 है तो ये a t n माइनस b और प्लस f n b. a पॉजिटिव होना चाहिए, b पॉजिटिव होना चाहिए, k जो है वो ग्रेटर देन इक्वल टू 0 होना चाहिए. फंक्शन ऑफ f n. If fn is in order of n the power k, then k greater than equal to 0. तो ये कंडीशंस देखनी है. अगर a लेस देन 1 है, ये वाला ये a लेस देन 1 है तो ऑर्डर द बिग ऑफ n द पावर क्या होगा, ये n है, और जो k है वो ये सेम n द पावर क्या हो जाएगा. और a इक्वल टू 1 है तो फिर ऑर्डर ऑफ n द पावर k प्लस 1 हो जाएगा. अगर a 1 हुआ तो a ग्रेटर देन 1 हुआ तो n द पावर k a द पावर n b हो जाएगा, n बाई b हो जाएगा, a द पावर n बाई
B.
b हो जाएगा. इससे
Marsh theorem. ये theorem
the equation t equal to t plus tn plus ssn, where 0 less than 1% and ss greater than 0 are constants, is O. 1.26 method of guessing and confirming. Now, let us discuss a method.
ये इसका सीधे याद रखना है, n log n होता है, अगर ऐसा आ जाता है अल्फा n प्लस टी 1 माइनस अल्फा n, दोनों जोड़ रहे हैं और बीटा n अलग से लिखा है. और जो अल्फा है वो 0 से लेके 1 के बीच में कोई वैल्यू हो सकती है, फ्रैक्शन में वैल्यू होगी. 0 से लेके 1 के बीच में तो फ्रैक्शन में होगी.
प्रोग्रामिंग में ऐसे
बीटा
डालने पड़ते हैं.
बीटा ग्रेटर देन 0 होना चाहिए और फिर n log n हो जाएगा.
Which can be used to solve any recurrence. The basic idea behind this method is guess the answer and then prove it correct by induction. In other words, it addresses the question, what if the given recurrence doesn't seem to match with any of these methods? If we guess a solution and then try to verify our guess inductively, usually either the proof will succeed or the proof will fail. As an example, consider the recurrence tn plus n. This doesn't fit into the form required by the master theoremist. Carefully observing the recurrence gives us the impression that it is similar to the divide and conquer method, dividing the problem into n subproblemus. 1.24 master theorem for subtract and conquer recurrences, each with size n. As we can see, the size of the subproblems at the first level of recursion is n. So, let us guess that t, O, and then try to prove that our guess is correct. Let's start by trying to prove an upper bound t less than or equal talk ln, t equal to ntn plus nnk, n ln plus n equal.
ये एक्चुअल में टेक्स्ट नहीं है, रीड नहीं कर पा रहा है, फोटो में आ रहा है. टी एन इज इक्वल टू रूट एन, इसमें क्या है इंडक्शन लगा दिया प्लस एन, टी रूट एन वापस इसमें डाल दिया, सी रूट एन लॉग रूट एन ये आ गया. इसमें मैथमेटिक्स में होता है ना, उसमें एलिमिनेशन मेथड, वो उसमें सब्स्टिट्यूशन मेथड, सब्स्टिट्यूट कर दिया इसको उससे वापस, और फिर ये वापस एन सी लॉग रूट एन प्लस एन हो गया. फिर इसमें फिर n बाई इसका लॉगरिथम का जो फॉर्मूला होता है n 1/2 आगे चला गया, और फिर इसको करके सी एन लॉग एन, वही है ऑर्डर ऑफ n log n आ जाएगा. ऑर्डर ऑफ n log n, ये बताया ना कैसे आएगा, कैसे आ गया, ऑर्डर ऑफ n log n आ गया, ऐसा कराता है. ठीक है, अगर ऐसा आ रहा है तो ऑर्डर ऑफ n log n होगा. ठीक है, और तो लास्ट ये फिर दूसरा इसका भी वैसे ही है, टी एन रूट एन टी रूट एन प्लस एन ग्रेटर देन इक्वल टू रूट एन, इसमें उल्टा है।
लेकिन ये कोडिंग जावा वाली होगी आपकी,
हम्म,
ये जावा का है,
सबका सेम रहता है।
नहीं रहती।
प्रॉब्लम सोल्व करने का तरीका सेम ही है, वो बस कोड लिखने का प्रोग्राम लिखने का तरीका बस अलग होता है, कुछ फर्क नहीं पड़ता। जावा में करते हो, पाइथन में करते हो, सी प्लस प्लस में करते हो, वो तरीका सेम रहेगा, सोल्व करने का तरीका सेम रहेगा, बस वो सिंटेक्स अलग होता है, लिखने का तरीका अलग होता है। अब ये जावा में कहाँ लिखा है, ये मैथमेटिकल इक्वेशंस है। कोड जो लिखे होंगे वो तो नेक्स्ट चैप्टर से चालू होंगे, इसमें कुछ कोड नहीं
फॉर्मूले
है।
होता है।
n. K ln plus n n K ln plus n equal to greater than or equal to k. T equal to plus n n C n log ln.
फंस जाता है।
तो ये देखो,
एकदम 2-3 जंप कर दिया।
दिस इज इनकरेक्ट एंड इज सफिशिएंटली लार्ज, लेस देन इक्वल टू 1 किया ना यहाँ पर, फॉर एनी कांस्टेंट के फ्रॉम द अबव प्रूफ वी कैन सी दैट आवर गेस इज इनकरेक्ट फॉर द लोअर बाउंड। फ्रॉम द अबव डिस्कशन वी अंडरस्टूड दैट इज टू बिग, ये वाला ये बहुत बड़ा है। हाउ अबाउट एवरेज ऑफ एन, द लोअर बाउंड इज इजीली टू प्रूव डायरेक्टली। इन्होंने पूरा प्रूफ किया कि ये बिग ऑफ एन है, या फिर ये थीटा ऑफ एन, थीटा ऑफ एन के लिए भी प्रूफ करेंगे इसको, सेम वो डाल के ग्रेटर देन इक्वल टू एन होना चाहिए। नाउ लेट अस प्रूव द अपर बाउंड ऑफ दिस थीटा एन, जो डाला उसके अंदर सी रूट एन greater than equal to nc plus 1. From the above induction we understood that theta n is too small and theta n log n is too big. ये छोटा है और थीटा एन log n वो जो आया था पहले वो बिग है, so we need something bigger than n and smaller than n log n, वो थीटा हो। So how about n root n log n, तो फिर ये देखो
It's n equal to n.
अब इसमें फिर n रूट एन log n ये डाल देंगे, n रूट log n डाल दिया यहाँ पर, फिर यहाँ पर चेक किया, ये ग्रेटर देन c ग्रेटर देन 1 डाल के देखो इसमें, प्रूविंग लोअर बाउंड ऑफ n log n, ये हो गया हमारा बीच वाला n log n बीच वाला हो जाएगा
E log ln Cn plus NCn log ln if c greater than or equal to 1. The last inequality assumes only that 1 degree Celsius dot ln. This is correct if n is sufficiently large and for any constant c, no matter how small. From the above proof, we can see that our guess is correct for the upper bound. Now, let us prove the lower bound for this recurrence. The last inequality assumes only that 12k ln. This is incorrect if n is sufficiently large and for any constant k. From the above proof, we can see that our guess is incorrect for the lower bound. From the above discussion, we understood that O is too big. How about E? The lower bound is easy to prove directly. Now, let us prove the upper bound for this O. From the above induction, we understood that E is too small and O is too big. So, we need something bigger than n and smaller than ln. How about n ln? Proving the upper bound for n, ln. Proving the lower bound for n ln. The last step doesn't work. So, O doesn't work. What else is between n and ln? How about log ln? Proving upper bound for log ln. Proving lower bound for log ln. From the above proofs, we can see that t less than or equal to sin log ln, if c greater than or equal to 1, and t greater than or equal to log ln, if k less than or equal to. Technically, we're still missing the base cases in both proofs, but we can be fairly confident at this point that TO 1.27 amortized analysis. Amortized analysis refers to determining the time averaged running time for a sequence of operations. It is different from average case analysis because amortized analysis does not make any assumption about the distribution of the data values, whereas average case analysis assumes the data are not bad. That is, amortized analysis is a worst case analysis, but for a sequence of operations rather than for individual operations. The motivation for amortized analysis is to better understand the running time of certain techniques, where standard worst case analysis provides an overly pessimistic bound. Amortized analysis generally applies to a method that consists of a sequence of operations where the vast majority of the operations are cheap, but some of the operations are expensive. If we can show that the expensive operations are particularly rare, we can change them to the cheap operations and only bound the cheap operations. The general approach is to assign an artificial cost to each operation in the sequence, such that the total of the artificial costs for the sequence of operations bounds the total of the real costs for the sequence. This artificial cost is called the amortized cost of an operation. To analyze the running time, the amortized cost thus is a correct way of understanding the overall running time, but note that particular operations can still take longer, so it is not a way of bounding the running time of any individual operation in the sequence. When one event in a sequence affects the cost of later events, one particular task may be expensive, but it may leave data structure in a state that the next few operations become easier. Example, let us consider an array of elements from which we want to find the kth smallest element. We can solve this problem using sorting. After sorting the given array, we just need to return the kth element from it. The cost of performing the sort is O. If we perform n such selections, then the average cost of each selection is O equal to O. This clearly indicates that sorting once is reducing the complexity of subsequent operations. 1.28 Algorithms Analysis, Problems and Solutions. Note, from the following problems, try to understand the cases which have different complexities, O, etc. Problem 21. Find the complexity of the below recurrence. Solution, let us try solving this function with substitution.
Okay, let me find the solution.
Equal to 3. Solution, let us try solving this function with substitution. T32, t equal to 3, t equal to 3, t equal to 3. This clearly shows that the complexity of this function is O. Note, we can use the subtraction and conquer master theorem for this problem. Problem minus 22. Find the complexity of the below recurrence. Solution, let us try solving this function with substitution. T, 2t to 1, t22 to 2 minus 1, minus 1, equal to 23 to 2t to 1. T, 22 to 21 minus 20. T equal to 1. Complexity is 0. Note that while the recurrence relation looks exponential, the solution to the recurrence relation here gives a different result. Problem 23. What is the running time of the following function? Public void function solution. Consider the comments in the below function. Public void function int I1 S1. S is increasing not at rate 1 but I. 1.27 amortized analysis. While SECI, system output println, we can define the S term as according to the relation 5 equal to 5 minus 1 plus I. The value of t increases by 1 for each iteration. The value
This is not
contained.
5, this is SI. SI is this SI. SI minus 1, this below it, and plus I. Okay, this is not 5.
In at the ith iteration is the sum of the first positive integers. If k is the total number of iterations taken by the program, then the while terminates if s loop. Problem 24, 1 plus 2 plus kkn equal to 0. Find the complexity of the function given below. Public void function int I count 0 for solution, count plus plus, void function int I count 0 for count plus plus. In the above mentioned function, the loop will end if I2 nt equal to O. The reasoning is same as that of problem 23. Problem 25. What is the complexity of the program given below? Public void function int I j k count 0 for car count plus plus. Solution. Consider the comments in the following function. Public void function int I j k count 0. Outer loop execute 1/2 times 4. Middle loop executes n 2 times 4. Inner loop execute long times for count plus plus. The complexity of the above function is O. Problem 26. What is the complexity of the program given below? Public void function int I j k count 0 for count plus plus. Solution. Consider the comments in the following function. Public void function int I j k count 0. Outer loop execute n 2 times 4. Middle loop executes long times 4. Inner loop execute long times for count plus plus. The complexity of the above function is O. Problem 27. Find the complexity of the program given below. 1.28 Algorithms Analysis, Problems and Solutions. Public void function if return 4 system out println break solution. Consider the comments in the following function. Public void function
Here
constant time
because
if
of break,
return.
no, here because of break it will break. Here it will run only one time for each end. It will run only one time because when it comes in the loop, it will break it. So it will run n times only, or big of n. You can see here.
Outer loop executes n times for inner loop executes only time due to break statement. For system out println break, the complexity of the above function is O, even though the inner loop is bounded by n. Due to the break statement, it is executing only once. Problem 28, write a recursive function for the running time t of the function given below. Prove using the iterative method that t equal to public void function if return for function system out println solution. Consider the comments in the function below. public void function, constant time if return. Outer loop execute n finis 4. Inner loop executes n times 4. Constant time system out println function. The recurrence for this code is clearly t equal to t plus cn2 for some constant c greater than 0, since each call prints out n2 asterisks and calls itself recursively on n3. Using the iterative method, we get t equal to t plus cn. Using the subtraction and conquer master theorem, we get t equal to 0. Problem 29 determine bounds for the recurrence relation t equal to
theta and q. Okay. Average time complexity of that is n cube.
2 trillions plus log.
2t n by 2 plus n log n. You can see by calculating n, both a and b are equal here. A b the power k. B the power k is 1, so it is 2 is equal. For equal, we will check out what is the power k. No. The power, what is the power p? P is greater than -1. Okay, so we will do n log ab, that is 1, n log, we increase the power of it, n log square n. It is the answer by divide and conquer method.
Solution using divide and conquer master theorem, we get O. Problem 30, determine bounds for the recurrence t equal to t plus t plus t plus n. Solution substituting in the recurrence equation, we get t less than or equal to c plus c plus c plus cn less than or equal to kn, where ek is a constant. Problem 31, determine bounds for the recurrence relation t equal to t plus 7. Solution using master theorem, we get problem 82, prove that the running time of the code below is public void red into k1 while k3k. Solution, the while loop will terminate once the value of k is greater than or equal to the value of n. In each iteration, the value of k is multiplied by 3. If I is the number of iterations, then k has the value of 3 after I iterations. The loop is terminated upon reaching I iterations when 3 feet in I log n, which shows that I equal to. Problem 88, t equal to t plus I equal to 1t equal to t plus sigma. Sigma t1 plus 1 I equal to 1 I equal to n 6 2.
This is the
Solve the
formula.
following recurrence.
This is the summation formula of I square minus I. You can understand the formula from that. This is I come from that arithmetic progression, and this come I square. This is all that derivations come from the arithmetic progression chapter. You can check out that chapter, and this is the formula that sigma of all I to 1 to n. I square is equal to n plus 1 to n plus 1 upon 6, and I is n plus 1 upon 2. And it is I cube also, n square plus n plus 1 all square divided by 4.
Solution by iteration equal to t plus n. T equal to 0. Note, we can use the subtraction and conquer master theorem for this problem. Problem 34 fibble. Consider the following program. If then return 1 else return fib plus fib. Solution, the recurrence relation for the running time of this program is. Note T has 2 recurrence calls indicating a binary tree. Each step recursively calls the program for n reduced by 1 and 2, so the depth of the recurrence tree is O. The number of leaves at depth n is 2, since this is a full binary tree, and each leaf takes at least O computations for the constant factor. Running time is clearly exponential in n. Problem 35, running time of following program for public void function for system out println. Solution, consider the comments in the function below. Public void function, this loop executes n times 4. This loop executes j times, with j increased by the rate of I for system out println. In the above program, the inner loop executes ni times for each value of I. Its running time is nx equal to O. Problem 36, what is the complexity of log 1? Solution, using the logarithmic property, log c equal to log x plus log e, we can see that this problem is equivalent to I equal to 1 log I equal to log 1 plus log 2 plus log n equal to log less than or equal to log less than or equal ton log. This shows that the time complexity equal to O. Problem 37. What is the running time of the following recursive function? First, write the recurrence formula and then find its complexity. Public void function if return 4. Solution. Consider the comments in the function below. Public void function, constant time if return. This loop executes with recursive loop of value 4. 1.28 algorithms analysis, problems and solutions. We can assume that for asymptotical analysis, k equal to for every integer k greater than or equal to. The recurrence for this code is t equal to 3 trillions plus 0. Using master theorem, we get t equal to O. Problem 88. What is the running time of the following recursive
we
function?
get because A is 3 and B is 3 and B the power k and k is here 0 because we know k is n the power k log p, and so we put 3 the power 0, so it is greater than this, and then direct the first case. What the first case is n log the power ab, log a, and this is a base 3, so it will become 1 n, so theta of n will be the answer.
First, write a recurrence formula and show its solution using induction. Public void function if return for function. Solution, consider the comments in the below function. Public void function. Constant time if return. This loop executes 3 times with recursive call of n1 value for function. The EF statement requires constant time. With the for loop, we neglect the loop overhead and only count 3 times that the function is called recursively. This implies a time complexity recurrence, Tc, if n less than or equal to 1, c plus 3 trillions if n greater than 1.
Because it is given that n is less than equal to 1. Because n is less than equal to n 1, so we we using the and this equation is there, so we are using subtraction conquer, and we know if n is less than equal to 1, then it is will be theta of 3 to the power n, and if n is greater than 1, then it will become 3 or theta becomes 3 to the power n plus 1. Okay, as you can see here. Okay, see if n is less than equal to 1. Okay, return n is greater than 1, so we get theta. Okay, fine. As you can see here, let me show you the equation. Yeah. Tn is equal to c and n. Okay, this is given. Okay, if a depend on a, that a is equal to 1. No, that is a is less than 1. A means this one. This, that is n minus 3 and a is 1. A is 1, so it becomes n the power k plus 1. Okay, k is greater than or equal to 0. Okay. K is the power of this and k plus 1. Fine.
In subtraction and conquer master theorem, we get t equal to 0.
So it is greater than 1. So theta is 3 to the power n. To the power this become this to the power n. Okay. This becomes 3 to the power n.
Problem 39. Write a recursion formula for the running time t of the function f, whose code is given below. What is the running time of function as a function of n? Public void function if return. For system outprint function solution, consider the comments in the below.
Okay, let me do it myself.
39.
If n is less than equal to 1. Okay, return it, and I less than it will run n times. Okay, 0.89 plus n times it running plus some constant, so it will become AB 0.8. What I think is that no 0.8 0.n square. Okay, definitely this is n and n times. Everything it will become different because this is 0.8n.
Constant time if return. This loop executes
0.8 no by 1. You can use 4 by 5 n. 4 by 5n. B is 5. This is 4. So 5 is greater than 4. Okay. And
Oh, tamia dikatan.
take that.
Papan dikon one.
N times with constant time loop for system out println, recursive call with point in function. The recurrence for this piece of code is t equal to t plus o equal to t plus o equal to t plus o. Applying master theorem, we get t equal to o. Problem 40, find the complexity of the recurrence t equal to 2 trillions plus ln. Solution, the given recurrence is not in the master theorem format. Let us try to convert this to the master theorem format by assuming n equal to 2. Applying the logarithm on both sides gives ln equal to log m equal to ln. Now, the given function becomes 2. Make it simple, we assume s equal to t equal to s equal to t equal to s equal to 2 seconds plus m. Applying the master theorem would result s equal to 0. If we substitute m equal to ln back, t equal to s equal to log ln. Problem 41, find the complexity of the recurrence.
T root n plus log n to the power 1 t to the power n. Okay. This is 2 root 2n. Let's assume that n is 2 to the power n. It will become 2 t root to the power n plus n. Okay, plus n. Plus n. 2 to the power n. 2 sm by 2. Now you can apply. Both are equal and m log m. M log m. Log of log log m.
các जन्मदिन हो मान के सबको सब पूरी फैमिली बैठी हुई है तीनों बेटा
t to t plus 1. Solution, applying the logic of problem minus 40 gives s equal to $+ plus 1. Applying the master theorem would result in s equal to o. Substituting m equal to ln gives t equal to s equal to o.
आराम भी थी भाई है ना आठवीं बेटी से भाइयों भी एक बयान हो गई इको जुड़ाई है अपन सारे ही अपन ठीक है भाई ना उनके
This one.
हां ओ वीडियो ओ ये जेपीआर जे था केडो सो भी रामवीर को भाई है ओ अलकुमार एक प्यार हुई नरेंद्र की भाई है इके दो है ये पूरा मैं गिने आज एने में नरेंद्र है को पूरा मतलब आपकी फैमिली में 21 जन आए हैं जेठा हमारे अब्सेंट इनको ने इन राजू को भाइयों को नहीं नरेंद्र को
टोटल ये कितने आते
और एक जुआई भी को नहीं 18 है ये 3 लाइव है पूरा 21 है एक फैमिली 21 जना की फैमिली मांग जियो मुसाकी हैं बड़ी है 3 बेटा है बच्चे बोलो
आपने वाला एमपी जेपी का विवाह करा आपने बनो 21 जन
का दूसरी जत्ता है आपा फुटा रे
भगवान सिंह कमल सिंह एमपी जेपी
अरे भगवान सिंह कमल सिंह
वो छोड़ के भयो
Problem 42. Find the complexity of the recurrence t equal to 2.
बाबू के तीन पच गुड्डू वा काइना भाई अंकल जी दो बांके अंकल जी बड़ी सरोज मां अगला मिला जरा 50 दिन जाए
नहीं आपा की
फैमिली के साथ
आप थाऊ वाऊ तो
Trillions plus 1. Solution. Applying the logic of problem 40 gives s equal to 25 plus 1. Using the master theorem results s equal to 0 equal to 0.
Applying logic, you're gonna go
ओ जी आगू ताड़ी
put his add to the column.
गंगा
To the power m/2. Like this again.
Problem 41. Find the complexity of the
Again, like this root to the power m, root to the power m, to m/2, then m/2. Okay, plus 1, and 2 is greater than 1, so it becomes this direct log m. Direct m. Log m. Because that is 0. That is 0. Okay. Log m. And the power k log m.
आपा घूमिया ना अच्छा सब्जी दिया केला
recurrence t equal to t plus 1. Solution. Applying the logic of problem minus 40 gives s equal to $+ plus 1. Applying the master theorem would result in s equal to O. Substituting m equal to ln gives t equal to s equal to O. Problem 42. Find the complexity of the recurrence t equal to 2 trillions plus 1. Solution. Applying the logic of problem 40 gives s equal to 25 plus 1. Using the master theorem results s equal to 0 equal to 0. Substituting m equal to ln gives t equal to O.
Both
Problem.
are equal. Both are equal. O is not equal. This is better. Direct we will put log 2. This is log n.
43%. Find the complexity of the function given below. Public int function if return 1. 1.28 algorithms analysis, problems and solutions. Else return +1 solution. Consider the comments in the below function. Public int function if return 1. Else constant time executes n plus 1 times return +1. Problem -44. Analyze the running time of the following recursive pseudocode as a
The
function.
equation becomes same. Tn is equal to root n minus root n plus 1. Again log n, it will become log n. By using this one, log n. To the power 0 both are equal and become log n.
Function of n. Public void function if returned. Else counter 0 for I1 to A2 function. for I minus 1 to n3 do counter counter plus 1. Solution. Consider the comments in below pseudocode and call running time of function as t, public void function, if return, constant time else counter, 0. This loop executes times with n value hall in every call for I1 to do function. This loop executes n3 times with constant time loop for I minus 1 to n3 do counter counter plus 1.
You can see here n cube times it will run. This will run. This will run 8 times. 8 times it will run function in by 2. And value half in every cell.
T can be defined as follows. T equal to 1 if n less than 2, equal to 8 trillions plus n3 plus 1 otherwise.
Equation वापस master theorem लगा दो. To the power 3, both are equal. N cube log n. ऐसे होता है.
Problem 45 temp minus 1 repeat. Find the complexity of the pseudocode given below. For I1 to n11 temp plus 1 until n less than own solution. Consider the comments in the pseudocode given below. Temp, 1 repeat constant time. This loops executes n times for I1 to n temp plus 1. Recursive call with value until...
इसमें भी वही कॉन्सेप्ट लगा. टेप 1 रिपीट, उसको n टाइम्स रिपीट कर रहे हैं. टेप प्लस 1 कर रहे हैं, यही कर रहे जोर से जा रहे हैं इसको पूरा. लेकिन इसमें एक और चीज़ हो रही है, n इज इक्वल टू n बाई टू भी हो रहा है, लेकिन ये बाद में हो रहा है n बाई टू until n इज लेस देन इक्वल टू, मतलब log n भी चल रहा है, n टाइम्स वो रिपीट भी चल रहा है और फिर उसको हाफ हाफ करते जा रहे हैं जब तक 1 नहीं हो जाता. n log n दिस आएगी, n इक्वल टू n बाई टू, n equal to n by 2 plus n. This is n times it's running. It's running n times. Okay, and this is become tn by 2 plus is running plus n. Then we apply that master theorem. मास्टर थ्योरम से वो n नहीं आएगा क्योंकि वो 2 है, वो बड़ा है उससे, तो वो n रह जाएगा as it is.
The less than on, the recurrence for this function is t equal to t plus n. Using master theorem, we get t equal to O. Problem 46 running time of the following program. Function. For system out println. Solution. Consider the comments in the function given below. Public void function. This loops executes n times for 1.28.
इसमें आज इसका 10% पूरा हो जाएगा किताब का. 400 पेजेस हैं, 400 पेजेस लग दो. मेरे जो पेजेस हैं ना 400
पूरे एक दिन में नहीं आएगी.
10% आज हो जाएगा, 10 दिन के अंदर पूरी किताब करने का विचार है.
10 दिन में करेगा
ये इतना लगेगा क्योंकि सवाल भी काफ़ी अच्छे हैं और इम्प्लीमेंट भी करना होता है ना, जो पढ़ा है उसको सॉल्व भी करके इम्प्लीमेंट करना होगा. 10 दिन में हो जाएगी. साथ में पहले और भी चीज़ें चलेगी, लीड कोड चलेगा और भी काफ़ी कुछ चलेगा, तो ये 10 दिन में करने का
DSA वाला चलेगा.
हाँ वो भी चलेगा. ठीक है, तो ये करते हैं.
DSA में क्या क्या है?
ये है डेटा सेट एल्गोरिथम है, ये सिलेबस में ये है सिलेबस.
वहाँ तो नॉर्मल होगा.
हाँ
इम्पोर्टेंट फीचर्स होंगे.
हाँ, ये तो पूरा
वहाँ देंगे तो
ये तो डेवलपर्स के लिए है पूरी किताब, जो कोडिंग वोडिंग करता है. ये देखो जो माइक्रोसॉफ्ट में सॉफ्टवेयर इंजीनियर मैनेजर में के तौर पर काम किया है मैंने.
ये थोड़ा ना
IBM में, अमेजन में. तो ये सब प्रॉब्लम यूज होती है वहाँ IBM में, बड़ी बड़ी कंपनीज में सारी
वहाँ पहले भर्ती होने पर होती है.
वो भी हो जाएगा. जब सॉल्व होगा तो वो बुलाएंगे ना, सॉल्व नहीं होगा तो क्यों बुलाएंगे. सॉल्व होना चाहिए तब बुलाएंगे, वरना वहाँ पर कंपनी लग होगा.
Algorithms analysis, problems and solutions. For the above function, recurrence function can be given as t equal to t plus 1.
So you can see this 43 n less than equal to 2 रिटर्न, तो रिटर्न इसमें है, इसमें फ्लोर भी लगा हुआ है. ये कांस्टेंट टाइम में हो जाएगा, ये फ्लोर में होगा रूट एन प्लस वन हो जाएगा, ठीक है। अब उसमें लग जाएगा फॉर्मूला टी रूट एन प्लस वन, उसमें वापस वो वही फॉर्मूला लग जाएगा, log n वाला हो जाएगा, log n वाला। इसका पहले ऑलरेडी प्रॉब्लम में 41 में इसका निकाला है, तो देखो ये 41 एस एम को एस एम प्लस वन प्लस एम बाई टू करके इसमें से जैसे करेंगे तो log m हो जाएगा, तो फिर log m से log सब्स्टिट्यूट करेंगे ना, log n हो जाएगा। अभी माना था उसको एस दी पावर m बाई टू था एक्चुअल में, यहाँ पर डालोगे ना रूट m यहाँ पर
टू की पावर m by 2
इसको यहाँ टू दी पावर m बाई टू था, और फिर उसके अंदर सब्स्टिट्यूट किया
टू की पावर m by 2 को 2s m by 2
हाँ, उसको भी दोबारा मान लिया s नहीं m बाई टू मान लिया
m by 2
एस एस हाँ एस, इसको पूरा है ना एस एस फंक्शन मान लिया m बाई टू का, एस m बाई टू को भी उसको भी लिमिट कर दिया, फिर उसको सब्स्टिट्यूट करना पड़ेगा ना, m बाई टू फिर टू एस m बाई टू, फिर वो log n हो जाएगा ना उधर पावर से हटके कुछ जाएगा ना, तो m बाई टू हो जाएगा। मैथमेटिकल लगता है पूरा।
This is same as that of problem 41. Using the master theorem he gives t equal to 0. This loop
ये ऑडियो वाला कौन सी कंपनी का है?
problem minus 44 analyze the running time of the following recursive pseudocode as a function of n. Public void function if returned, else counter 0 for i1 to a2 function, for i minus 1.
वैसे ये 8 टाइम्स इसको रन किया है m बाई टू, और n क्यूब डू काउंटर ये n क्यूब टाइम्स हुआ, ये 8 n बाई टू फंक्शन में n t n बाई टू है, यहाँ पर देखो और n क्यूब है। अब इसका भी सीधा फॉर्मूला है टू दी पावर 3, ये हो गया 8 दोनों बराबर हो गए, ये दोनों बराबर हो गए, तो इसमें लगेगा केस नंबर 2 लग जाएगा इसमें, ठीक है, केस नंबर 2 लग गया, और फिर इसमें p जो है वो ग्रेटर देन -1 है, तो इसमें हो जाएगा ये n क्यूब log n लग जाएगा, तो सही आ गया। बस इस तरह से
And 3 do the counter plus 1. Solution. Consider the comments in below pseudocode and call running time of function as t. Public void function if returned, constant time else counter 0. This loop executes times with n value hall in every call for i1 to do function. This loop executes n 3 times with constant time loop for I minus 1 to n3 do counter plus 1. T can be defined as follows. T equal to 1 if n less than 2, equal to 8 trillions plus n3 plus 1 otherwise. Problem 45 temp minus 1 repeat. Find the complexity of the pseudocode given below. For I1 to n11 temp plus 1 until n less than own solution. Consider the comments in the pseudocode given below.
इसमें भी तो सिंपल ये n टाइम्स रन किया है temp प्लस 1, ये तो पहले किया है ना, ये तो हमने किया अभी n बाई टू t n बाई टू प्लस n, तो इसमें क्या ये बड़ा हो गया इससे, तो सीधे n लग गया, ये तो किया है।
Temp 1 repeat. Problem 45 temp minus 1 repeat. Find the complexity of the pseudocode given below. For I1 to n11 temp plus 1 until n less than own solution. Consider the comments in the pseudocode given below. Temp 1 repeat constant time. This loops executes n times for I1 to n temp plus 1. Recursive call with value until n less than none. The recurrence for this function is t equal to t plus n. Using master theorem we get t equal to O. Problem 46 running time of the following program. Function. 4 system out println. Solution. Consider the comments in the function given below. Public void function.
इसमें क्या हो जाएगा कि ये n टाइम्स रन हो रहा है, फिर इसके अंदर एक और है जो log n टाइम्स रन हो रहा है, j बाई 2 कर रहे हैं ना, j मल्टीप्लाई बाई 2 करके, तो ये n log n सिंपल है।
This loops executes n times for 1.28 algorithms analysis % solutions. For the above function, recurrence function can be given as t equal to t plus 1. This is same as that of problem 41. Using the master theorem he gives, t equal to 0. This loops executes long times from our logarithmus. Guideline for system out println. Complexity of above program is O. Running time of the following program. Problem 47 public void function. Solution public void function int I equal to 1.
यहाँ पर देख सकते हैं ये n बाई 3 टाइम्स रन होगा, ठीक है, और फिर इसके अंदर जो है वो n टाइम्स तक रन होगा, ठीक है, n बाई 3 n टाइम्स, और इसके अंदर भी j प्लस 4 हो रहा है 4 टाइम्स, वो बात बराबर ही है, तो वो n स्क्वायर हो जाएगा ये, n/4 टाइम्स से n/4 टाइम्स होगा, लेकिन वो अप्रोक्सीमेटली इसको n² मान लेंगे।
while in TN, while JJ2, loan code I2I,
तो ये हो गया अपना ये वाला प्रॉब्लम, ठीक है। 48 फाइंड द कॉम्प्लेक्सिटी ऑफ द बिलो फंक्शन एन लेस देन इक्वल रिटर्न कर दो, ग्रेटर देन होगा तो फंक्शन n/2, ये हो गया 2t(n/2) प्लस कोई कांस्टेंट यहाँ पर, ठीक है। तो अब इसमें देखें तो ए और बी दोनों बराबर हो गए, नहीं बराबर नहीं हो गए, ए बड़ा हो गया बी से, क्योंकि वो वहाँ से चलेगा, तो ऐसा सिंपल रहेगा फिर तो एन लोग ए बी होगा, ठीक है। 2 है ऊपर 1 है, नहीं दोनों बराबर है तो 1 हो जाएगा, एन आ जाएगा, एन बिग ऑफ एन आ जाएगा।
long
अरे
times.
यहाँ से
Time complexity O equal to
खुद ही
O.
देख लेते हैं, पूरा एकदम डगमगा जाता है n/2 हाँ आ गया ना, बिग ऑफ एन आ जाएगा। और फिर 49 पे चल रहे हैं, फाइंड द कॉम्प्लेक्सिटी ऑफ द
O. Problem 51, 2 and 3, 2 n plus
51 पे चला गया, हम इसको 49 करते हैं। फाइंड द कॉम्प्लेक्सिटी ऑफ द बिलो फंक्शन, इस पब्लिक वॉइड फंक्शन, इसमें क्या है, इन्होंने स्पेस कोई प्रॉपर फॉर्मेट बुक में उतना फॉलो नहीं किया, ये क्या फॉर्मेट के अकॉर्डिंग पहचान लेता है कि कहाँ पे क्या लिखा है। मैथमेटिकल इक्वेशंस और इतना कुछ आ गया है, तो ये जो वॉइड असिस्टेंट है ना, वो जो उसको बोल रहा है वो थोड़ा सा क्या डगमगा जाता है, क्योंकि समझ नहीं आता कहाँ पर क्या है, ये फॉर्मेटिंग नहीं है ना प्रॉपर, तो कितना मिक्स करके डाल दिया। तो पूछो एक को क्लिक करते हैं, ऊपर वाला भी क्लिक हो जाता है। प्रॉब्लम 48 फाइंड द कॉम्प्लेक्सिटी ऑफ द बिलो फंक्शन, ये जे का आधा हो रहा है और फिर मल्टीप्लाई भी हो रहा है आई, 2i तो ये हो जाएगा log n हो जाएगा ये, जे इक्वल n कर देंगे, जो भी जे इक्वल n है हर बार, जे इज ग्रेटर देन 0, और इसमें भी यहाँ पर भी काम चल रहा है इसका log n का, log स्क्वायर n हो जाएगा ये, तो है ना, log स्क्वायर n हो गया ना। ऐसे ऐसे दिमाग लगाना होगा।
1 to 0 y.
अब 15 प्रॉब्लम और बची है, 65 प्रॉब्लम से।
ये तो और उसमें भी ऐसी रीड कोड में ऐसी आती है
हाँ,
ये
नहीं,
हमारा
नहीं,
होती है।
ये सब निकालने का टाइम कॉम्प्लेक्सिटी, कोई प्रॉब्लम होगी ना उसमें कितना टाइम लगने वाला है, उस ऐसे एक्चुअल टाइम नहीं निकालते, उसको फिर जो कोड लिखा होता है उससे टाइम कॉम्प्लेक्सिटी निकालते हैं, वो उसमें कितने लूप लगे हैं, वो टाइम कॉम्प्लेक्सिटी से ये पता चलता है कि वो ज़्यादा नंबर ऑफ इनपुट्स में कितने नंबर ऑफ इनपुट्स है, वो कितना फास्ट रन करेगी। ज़्यादा नंबर ऑफ इनपुट्स आएंगे ना, तो वो कंपेयर करने के लिए कि ये नंबर ऑफ इनपुट्स के हिसाब से ये ज़्यादा फास्ट चलेगी उसके कंपेयर में, टाइम कॉम्प्लेक्सिटी जैसे एन स्क्वायर, अब बिग ऑफ एन है वो ज़्यादा फास्ट चलेगी बिग ऑफ एन स्क्वायर से, एन क्यूब से, log n वाली फिर एन से भी बहुत फास्ट चलेगी, log n फिर log n उससे भी फास्ट चलेगी, इस तरह से log n फिर वो उसमें वैसे लगाया है, लोग टाइम कॉम्प्लेक्सिटी कैलकुलेट कर रहे हैं ना, कैसे log n आ रहा है, वो उसमें वो जो तरीका निकाला ना, वो लूप वगैरह लगा के वैसे, तो वैसे उससे पता चलता है कि फास्ट कितनी काम कर रही है वो, नंबर ऑफ इनपुट से स्पेस कितना ले रही है, स्पेस कॉम्प्लेक्सिटी भी ऐसे निकाल देंगे। अभी तो फिलहाल टाइम कॉम्प्लेक्सिटी की बात हो रही है,
अगला चैप्टर में स्पेस का है।
नहीं, मेन टाइम कॉम्प्लेक्सिटी की होती है, स्पेस की कोई दिक्कत ही नहीं है, स्पेस तो बहुत ज़्यादा, मतलब इतनी स्पेस होगी ना आजकल, तो वो दूसरा टाइम कॉम्प्लेक्सिटी अगर अच्छी है तो फिर वो स्पेस का वो देख लेते हैं पूरा क्या करना
टाइम फास्ट
है। हाँ, स्पेस का कोई झंझट नहीं है, टाइम की ज़्यादा वैल्यू है। Where O(n) stand for, big of stand for order of n is order of n। अब इसके अंदर देखो ये अच्छा सवाल, इसमें सबमिशन दे दिया है इसका सबका 1 से 1 2 3 4 n तक,
मैं पहले और लेवे
सबमिशन ऑफ ये अरिथमेटिक प्रोग्रेशन का सम आ जाएगा, n स्क्वायर आ जाएगा, n स्क्वायर बिग ऑफ n स्क्वायर, अरिथमेटिक का पूरा सबमिशन है, देखो 1 2 3 4 5 6 7 8 9, इसका फॉर्मूला होता है ना n+1/2, वो लगा दिया है तो n स्क्वायर आ गया। अब वो पढ़ते हैं ना मैथमेटिक्स में, अरिथमेटिक प्रोग्रेशन, ज्योमेट्रिक प्रोग्रेशन, हार्मोनिक प्रोग्रेशन, वो सब यहाँ काम आता है, डेटा स्ट्रक्चर एल्गोरिथम में काम आता है, तो मैथमेटिक्स में पढ़ा जाता है 11 12 और भी दूसरी जो 9 10 में छोटी क्लास में भी पढ़ा जाता है। विच ऑफ द फॉलोइंग 3 themselves. But K and M are constants. इनमें से कौन सा करेक्ट है? 3 claims are correct. इसमें देखना LHS इक्वल टू RHS किसी इसका है, ठीक है, n प्लस k द पावर m थीटा ऑफ n द पावर m, फिर k and m आर कांस्टेंट. सही है, ये बिल्कुल सही है. लेकिन इसमें बात ये हो जाएगी, हाँ सही है, टू द पावर n प्लस 1 बिग ऑफ टू द पावर n, नहीं टू द पावर n प्लस 1 है तो हाँ कह सकते हैं, ये भी सही है. टू द पावर टू n प्लस 1, ये तो गलत. ओनली फर्स्ट एंड सेकंड सही है, फर्स्ट और सेकंड सही है, फर्स्ट ए ऑप्शन सही है. ये इसलिए गलत हो जाएगा क्योंकि टू द पावर 2n तो वो ज़्यादा बड़ा हो गया ना, वो तो 2 स्क्वायर दे दो टू द पावर n से, तो ये बिग ऑफ 2n नहीं कर सकते. बिग ऑफ मतलब अपर लिमिट, अपर बाउंडेड लिमिट होता है. तो टू द पावर 2n प्लस 1 का अपर बाउंड, ये टू द पावर n कैसे होगा? टू द पावर 3n होता है ना, 4n होता तो हो जाता. या टू द पावर 2n भी लिख देते तो हो जाता, जैसे यहाँ पर होगा ना, टू द पावर n प्लस 1 का टू द पावर बिग ऑफ n लिख सकते हैं, क्योंकि वो 3 2n हो सकता है, 4 2n हो सकता है.
2 and 2, 22, n plus 1. Which of the following 3 claims are correct? Oh, where k and m are constants, I and 2, I and...
ये जो नीचे इक्वेशन लिखी है ना, ये इक्वेशन मेरे दिमाग में छप गई थी जब उसको देखा था ना. ये बाइनोमियल कोएफिशिएंट जो पढ़ते हैं मैथमेटिक्स में, उसका यूज हुआ था.
So you claim n plus cln minus 1 plus km and 2n plus 1 2 times 2 o ln. Problem minus 50 o zisks in o, where o stands...
अचानक से यहाँ आ जाता है इसका फॉर्मेटिंग. ठीक है, अब अगला सवाल ये था, कंसीडर द फॉलोइंग फंक्शन fn. अब ये जो प्रॉब्लम्स इतनी अच्छी होती है, इनको डायरेक्ट कॉम्पिटिटिव एग्जाम में भी डाल सकते हैं. ऑप्शंस वाला है ना, ABCD डायरेक्ट डाल सकते हैं. कौन पढ़ता है किताब? जो पढ़ता है उसकी मर्जी. fn इक्वल टू द पावर n gn n फैक्टोरियल hn इक्वल टू n log n. Which of the following statement about the asymptotic behavior of fn gn hn is true? तो इसमें ये होगा कि देखो, इसमें gn जो है वो बड़ा हो जाएगा, n द पावर n होता है, n फैक्टोरियल अप्रोक्सीमेट बिग ऑफ n द पावर n मानेंगे. n log n फिर से छोटा होगा, ठीक है, टू द पावर. लेकिन इसमें क्या हो जाता है कि टू द पावर n जो है ना, ये बस वो देखना पड़ेगा. fn जो है बिग ऑफ gn बोलेंगे, हाँ डेफिनेटली जो fn है वो बिग ऑफ gn होगा. जो जिसमें ऐसा लिखा है ना fn इक्वल टू बिग ऑफ gn, वो सब सही है, जिसमें ऐसा लिखा है वो सही है. फिर gn जो है n द पावर n, वो ये गलत है, ये वाला बिग ऑफ hn गलत है. gn इज इक्वल टू बिग ऑफ fn इज इक्वल टू बिग ओमेगा ऑफ gn n द पावर n, ये गलत है. hn इज इक्वल टू बिग ऑफ n log n है ना, n log n. बिग ऑफ fn और gn इज इक्वल टू n द पावर n इज इक्वल टू डी ऑप्शन करेक्ट है. डी ऑप्शन करेक्ट है. ये थोड़ा सा क्या है, बहुत अच्छा सवाल है, क्योंकि इसमें बहुत सोचना पड़ा. हर एक ऑप्शन ऐसे बनाए हुए थे ना, और इसमें मैं पहले वाला ऑप्शन भी सही हो सकता था. इसमें बस ये क्या कर दिया उन्होंने, ये अगर ऐसे लिखा होता ना hn इज इक्वल टू बिग ऑफ gn, तो पहला ऑप्शन करेक्ट हो जाता. उन्होंने बस पहला स्टेटमेंट करेक्ट था, ये वाला बस गलत हो गया, क्योंकि ये थोड़ा ऐसा होता है. बाकी यहाँ पर देखा जाएगा समझ में आ जाएगा. hn इज इक्वल टू बिग ऑफ, जो hn है n log n, बिग ऑफ fn हो जाएगा, कि टू द पावर n बड़ा होगा ना n log n से. यहाँ n है, यहाँ log n है, तो डेफिनेटली ये बड़ा होगा टू द पावर n, ठीक है. gn जो है वो बिग ऑफ n द पावर n जो है वो बिग ऑफ fn हो जाएगा.
Order is FOG, OGO, HO. According to the rate of growth, HFG asymptotically greater than fin and f is
बता दिया ना
asymptotically
इसमें,
greater.
देखो देखो बता दिया ना, जो एच एन है ना, एच एन जो है वो ये एफ एन बड़ा है एच एन से, और एच एन जी एन, ये लिख लेना होता है एग्जाम में। पहले डायरेक्ट इसको सोल्व करने से पहले है ना, ये से लिख लो जिसने बनाया है, फिर उसमें फिर उसको डाल डाल के देख लो कौन कौन सा बिग ओ ओमेगा की जो ओमेगा और बिग ओ का जो डेफिनेशन है उसके अकॉर्डिंग फिर उसमें डाल के देखो कि वो सेटिस्फाई हो रहा है, जिसमें सेटिस्फाई हो रहा है वो स्टेटमेंट ट्रू हो जाएगी।
With an h, we can easily see the above order by taking logarithms of the given three functions.
ऐसे
Log ln n log. Note that log o. Problem 58 in J1n. Consider the following
लोगरिथम ले लो, लोगरिथम ले लो सबका, उससे भी हो जाएगा। लॉग लॉग एन ये बहुत अच्छा तरीका है सोल्व करने का, ये एन हो जाएगा, लॉग लॉग एन हो जाएगा, ये लॉग एन का फैक्टर है, एन लॉग एन हो जाएगा, तो फिर ये बड़ा हो गया। ये भी जहाँ कन्फ्यूजन लगे वहाँ पर लॉग ले लो, आ जाएगा। अब जैसे ये देखो सी कोड दिया है, देखो सी
segment of C code.
ये जो पूरी किताब है, वैसे तो ये वाली तो जावा के अंदर है, सी कोड भी इसमें दिया है, क्योंकि वो एक ही बात है, सी में करो जावा में करो, क्योंकि वो इनडायरेक्ट से लगभग सेम ही सिंटेक्स फॉलो करते हैं, ऑलमोस्ट सेम है, बस थोड़ा अलग होता है। जावा थोड़ा सा उसमें और चीज़ आ जाती
While JJ2
है। इंट आई जे वन एन जे लेस देन इक्वल टू एन जे तो ये हो जाएगा लोग एन हो जाएगा, लोग एन बेस टू। अब इसमें बताना सील है या फ्लोर है, ये सब बताना पड़ेगा, वो तो पता है लोग एन होगा। तो इसके अंदर ये है ना, हाँ तो ये पूरा चलेगा, फ्लोर चलेगा या सीलिंग वाला चलेगा, +1 चलेगा क्योंकि कांस्टेंट है ना, ये वाला कांस्टेंट है, तो ये चलेगा, पहला ऑप्शन सही हो। सीलिंग इसलिए होगा क्योंकि लेस देन इक्वल टू एन है, ठीक है, तो सीलिंग है लेस देन इक्वल टू एन, फ्लोर नहीं है, वो एग्जैक्ट चलेगा वहाँ तक, n/2 तक चलेगा एग्जैक्ट।
The number of comparisons made in the execution of the loop for any n greater than 0 is seal +1 and seal floor +1. Solution. Let us assume that the loop executes k times. After kt step, the value of j is 2. Taking logarithms on both sides gives k equal to log. Since we are doing one more comparison for exiting from
तो ऐसी दो किताबें हैं, इसके अंदर क्या है कि थ्योरी है और कॉन्सेप्ट है, और जो प्रॉब्लम्स के साथ जो प्रॉब्लम दी है उस प्रॉब्लम का सोल्यूशन है, ठीक है। और एक किताब आती है अपनी इंटरव्यू कंपटीशन, ये जो किताब इसमें क्या है कि क्वेश्चन प्रैक्टिस क्वेश्चन है, इसमें भी होंगे कुछ सवाल होंगे सॉल्व करने के तरीके दिखाए होंगे, इसमें भी क्वेश्चंस के आंसर दिए हैं। ये जो है कोडिंग इंटरव्यू क्वेश्चंस बाय नरसिम्हा करुमांची वाली जो किताब है, प्रोग्रामिंग बेसिक्स, पहले तो बेसिक जो है पूरे इसमें ये बताया है। नहीं, नरसिम्हा करुमांची की जितनी भी किताबें हैं सब में कोई अनसॉल्व प्रॉब्लम्स नहीं है, सबका सोल्यूशन है। वो इसलिए होता है क्योंकि ये सब वो क्या है कि वो ऐसा वो सस्पेंस नहीं छोड़ा जाता है ना, कुछ भी गलत मिसकॉन्सेप्शन नहीं हो, ये कॉन्सेप्ट समझाने की प्रॉब्लम्स होती है, इसलिए ये ऐसा करते हैं कि हर एक प्रॉब्लम का सोल्यूशन दो, क्योंकि फिर कई क्या करते हैं कि उसको गलत तरीके से सोल्व करके कहीं डाल दिया, उसको पढ़ लिया, गलत समझ से समझ लिया, है ना, तो वो किताब
ये तो तूने कर लिया,
ये भी करेगा, ये होने के बाद में इसके बाद में इसमें तो पूरे जो बाकी जो कोडिंग के जो सब्जेक्ट्स है वो भी, मतलब वो बाकी जो सब्जेक्ट्स है ना, ऑपरेटिंग सिस्टम, DBMS,
बड़े इंटरव्यू के लिए होंगे।
जैसे स्क्रिप्टिंग लैंग्वेज, वो पूरा सिलेबस है, वो कंप्यूटर नेटवर्क बेसिक्स जो DTBS का जो सिलेबस है ना, वो है कंप्यूटर नेटवर्क बेसिक्स, स्क्रिप्टिंग लैंग्वेज, मतलब वो वेब डेवलपमेंट वगैरह वो सब, डेटाबेस कॉन्सेप्ट, ये वापस वो रिवीजन करके बिग ओ नोटेशन, ये सब सवालों के साथ, रिकर्शन एंड बैकट्रैकिंग, लिंक लिस्ट, स्टैक्स, कुछ तो यही इसके वापस आ जाएंगे रिवीजन के लिए दोबारा, ये और अच्छी काम आती है,
ये सब का भी सवाल आएंगे।
बिल्कुल ठीक है, ओके, हम कंटिन्यू करते हैं। जैसे ये वाला चैप्टर पढ़ना, इसके अंदर मैं कंपेयर करता हूँ दोनों का कंटेंट कैसा है। इसमें इंट्रोडक्शन वाला जो देखोगे ना, जैसे इसमें देखोगे एल्गोरिथम इंट्रोडक्शन है ना 167, मुझे लग रहा है इसमें सेम ही चिपका दिया है, क्योंकि ये देखोगे ना इन्होंने किताब तो छोटा में क्यों देखना है, इतना बड़े में अवेलेबल है, डायनेमिक प्रोग्रामिंग, इंग्लिश, हाँ सेम है सेम ही चिपका दिया है। मिसलेनियस कौन सा, हाँ सेम ही चिपका दिया मैंने। तभी इसका थोड़ा ज़्यादा हो गया, वो कुछ चैप्टर नंबर वहाँ से चालू होगा पूरा, यहाँ तक है ना, यहाँ तक बस ये कह सकते हैं ये जावा की है। और इसमें जो कोड होगा सी प्लस प्लस में होगा, और ये इसमें जो कोड लिखा होगा ना सी प्लस में होगा, ये सी में लिखा है, सी प्लस में लिखा है, वो सेम कोर्स में देखोगे, हाँ सी प्लस प्लस में सेम प्रॉब्लम है, बस थोड़ी इसमें कम है, प्रॉब्लम्स कम है। इसमें 65 थी, इसमें 57 कर दी, कुछ प्रॉब्लम्स हटा दिए बुक को थोड़ा वैसा रखने के लिए, तो वो सेम प्रॉब्लम है। ये प्रॉब्लम 39 हमने देखी थी, अब देखो प्रॉब्लम 53 देखोगे ना, मिल जाएगी 53 देखो, बुक का अपना अलग मजा है। देखो ये वाली प्रॉब्लम हटा दी है, 53 वाली नहीं है, कुछ प्रॉब्लम उसको थोड़ा और उसके स्पेसिफिक कर दिया, मतलब जो इंटरव्यू में तैयारी करेंगे कोडिंग इंटरव्यू से ना, तो उसको कितना टाइम होता है उसके हिसाब से थोड़ा कम किया कोड, तो ऐसा कर सकते हैं। ठीक है, ओके फाइन।
The answer is CO+1. Problem 54. Consider.
हाँ, मुझे क्या लग रहा है, ये जो बीच में ऑप्शन वाली है ना, जो बीच में ऑप्शंस वाली है वो हटा दी। जैसे यहाँ पर आप देखो प्रॉब्लम नंबर 59, प्रॉब्लम नंबर 49 देखो, प्रॉब्लम नंबर 49 सेम है, ये वाली जो प्रॉब्लम है ये वाली प्रॉब्लम सेम है। देखो फाइंड द कॉम्प्लेक्सिटी ऑफ द बिलो फंक्शन int i इक्वल, ये लिखा है ना पब्लिक वॉइड, ये जावा में लिखा है, कोड अलग है लेकिन वो मतलब सेम ही है। क्या डिफरेंस है, बस पब्लिक वॉइड लिखने का डिफरेंस है, बाकी सेम है, फंक्शन इंटेंट, बस ये फर्क होता है जावा और सी प्लस। पब्लिक वॉइड लिखा जाता है,
कंपनी एक ही ना।
हाँ, और फिर ये देखो j इक्वल टू 2 मल्टीप्लाई आई, और वही सेम, वो अभी ये हो गया। अब आगे जो 50 है ना, वो जो ये MCQ वालों के आगे है, देखो MCQ वाली 50, 51 ये सब MCQ वाली प्रॉब्लम से, 54 भी MCQ वाली है, 55 भी MCQ वाली है, 56 MCQ है।
एक में कर ले तो
हाँ।
एक में पूछ।
नहीं, MCQ वाली अपने को करनी ज़्यादा जरूरी, ये किताब ज़्यादा सही है क्योंकि MCQ कंपटीशन में बहुत आती है, तो मतलब ये डिटेल्स हो गया। 57 जो है ना, 57 वो इसमें दी हुई है, ये रही 4 फंक्शन 4 जो ही रहा, कितना मस्त। अब छोटा देखने की जरूरत नहीं है।
सी प्रोग्राम में देखेगा जावा का।
हाँ, जावा सी प्लस प्लस दोनों एकदम मास्टर है, दोनों बहुत सिमिलर लैंग्वेज है। और पाइथन तो और आसान, वो तो उसमें तो कोड लिखना बहुत आसान है। तो बुक का अपना अलग मजा है। तो ये 15 घंटे का पूरा किताब है, जिसमें से हमारा 1 घंटा 11 मिनट का हिसाब हो गया है उसमें लिखना ऑडियो में।
कौन देना किसका है?
Following C code segment. Let T denote the number of times the for loop is executed by the program on it.
Okay, starting from here, question number 54. I think.
Problem 54. Consider the following C code segment. Let T denote the number of times for loop is executed by the program on input n. Which of the following is true? Public int is prime return 1, TONT, TONT, TONT2, none of the above. Solution.
Okay. Let me check it. I was. $54. Public int I equal to 2 and square root of n I plus plus modulo. Okay, not prime. It's root n, no? Into square root n. Root n, big of root n, and omega of what? No? B option.
Big O notation describes the tight upper bound and big omega notation describes the tight lower bound for an algorithm. The for loop in the question is run maximum 7 times and minimum 1 time. Therefore, TO and TQ2. Problem 55 in the following C function. Let n greater than or equal to m.
Okay, in the following C function that n is greater than or equal to m. N is greater than or equal to m. How many recursive calls are made by this function? Public int GSD n m. N is n modulo m is equal to 0, then return m. Otherwise n modulo m, return GSD mn. Return m. N modulo m, return GSD mn. Log how many recursive calls? N modulo m. Return. Calling only one time. Then returning no. Return m. GST mn. Mn. Then m is going, n is going. Then again m modulo n. No option is correct. Okay.
How many recursive calls are made by this function? Public int get o omega eo. Solution, no option is correct. Big O notation describes the tight upper bound, and big omega notation describes the tight lower bound for an algorithm. For m equal to 2, and for all n equal to 2, the running time is O, which contradicts every option. Problem 50t equal to O equal to 2 trillion.
Okay. If m is equal to 2, for all n is equal to 2i, then this big of n, 1, which is contradicting every option. Okay. You understood what is saying? Big O notation is the tight upper bound, and big omega notation is the tight lower bound for algorithm. But m and n are not fixed here. You can see. Suppose we take m is equal to 2 and n is equal to 2i. The running time is big O of 1. It will be break here. It will return from here. Okay. So this contradicts every option. Every other option.
Plus n tt minus 1. Which one of the following is false? T equal to OT equal to OT.
Suppose Tn is equal to 2t n by 2 plus n t0 t1. Which one of the following is false? False, okay. Both are equal. Okay. This will become n. Both are equal n log n. This is correct. Big of n square is correct. And big of n log n is also correct. This is incorrect. C option.
Equal to 2. Solution. Big O notation describes the tight upper bound, and big omega notation describes the tight lower bound for an algorithm. Based on master theorem.
हाँ कह दीजिए तो एट करा लीजिए 5 है खाना का बहुत कुछ करता हूँ एट मान चुका दो ओ ए 500 तो और ले लीजिए एट का चढ़ा 500 और 500 तो ये ले लीजिए ये 5000 के खाता ओ करने रख के वो नीचे रख पिन कार्ड कोड है ओ ऊपर रख शाम का 8 घंटे नजदीक हो जाएगा टिक रहा है जी हैं बजाओ जरा देख लीजिए फोन लेट जाते ये ओ थेलो ले जाना है
ठीक है ओके
तो थोड़ा थेलो है
We get t equal to O. This indicates that tight lower bound and tight upper bound are the same. That means O and Q are correct for given recurrence. So option is wrong. Problem 57%, find the complexity of the below function. Public function print EF. 1.28 algorithms.
Here you can see the function public void int n. Options are okay. I'm going to find it. Function int n. I is equal to I less than n. I plus plus I square. Okay. It is root. This is run n times. And next loop will run. This next loop will run root n times, but it depends on I also. It depends on I also. Returns root I square. Okay. So j is modulo I then equal to 0 for int, and it again run if you modulo by k less than j. N times j I plus I square times. Now executes. Now this executes again n plus n times j times. So it becomes n square n the power 4, and then again n the power 5. So the big of n the power 5.
Analysis, problems, and solutions. Problem 59 for problem 58. Can we improve the time complexity? Solution. Refer to the divide and conquer chapter.
To get that 9 the power n, give algorithm and discuss its complexity. Start with 1. Multiply by 9 until reaching 9 the power n. Time to complexity, there are n minus 1 multiplication, and each takes constant time, giving a big of n algorithm. Big of n, theta of n algorithm. Start with 1, multiply n until reaching 9 the power n. There are n minus 1 multiplications, and each takes constant times, giving a theta of n algorithm. For problem 58, can we improve the time complexity? Refer the divide and conquer chapter. Okay. Can we improve the time complexity? We can improve it. Divide and conquer. Divide it and then conquer. Find the complexity of below function. The public void function int n, sum equal to 0 for int I equal to 0, I less than n, I plus plus 2. If I is greater than j, sum plus 1. Okay.
Problem 60. Find the complexity of the below function, public void function, in sum 0 for if sum plus 1.
Okay, greater than j, but where is j declared? Okay. Sum 0. Let j be declared. Okay. I is greater than j, sum plus 1, else. Okay. It depends on k. It will run n times. Okay. It will run n times. Instead of okay, it will run n times. And execute n times. This will also execute n times. Execute n times. If this will execute n times. This will execute n times.
As for sum minus 1 solution, consider the
Big
worst
of
case. Problem C1. Solve the following recurrence relation using the recursion tree method, t equal to t plus n. 2. Solution. How much work do we do in each level of the recursion tree?
This execute n times. This will not execute n times. It will just check, and this will execute one time only. But it depends. It will execute n times. Okay. So the following recursion using the recursion tree. Tn by 4 to t2n by 3 plus n square. Tn by 2, tn by 4, tn by 8 plus n. This is different problem, and this is like another different. So nothing here. And tn by 2 to tn by plus n square. Recursive tree method.
Solution. Public void function for if executes n times, executes n time. Problem 61. Solve the following recurrence relation using the recursion tree method, t equal to t plus n. 2. Solution. How much work do we do in each level of the recursion tree? Solution. Public void function for if executes n times, executes n times 4, executes j In level 0, take n2 time.
Level 0 take n square time. At the level 1, the 2 sub-problem takes time. Level 0 takes n square time. This level 0. N square. This over take time. 2n by 3 whole square. Okay. N by 2 the whole square. 2n by 3 the whole square. Okay. Plus n square. 225 by 36 n square.
Level 1, the 2 subproblems take time. 1.28 algorithms analysis, problems and solutions. K. Level 2. The 4 subproblems are of size 1, n2, and 12n, 32 feet 2 inches, 3, and respectively. These 2 subproblems take time. Similarly, the amount of work at level K is at most 2. Let A equal to the total runtime is then. That is, the first level provides a constant fraction of the total runtime. Problem
Okay. Here it from here to here. Okay. 1 minus alpha n square. 1 upon 1 minus 25 by 36 n square. 36 by 11 n square.
62. Find the time complexity of recurrent. T, TA, plus T, plus A, plus N. Solution: let us solve this problem by method of guessing. The total size on each level of the recurrence tree is less than n, so we guess that f equal to n will dominate. Assume for all in that Cn TSC 2n. Then 1848 Cn less than or equal tot less than or equal to n.
You can see as C1 n by 2, C1 n by 4, and C1 n by 8 plus Kn. C2 okay, fine. Okay. 7 by 8. So C1 is equal to 8k, greater than 8k. C2 is less than 8k. So this is k. Huh? We go off Fn. Loss. This cause is less than n. Okay, fine.
If C greater than or equal to 8k and C 2 less than or equal to 8k, then C 1 end, TC 2n. So, t minus 8. In general, if you have multiple recursive calls, the sum of the arguments to those calls is less than n, and f is reasonably large. A good guess is tin, e, 24, 8. Problem minus 68. Rank the following functions by order of growth. N, 4, nx3, 3, plus n2 plus 20n, 4n2, 41gn, n, 2 plus 200, 20n, 2 plus 20n. Solution. Solution equal to O.
So here we can see the n plus 1 factorial is out of n factorial is greater than, then n factorial is greater than 4 to the power n, then n 3 to the power n, then 3 to the power n plus n square plus 20n. This was really confusing, but it was there. n 3n, 3 by 2 to the power n, 4n square, 4 log n, 4 log n, rate of growth order of n square. So 2 here, n square, okay, n square is 220 and this is n divided 2 by 3 or this one. Can we say yes because
Solution, yeah, says 37% less than 3% to the power of 1. Problem 65. Can we say 23% to the O? Solution, no, because 23 equal to 8, not less than. Recursive backtracking. Chapter 2.1 Introduction. In this chapter, we will look at one of the important topics, recursion, which will be used in almost every chapter, and also its relative backtracking. 2.2. What is recursion? Any function which calls itself is called recursive. A recursive method solves a problem by calling a copy of itself to work on a smaller problem. This is called the recursion step. The recursion step can result in many more such recursive calls. It is important to ensure that the recursion terminates each time the function calls itself with a slightly simpler version of the original problem. The sequence of smaller problems must eventually converge on the base case. 2.3. Why recursion? Recursion is a useful technique borrowed from mathematics. Recursive code is generally shorter and easier to write than iterative code. Generally, loops are turned into recursive functions when they are compiled or interpreted. Recursion is most useful for tasks that can be defined in terms of similar subtasks. For example, sort, search, and traversal problems often have simple recursive solutions. 2.4 Format of a recursive function. A recursive function performs a task in part by calling itself to perform the subtasks. At some point, the function encounters a subtask that it can perform without calling itself. This case, where the function does not recur, is called the base case. The former, where the function calls itself to perform a subtask, is referred to as the recursive case. We can write all recursive functions using the format. If return some base case value else, if return some other base case value, the recursive case else return. As an example, consider the factorial function n is the product of all integers between n and 1. The definition of recursive factorial looks like, this definition can easily be converted to recursive implementation.
here you can see the n factorial is equal to 1. If n equals 0, then n factorial is equal to n multiply n minus 1 factorial. Then n is greater than 0. Okay, you can see it. So this definition can be really converted into recursive implementation.
Here the problem is determining the value of n, and the subproblem is determining the value of. In the recursive case, when n is greater than 1, the function calls itself to determine the value of, and multiplies that with n. In the base case, when n is 0 or 1, the function simply returns 1. This looks like the following. Class factorial, recursive definition of method factorial public long factorial, if, test for base case.
Okay, you can see here.
Return 1, base cases 0, 1, and 1. 1 else recursion step return for factorial. Public static void main factorial obj, new factorial for system
Okay,
out
you can
print.
see here.
Class factorial, recursive definition of method factorial public long factorial, if, test for base case return 1, base cases 0, 1, and 1. 1 else recursion step return number factorial. Public static void main factorial obj, new factorial for system out tf. 2.5 recursion and memory. Each recursive call makes a new copy of that method in memory. Once a method ends, the copy of that returning method is removed from memory. The recursive solutions look simple, but visualization and tracing takes time. For better understanding, let us consider the following example. Public int print if this is the terminating base case return 0, else system out print ln return print recursive call to itself again.
Okay.
For this example, if we call the print function with n-4, visually our memory assignments may look like. Now, let us consider our factorial function. The visualization of factorial function with n-4 will look like 2.6 recursion versus iteration. While discussing recursion, the basic question that comes to mind is, which way is better, iteration or recursion? The answer to this question depends on what we are trying to do. A recursive approach mirrors the problem that we are trying to solve. A recursive approach makes it simpler to solve a problem that may not have the most obvious of answers. But recursion adds overhead for each recursive call. Recursion terminates when a base case is reached. Each recursive call requires extra space on the stack frame. If we get infinite recursion, the program may run out of memory and result in stack overflow. Solutions to some problems are easier to formulate recursively. Iteration terminates when a condition is proven to be false. Each iteration does not require any extra space. An infinite loop could loop forever since there is no extra memory being created. Iterative solutions to a problem may not always be as obvious as a recursive solution.
Terminates when the condition is proven to be false. Each iteration does not require any extra space. Terminates when the condition is proven to be false. Each iteration does not require any extra space. Terminates when the condition is proven to be false. And each iteration does not require any extra space. An infinite loop will loop forever since there is no extra memory being captured. स्टिक ओवरफ्लो होगा रिकर्शन में, इसमें नहीं होगा, इटरेशन में नहीं होगा.
2.5 Recursion and Memory. 2.6 Notes on Recursion. Recursive algorithms have two types of cases, recursive cases and base cases. Every recursive function case must terminate at base case. Generally, iterative solutions are more efficient than recursive solutions. A recursive algorithm can be implemented without recursive function calls using a stack, but it's usually more trouble than it's worth. That means any problem that can be solved recursively can also be solved iteratively. For some problems, there are no obvious iterative algorithms. Some problems are best suited for recursive solutions, while others are not. 2.8 Example algorithms of recursion. Fibonacci series factorial finding. Merge sort, quick sort, binary search. Tree traversals and many tree problems in order, pre-order, post-order. Graph traversals, DFS and BFS. Dynamic programming examples. Divide and conquer algorithms. Towers of Hanoi. Backtracking algorithms. 2.9 Recursion, problems and solutions. In this chapter, we cover a few problems with recursion, and we will discuss the rest in other chapters. By the time you complete reading the entire book, you will encounter many recursion problems.
Yeah.
Problem 1, discuss Towers of Hanoi puzzle. Ratten. Solution, Towers of Hanoi is a mathematical puzzle. It consists of 3 rods and a number of disks of different sizes, which can slide onto any rod. The puzzle starts with the disks on one rod in ascending order of size, the smallest at the top, thus making a conical shape. The objective of the puzzle is to move the entire stack to another rod, satisfying the following rules. Only one disk may be moved at a time. Each move consists of taking the upper disk from one of the rods and sliding it onto another rod, on top of the other disks that may already be present on that rod. No disk may be placed on top of a smaller disk. Algorithm. Move the top N1 disks from source to auxiliary tower. Move the nth disk from source to destination tower. Move the N1 disks from auxiliary tower to destination tower. Transferring the top N1 disks from source to auxiliary tower can again be thought of as a fresh problem and can be solved in the same manner. Once we solve Towers of Hanoi with 3 disks, we can solve it with any number of disks with the above algorithm. Public void Towers of Hanoi. If only a disk, make them move and return. If system out println. Move top n-1 disks from A to B, using C as auxiliary. Towers of Hanoi. Move remaining disks from A to C. System out top println. Move n-1 disks from B to C, using A as auxiliary. Towers of Hanoi. Problem 2, given an array,
Okay, that's
check
very
what...
cool problem. From peg to peg. Okay. Move n-1 disks from A to B using C auxiliary. From pack to pack. Using C of from pack. From pack. Okay. Move to define the one. M-1 A to B. You see auxiliary. Move the unit is A to C. And then okay, and we will do
The array is in sorted order with recursion. Public int array in sorted order A, int index.
okay, fine. Given array, check whether the array is sorted order with recursion. Public is array in sorted. Public int is array in sorted. Int index.
A one or index.
8 or length is 1. Index is equal to 1. Return 1. Zero. Okay, fine.
1, return 1, return alindex minus 2 as array in sorted order. Time complexity, O. Space complexity, O for recursive stack space. 2.10, what is backtracking? Backtracking is an improvement of the brute force approach. It systematically searches for a solution to a problem among all available options. In backtracking, we start with one possible option out of many available options and try to solve the problem. If we are able to solve the problem with the selected move, then we will print the solution, else we will backtrack and select some other option and try to solve it. If none of the options work out, we will claim that there is no solution for the problem. Backtracking is a form of recursion. The usual scenario is that you are faced with a number of options and you must choose one of these. After you make your choice, you will get a new set of options. Just what set of options you get depends on what choice you made. This procedure is repeated over and over until you reach a final state.
Yeah.
If you made a good sequence of choices, your final state is a good state. If you didn't, it isn't. Backtracking can be thought of as a selective tree graph traversal method. The tree is a way of representing some initial starting position and a final goal state. Backtracking allows us to deal with situations in which a raw brute force approach would explode into an impossible number of options to consider. Backtracking is a sort of refined brute force. At each node, we eliminate choices that are obviously not possible and proceed to recursively check only those that have potential. What's interesting about backtracking is that we back up only as far as needed to reach a previous decision point with an as-yet unexplored alternative. In general, that will be at the most recent decision point. Eventually, more and more of these decision points will have been fully explored, and we will have to backtrack further and further. If we backtrack all the way to our initial state and have explored all alternatives from there, we can conclude the particular problem is unsolvable. In such a case, we will have done all the work of the exhaustive recursion and known that there is no viable solution possible. Sometimes, the best algorithm for a problem is to try all possibilities. This is always slow, but there are standard tools that can be used to help. Tools, algorithms for generating basic objects, such as binary strings, permutations, combinations, general strings, etc. Backtracking speeds the exhaustive search by pruning. 2.11 example algorithms of backtracking. Binary strings generating all binary strings. Generating k-ary strings, the knapsack problem, n-queens problem, generalized strings, Hamiltonian cycles. Coloring problem. 2.12 backtracking problems and solutions. Generate all the strings of n bits. Assume A is an array of size n. Problem 8 solution. Import java.util. public binary strings else, A, 0 binary, ALN 1-1 binary. Public static void
Oh,
main
wait, let me see.
args throws
Let me see the
java.lang.exception
program number
into
5 again. 1 second. What is asked? Generate all strings of n bits. Assume a0 minus 1 in an array of size n. Import java.util utility.store. You have to do it. Public class binary string. Okay. Now write int. You have to declare array a. Okay. Public binary string int n. A new int n. Now public void binary int n. If n is less than equal to 0, then print the string here. Okay. Else an minus 1 equal to 0. Binary n minus 1. Okay, call it again. Call this function again. Binary n minus 1 is a n minus 1 last string of n bits. Print again. Is a n minus 1 0. Last string of n is less than print. Using array a is global. Okay. System array to string. Okay. Okay, it's declared already. New int. Binary string will be taken from another way. From here taken. 4 plus binary n minus n equal to 4. N equal to 4. Binary string I. New 92nd here. I binary n. Int n equal to 4. New binary n. This is 4. Go on here. N minus n equal to 0. Binary n minus 4. Okay. ले जाएंगे टक जनरेट हो गया
n minus 4 binary strings I new binary strings I dot binary. Let t be the roaming time of binary. Assume function system out println takes time o. t equal to 2c if n less than 0 plus d. Otherwise, subtraction and conquer master theorem, we get t equal to 0. This means the algorithm for generating bit strings is optimal. Using problem 4, get all the strings of length n drawn from 0. K1. Solution. Let us assume we keep current k-array string in an array A. Call function kstring. Import java.util. Class carry strings, int a, public binary strings, a, new int e, public void basic strings. Process all k-array strings of length m if system out println, else for aj basic strings. Assume
public bin barrel string. Class k array string. Okay, public barrel string new int. And public key string
array A is a class variable 1 public static void main args throws java.lang.exception intent for carry strings obj, new carry strings obj.basic strings. Let t the running time of k string. Then, if n less than 0 trillions equal to plus d otherwise. Problem 5. Using
here you can see k tn minus 1. Yeah, fine. Goes to tn minus 1. Binary. Tn minus 1.
subtraction and conquer master theorem, we get t equal to O. Note, for more problems, refer to String Algorithms chapter. Solve the recurrence t minus 2 plus 2. Solution, at each level of the recurrence tree, the number of problems is double from the previous level, while the amount of work being done in each problem is half from the previous level. Formally, the ITH level has 2 problems, each requiring 2 work. Thus, the each level requires exactly work. The depth of this tree is n, because at the h level, the originating call will be Tony. Thus, the total complexity for t is t. Linked lists. Chapter 3.1. What is a linked list?
So it's ended now. You can see this chapter is ended now. 40 is ended now. So the recursion Tn, you can see at each level of recursion tree, the number of column is double from the previous level, and the amount of work being done is each column is half from the previous level. For only the ith level, as 2 the power I is requiring 2n minus I work, thus the I level requires 2n the to the power n work. Okay, the depth is n. To the power n is n to the power n. To the power n to the power n. कहाँ से लगाया? तो उससे वो कर दिया. Okay, fine. It's ended now. Chapter number 2 is ended. English I will continue tomorrow, but before continuing, I want to do something. I will read the book number 1, that main book. I'm going to read that. File, class file. We're going to download. Must review for developer. Yeah, going to open this. We are going to start. Okay, I am this.
Problem 4. Generate all the strings in length.
1 minute, please.
N drawn from 0. K1. Solution. Let us assume we keep current K array string in an array A. Call function K string. Let T be the running time of a string. Then
You can see your void K string in 10 in K. If n is greater than 1, print just the function. Else for int j equal to K, j less than K, I j plus plus a minus 1 j. Okay, K string n minus 1 K. Again go there. Go till you. Okay, fine. Generate it 2 times. N minus 1 K. K array string in an array. Okay, fine. N minus 1 K.
Using subtraction and conquer master theorem, we get T.
Tn minus 1. Okay. Okay. Tn minus 1. Tn minus 1. Okay. This will run k times, okay? This is some constant. This is run k times of Tn minus 1 d. Subtraction we can see k the power n.
E equal to O. Note, for more problems, refer to string algorithm chapter. Problem 5, finding the length of connected cells of 1 second in a matrix of OS and 1 second given a matrix, each of which may be 1 or...
Okay, this is great.
or 0. The filled cells that are connected form a region. Two cells are said to be connected if they are adjacent to each other horizontally, vertically, or diagonally. There may be several regions in the matrix. How do you find the largest region in the matrix? Solution. The simplest idea is for each location traverse in all 8 directions, and in each of those directions keep track of maximum region found. Int get val, int I, int j, int l, int h. For int nui r plus direction, int nu jc.
Fine. 1, 2, 3, 4, 5, 6, 7, 8. And this bit also is done. Okay, fine. If I doesn't do it, I will do J doesn't do it, okay, fine. I'll say done. EIJ.
Six, solve the recurrence t equal to 2 trillions plus 2n. Solution. At each level of the recurrence tree, the number of problems is double from the previous level.
Okay, now I'm going to start chapter number 3, linked list of Narasimha Karumanchi's book, Data Structure and Algorithm, made easy. Okay, going to start it now.
What is a linked list? A linked list is a data structure used for storing collections of data. A linked list has the following properties. Successive elements are connected by pointers. The last element points to null, can grow or shrink in size during execution of a program, can be made just as long as required, does not waste memory space, it allocates memory as list grows. 3.2.
So you understood? Linked list is a data structure used for storing collection of data. It can successive elements are connected by pointers. The last element points to null and can grow or shrink in size during execution of a program. Okay, and can be made just as long as required until system memory exhausts. Okay, does not waste memory but takes some extra memory for pointers. It allocates memory as list go. Okay, but takes some extra memory for pointers. It allocates memory as list grow. So linked list ADT, you can see it. Okay. Let me show you. This is first. This is head. Okay. As you can see this. Okay, this is head, and this is another pointer to it, the another linked list, and this is the data, and this is another pointer, and this is pointing here, and this is again pointing to this, and last is pointing to null. Okay, we're going to start it now.
The following operations make linked lists in ADT. Main linked lists operations. Insert inserts an element into the list. Delete removes and returns the specified position element from the list. Auxiliary linked list operations. Delete list removes all elements of the list. Count returns the number of elements in the list. Find nth node from the end of the list. 3.3. Why linked lists? There are many other data structures that do the same thing as linked lists. Before discussing linked lists, it is important to understand the difference between linked lists and arrays. Both linked lists and arrays are used to store collections of data, and since both are used for the same purpose, we need to differentiate their usage. That means in which cases arrays are suitable and in which cases linked lists are suitable.
Yeah, this is nice thing.
3.4 Arrays Overview. One memory block is allocated for the entire array to hold the elements of the array. The array elements can be accessed in constant time by using the index of the particular element as the subscript. Why constant time for accessing array elements? To access an array element, the address of an element is computed as an offset from the base address of the array, and one multiplication is needed to compute what is supposed to be added to the base address to get the memory address of the element. First, the size of an element of that data type is calculated, and then it is multiplied with the index of the element to get the value to be added to the base address. This process takes one multiplication and one addition. Since these two operations take constant time, we can say the array access can be performed in constant time.
So you can see this is very important, that why it's take constant time. This is the most important question. Why constant time for accessing array elements? Because to access an array element, the address of element is composed of an offset from the base address of the array, and one multiplication is needed to compute what is supposed to array to the base address to get the memory address of the element. The size of the element of the data type is calculated. First you will calculate the data type size, and then it is multiplied with index of the element. Okay, to get the value to be added to the base address. So this process takes one multiplication and one addition. One multiplication and one addition it takes. Since these two operations take constant time, so we can say that the array access can be performed in constant time. Okay. Now advantages of array.
Of arrays, simple and easy to use. Faster access to the elements. Disadvantages of arrays. Pre-allocates all needed memory up front and wastes memory space for indices in the array that are empty. Fixed size, the size of the array is static. One block allocation to allocate the array itself at the beginning. Sometimes it may not be possible to get the memory for the complete array. Complex position-based insertion. To insert an element at a given position, we may need to shift the existing elements. This will create a position for us to insert the new element at the desired position. If the position at which we want to add an element is at the beginning, then the shifting operation is more expensive. Dynamic arrays. Dynamic array is a random access, variable size list data structure that allows elements to be added or removed. One simple way of implementing dynamic arrays is to initially start with some fixed size array. As soon as that array becomes full, create the new array double the size of the original array. Similarly, reduce the array size to half if the elements in the array are less than half. Note, we will see the implementation for dynamic arrays in the stacks, queues, and hashing chapters. Advantages of linked lists. Linked lists have both advantages and disadvantages. The advantage of linked lists is that they can be expanded in constant time. To create an array, we must allocate memory for a certain number of elements. To add more elements to the array when full, we must create a new array and copy the old array into the new array. This can take a lot of time. We can prevent this by allocating lots of space initially, but then we might allocate more than we need and waste memory.
Yeah.
With a linked list, we can start with space for just one allocated element and add on new elements easily without the need to do any copying and reallocating. Issues with linked lists. There are a number of issues with linked lists. The main disadvantage of linked lists is access time to individual elements. Array is random access, which means it takes O to access any element in the array. Linked lists take O for access to an element in the list in the worst case. Another advantage of arrays in access time is spatial locality in memory. Arrays are defined as contiguous blocks of memory, and so any array element will be physically near its neighbors. This greatly benefits from modern CPU caching methods. Although the dynamic allocation of storage is a great advantage, the overhead with storing and retrieving data can make a big difference. Sometimes linked lists are hard to manipulate. If the last item is deleted, the last but one must then have its pointer changed to hold a null reference. This requires that the list is traversed to find the last but one link, and its pointer set to a null reference. Finally, linked lists waste memory in terms of extra reference points. 3.5 Comparison of linked lists with arrays and dynamic arrays. 3.6 Singly linked lists. Generally, linked list means a
So you can see here the parameters. You can see the linked list. You can see array and dynamic array. You can see.
Generally, linked list means a singly linked list. This list consists of a number of nodes in which each node has a next pointer to the This list consists of a number of nodes in which each node has a next pointer to the following element. The link of the last node in the list is null, which indicates the end of the list. Head. Following is a type declaration for a linked list of integers. Struct list node. Int data. Struct list node next. Basic operations on a list. Traversing the list. Inserting an item in the list. Deleting an item from the list. Traversing the linked list. Let us assume that the head points to the first node of the list. To traverse the list, we do the following. Follow the pointers. Display the contents of the nodes as they are traversed. Stop when the next pointer points to null. The list length function takes a linked list as input and counts the number of nodes in the list. The function given below can be used for printing the list data with extra print function.
Here you can see the list and structure list node and is pointing to head, and the struct list node current is pointing head and count 0, and while the current node equal to null, count plus plus and count next and return next.
Time complexity O for scanning the list of size n.
This is very important.
Space complexity O for creating a temporary variable. Singly linked list insertion. Insertion into a singly linked list has 3 cases: inserting a new node before the head, inserting a new node after the tail, inserting a new node at the middle of the list. Note, to insert an element in the linked list at some position P, assume that after inserting the element, the position of this new node is P.
To insert an element in the linked list with the same position P, assume that after inserting the element, the position of this new node is P.
Inserting a node in singly linked list at the beginning. In this case, a new node is inserted before the current head node. Only one next pointer needs to be modified, and it can be done in 2 steps. Update the next pointer of new node to point to the current head. In this case, we need to modify 2 next pointers. Update head pointer to point to the new node. Inserting a node in singly linked list at the ending. New node's next pointer points to null.
क्या कर रहा है? होने से वहीं
पढ़ाई करा
पढ़ाई कर रहा है तो बैठ के कर लेट के कर रहा है पूरे दिन ही थोड़ा थक जाता होगा बैठे बैठे तूने क्या किया क्या
Inserting a node in singly linked list at the middle. Let us assume
बस
that we are given a position where we want to insert the new node. In this case, also, we need to modify 2 next pointers. If we want to add an element at position 3, then we stop at position 2. That means we traverse 2 nodes and insert the new node. For simplicity, let us assume that the second node is called position node. The new node points to the next node of the position where we want to add this node. Let us write the code for all 3 cases. We must update the first element pointer in the calling function, not just in the called function. For this reason, we need to send a double pointer. The following code inserts a node in the singly linked list. Note, we can implement the 3 variations.
get a code. इसके अंदर क्या किया है?
एक बार रख दे थे
अब insert linked list, data, position, and head is there. Okay. K is 1. There are 2 pointers and 1 pointer to new node. Up 1 pointer of new node. Then what is given size of structure of listener. Okay. This is in previous. Okay, fine. Any node data is given, and okay, fine. Key is the head. If position equal to 1, insert in the beginning. Okay. Head को new node दे दिया. A plus 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 and QP and P next.
Of the insert operation separately. Time complexity O, since in the worst case we may need to insert the node at the end of the list. Space complexity O for creating one temporary variable. Singly linked list deletion. Similar to insertion, here we also have three cases. Deleting the first node, deleting the last node, deleting an intermediate node, deleting the first node in singly linked list. First node is removed from the list. It can be done in 2 steps. Create a temporary node which will point to the same node as that of head. Now, move the head nodes pointer to the next node and dispose of the temporary node, deleting the last node in singly linked list. In this case, the last node is removed from the list. This operation is a bit trickier than removing the first node because the algorithm should find a node which is previous to the tail. It can be done in 3 steps. Traverse the list and while traversing maintain the previous node address also. By the time we reach the end of the list, we will have 2 pointers, one pointing to the tail node and the other pointing to the node before the tail node. Deleting an intermediate node in singly linked list. In this case, the node to be removed is always located between 2 nodes.
तो ये हटाना है सपोज, तो इसमें क्या करना है, इसको हटाना है नोट प्रीवियस टू टेल्स, प्रीवियस करना पड़ेगा, अपडेट प्रीवियस नोट नेक्स्ट पॉइंट विद नो, ये हट गया, डिस्पोज कर दो. फिर इंटरमीडिएट लास्ट नोट को लास्ट लिंक इसको हटाने की, इंटरमीडिएट नोट को हटाना हो तो node is removed. Node is located between 2 nodes. Head and links are not updated in this case. Such a removal can be done in 2 steps.
Head and tail links are not updated in this case. Such a removal can be done in 2 steps. Similar to the previous case, maintain the previous node while traversing the list. Once we find the node to be deleted, change the previous node's next pointer to the next pointer of the node to be deleted. Void delete node from linked list if print f else q next.
इसको कोड देखें कैसे रिमूव करना है. डेट नोट फ्रॉम द लिंक लिस्ट, स्ट्रक्चर लेना पड़ेगा लिस्ट नोट का हेड, डबल पॉइंट इन पोजीशन. ओके ओके
vulnerability, vulnerable बोलो, vulnerable, vulnerability, vulnerability.
sorry. CP.
मिर्चा लागी
types of hacker right head left head right head से so improve करते हैं left head वाला
You know to go down and get that position.
और right head होते हैं जो दोनों अलग
K++ QP and PPV next. P not equal to null. And K less than position.
Blend of what?
K plus plus and Q equal to P units. Equal to null and K less than position.
Wireless network database
सही है
Next P, next free, at the end, from the middle. Time complexity, O. In the worst case, we may need to delete the node at the end of the list. Space complexity, O for one temporary variable. Deleting singly linked list. This works by storing the current node in some temporary variable and freeing the current node. After freeing the current node, go to the next node with a temporary variable and repeat this process for all nodes.
So you can see it here.
Void delete linked list, struct list node auxiliary node, iterator equal to head, while auxiliary node iterator, next, free, iterator equal to auxiliary node, head equal to null, to affect the real head back in the car.
So here you can see during single releases.
Time complexity O for scanning the complete list of size n. Space complexity O for creating one temporary variable. 3.7 doubly linked lists. The advantage of a doubly linked list is that given a node in the list, we can navigate in both directions. A node in a singly linked list cannot be removed unless we have the pointer to its predecessor. But in a doubly linked list, we can delete a node even if we don't have the previous node's address. The primary disadvantages of doubly linked lists are each node requires an X pointer, requiring more space. The insertion or deletion of a node takes a bit longer. Similar to a singly linked list, let us implement the operations of a doubly linked list. If you understand the singly linked list operations, then doubly linked list operations are obvious. Following is a type declaration for a doubly linked list of integers. Struct DLL node, int data, struct DLO node next, struct DL node prev, doubly linked list insertion. Insertion into a doubly linked list has three cases. Inserting a new node before the head, inserting a new node after the tail, inserting a new node at the middle of the list. Inserting a node in doubly linked list at the beginning. In this case, node is inserted before the head node. Previous and next pointers need to be modified, and it can be done in 2 steps. Update the right pointer of the new node to point to the current head node and also make left pointer of new node as null. Update head node's left pointer to point to the new node and make new node as head. 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 Inserting a node in doubly linked list at the ending. In this case, traverse the list to the end and insert the new node. New node right pointer points to null and left pointer points to the end of the list. Inserting a node in doubly linked list at the middle. As discussed in singly linked lists, traverse the list to the position node and insert the new node. New node right pointer points to the next node of the position node where we want to insert the new node. Also, new node left pointer points to the position node. Position node right pointer points to the new node, and the next node of position node left pointer points to new node. Now, let us write the code for all of these 3 cases. We must update the first element pointer in the calling function, not just in the called function. For this reason, we need to send a double pointer. The following code inserts a node in the doubly linked list. Void DLL insert int k equal to 1, struct DL node temp, new node malloc, if printf, always check for memory errors return, if new node data new node next head new node prev equal to null, if prev equal to new node. Inserting a node at the beginning head equal to new node. Return temp equal to head, while and temp next equal to null, temp equal to temp next, k++ if printf new node, next temp next new node, prev equal to temp, if temp next, prev new node, temp next equal to new node, return. Time complexity, O. In the worst case, we may need to insert the node at the end of the list. Space complexity, 0, for creating one temporary variable. Doubly linked list deletion. Similar to singly linked list deletion, here we have three cases. Deleting the first node, deleting the last node, deleting an intermediate node, deleting the first node in doubly linked list. In this case, the first node is removed from the list. It can be done in 2 steps. Create a temporary node which will point to the same node as that of head. Null head temp null. Now move the head node's pointer to the next node and change the head's left pointer to null. Then dispose of the temporary node, deleting the last node in doubly linked list. This operation is a bit trickier than removing the first node because the algorithm should find a node which is previous to the tail first. This can be done in 3 steps. Traverse the list, and while traversing, maintain the previous node address also. By the time we reach the end of the list, we will have 2 pointers, one pointing to the tail and the other pointing to the node before the tail. Dispose the tail node, deleting an intermediate node in doubly linked list. In this case, the node to be removed is always located between 2 nodes, and the head and tail links are not updated. The removal can be done in 2 steps. Similar to the previous case, maintain the previous node while also traversing the list. Upon locating the node to be deleted, change the previous node's next pointer to the next node of the node to be deleted. Void DL delete printf temprev temp next.
इधर आ जा हमके लाइट है
इसमें जो ड्यूरेशन है वैसे होगा, अगर नल है तो एम्प्टी है रिटर्न कर दो उसको, जो तो नहीं है उसको। अगर पोजीशन 1 है तो डिलीट करके वो जिसको डिलीट करने के वो तो फ्री कर देंगे बाद में। पहले जो हेड है उसको दूसरे उसके हेड के नेक्स्ट को वो हेड पॉइंटर को दे दो, बस हो गया और डिलीट हो गया पहले वाला। और अगर ऐसा होता है कि इफ़ हेड नॉट इक्वल टू नल, हेड प्रीवियस इक्वल टू नल एंड फ्री टाइम, ये एकदम अगर हेड अगर नल नहीं है तो ये ऐसा करना है, ये बाद में करना है। अगर वो रीड करने के बाद की बात है ये ऐसे करने की। अब पोजीशन 1 होती है तो ठीक है कि अगर हेड है नल नहीं है तो हेड प्रीवियस को क्या कर दो, नल कर दो, ठीक है। और फ्री कर दो उसको टेम्परेरी, जो टेम्परेरी वेरिएबल था जो हेड को लिया हुआ था, ऊपर यहाँ है डिक्लेयर कर दिया था हेड को, मेन हेड को टेम्परेरी वेरिएबल दिया हुआ था, तो उसको हम फ्री कर देंगे और रिटर्न कर देंगे, बस हो गया काम। और अगर हम किसी पोजीशन पर्टिकुलर पोजीशन में किसी को रीड करना चाहते हैं उस लिंक लिस्ट को, डब्ल्यू लिंक लिस्ट को, तो फिर क्या करेंगे, उस पोजीशन तक जब तक आते हैं तब तक चलाते जाओ उस के को। वो जो के है हमारा यहाँ पर 1 दिया हुआ है, उसको लास्ट तक चलाते जाएंगे, जो पोजीशन है उसके एक से पहले चला देंगे। एंड ये भी चेक करना है कि वो जो नेक्स्ट है वो नल ना हो। अगर वो नल हो गया है इसका मतलब वो आगे कुछ नहीं है, आगे सब खत्म हो गया, तो इसलिए वो नॉट इक्वल टू नल होना चाहिए। वो लास्ट आ गया उसका टेम्पो नेक्स्ट कर दो, ये लास्ट तक जा सकता है, उसके आगे नहीं जाएगा के प्लस प्लस। और अगर इसमें फिर ये देखना है ये तो हो गया, ठीक है। अगर के जो है वो पोजीशन -1 के इक्वल नहीं है तो प्रिंट कर दो डिजायर्ड पोजीशन डज नॉट एग्जिस्ट, ठीक है। पोजीशन -1 के इक्वल नहीं है, पोजीशन जो है उसे कम करो तो के वहाँ तक अगर पहुँच नहीं पाया, ठीक है, मतलब पोजीशन कुछ ऐसी डाल दी है जो पोजीशन उसमें है ही नहीं, है ना, वो कुछ ज़्यादा ही डाल दी उन्हें वैल्यू, उतनी लिंक लिस्ट ही नहीं है अपनी, तो पोजीशन एग्जिस्ट नहीं करती है। अगर उसके अंदर ला लेंगे तो वो पोजीशन एग्जिस्ट करेगी। सपोज वो पोजीशन कुछ बहुत ज़्यादा डाल दी उसने, और फिर वो ये मतलब ये तो बंद हो जाएगा, तो नल तो पहुँचेगा नहीं, वो ये तो बंद हो जाएगा, तो फिर यहाँ पर वो लिखेगा कि यह पोजीशन एग्जिस्ट नहीं करती है ना, हाइट नॉट इक्वल टू करेगा, और टेम्परेचर फिर प्रीवियस को करेगा, फिर ये पूरा टेम्परेचर प्रीवियस को करेगा, टेम्प टू नेक्स्ट टेम्प टेक्स को करेगा। टेम्प टू जो है वो ये रहा, ठीक है। अच्छा टेम्प प्रीवियस करेगा, और टेम्प टू नेक्स्ट जो है वो टेम्प नेक्स्ट को करेगा।
Next, if deletion from intermediate node temp next prev temp free, return time complexity O for scanning the complete list of size n, space complexity O for creating one temporary variable. 3.8 circular linked lists. In singly linked lists and doubly linked lists, the end of lists are indicated with null value. But circular linked lists do not have ends. While traversing the circular linked lists, we should be careful, otherwise we will be traversing the list infinitely. In circular linked lists, each node has a successor. Note that unlike singly linked lists, there is no node with null pointer in a circularly linked list. In some situations, circular linked lists are useful. For example, when several processes are using the same computer resource for the same amount of time, we have to...
यहाँ होता है. For example, when several processes are using the same computer resource CPU for the same amount of time, and we have to assure that no process accesses the resource before all the other processes do. ठीक है. No process accesses the resource before all the processes do. Round robin algorithm.
Sure that no process accesses the resource before all other processes do. The following
पहले वो कुछ स्पेसिफिक जो हम जो काम कर रहे हैं वो पहले एक्सेस करें ना, एक साथ तो कई सारी करेगी, लेकिन पहले वो है ना एक एक करके.
is a type declaration for a circular linked list of integers.
Yeah.
In a circular linked list, we access the element.
डिक्लेयर किया जाता है सर्कुलर लिंक का टाइप टेफ स्ट्रक्चर CLL नोड इन डाटा स्ट्रक्चर लिस्ट नोट स्टार नेक्स्ट. इस तरह से स्ट्रक्चर्स लिस्ट नोट मतलब इसी का फिर उसके अंदर बना दिया, उसको पॉइंट करने के लिए पॉइंटर बना दिया इसी का, इसका नहीं लिस्ट नोट का, लिस्ट नोट का बना दिया है जो नोड पहले डिक्लेयर किया है लिंक लिस्ट का.
Using the head node, counting nodes in a circular linked list. Head. The circular list is accessible through the node marked head. To count the nodes, the list has to be traversed from the node marked head with the help of a dummy node current, and stop the counting when current reaches the starting node head. If the list is empty, head will be null, and in that case set count equal to 0. Otherwise, set the current pointer to the first node and keep on counting till the current pointer reaches the starting node. In circular list length while return count. Time complexity O for scanning the...
अदरवाइज क्या करेंगे, नेक्स्ट ऑल प्लस प्लस कर देंगे, तब तक करंट है वो हेड के इक्वल नहीं होता है. सिंपल. देखो ये हेड है, जब तक वापस हेड तक नहीं आता तब तक वो प्लस प्लस तो हो जाएगा पूरा, तो वापस वो आ जाएगा वहाँ. यही उसमें कोडिंग में लिखा है. जो करंट नेक्स्ट करते जाओ, जब काउंट प्लस प्लस वाइल करंट नॉट इक्वल टू हेड. वो फ्लो चार्ट को उसने कोड में लिख दिया है, सी में लिख दिया है, सी प्रोग्रामिंग में. रिटर्न काउंट, इसका टाइम कॉम्प्लेक्सिटी भी बिग ऑफ एन रहेगा फॉर स्कैनिंग द कंप्लीट लिस्ट ऑफ साइज एन.
complete list of size n.
और
Space
स्पेस
complexity
कॉम्प्लेक्सिटी ऑर्डर
for
ऑफ
creating-
क्योंकि कोई एक्स्ट्रा स्पेस नहीं कुछ हो रही है. ये सब पॉइंटर ही है ना, हेड पॉइंटर है और काउंट वेरिएबल है, कुछ ज़्यादा कुछ है नहीं इसमें, तो बिग ऑफ 1 होगा. और क्रिएटिंग 1 टेम्परेरी वेरिएबल, ये टेम्परेरी वेरिएबल मैन तो ये है काउंट, ठीक है. फिर उसको भी रिटर्न कर देंगे. और करंट जो है, करंट भी इसमें
One temporary variable. Printing the contents of a circular linked list. We assume here that the list is being accessed by its head node. Since all the nodes are arranged in a circular fashion, the tail node of the list will be the node previous to the head node. Let us assume we want to print the contents of the node starting with the head node. Print its contents, move to the next node, and continue printing till we reach the head node again.
ऐसे
Head. Void print circular list data while.
Print-
Time complexity O for
जैसे प्रिंट करके बताया है, ये जैसे हेड को पॉइंट किया, अगर हेड अगर नल है, कुछ है ही नहीं, पूरा खाली है, तो रिटर्न कर दो, कुछ नहीं है वही। अगर कुछ है तो फिर चालू करो, लूप चालू करो, एक बार तो घुसना पड़ेगा अगर इसमें है तो। प्रिंट करंट का इसका जो डेटा है जो है उसका, और फिर आगे फिर पढ़ते जाओ, करंट करंट नेक्स्ट, जब तक करंट कब तक, जब तक वापस वो घूमकर हेड के पास नहीं आता। जब वो हेड के पास आ जाएगा तो वही लूप उसको ब्रेक लगा देंगे, ऑर्डर ऑफ एन हो जाएगा।
the complete list of size n. Space complexity O for temporary variable. Inserting a node at the end of a circular linked list. Let us add a node.
मैं अगर इसमें नहीं होता तो कंप्यूटर इंजीनियर होता।
हाँ, इंसर्टिंग, inserting a node at the end of a circular linked list. Let us add a node containing data at the end of a list, circular list headed by head.
Containing data at the end of a list headed by head. The new node will be placed just after the tail node, which means it will have to be inserted in between the tail node and the first node. Create a new node and initially keep its next pointer pointing to itself. New node. Update the next.
ये new node है, create a new node, initially keep it next pointer pointing to itself. ये हमने कुछ को पॉइंट करवा दिया, न्यू नोड लिया क्योंकि हम इसको इंसर्ट करना चाहते हैं यहाँ एंड में। तो ऐसे एक पहले बना लिया, ठीक है, क्रिएट कर लिया। उसके बाद में क्या किया, अपडेट द नेक्स्ट पॉइंटर ऑफ द न्यू नोड विद द हेड नोड। इसको यहाँ हेड नोड पहले यहाँ से स्टार्ट करूँ, एंड आल्सो ट्रैवर्स द लिस्ट टू द टेल तक
Next pointer of the new node with the head node and also traverse the list to the tail. That means in a circular list, we should stop at the node whose next node is head. Update the next pointer of the.
हम कहाँ स्टॉप होंगे, कब तक इसको आगे चलाते जाएंगे, जब तक वापस हेड नहीं आता उसका। नहीं, जो नेक्स्ट नोड इज हेड, यहाँ तक नेक्स्ट नोड जब तक हेड नहीं आता, करंट नेक्स्ट नोड इज नॉट इक्वल टू हेड, तब तक लूप चलाते जाओ। यहाँ पर आते हमें क्योंकि इसको लास्ट में ऐड करना ना, एंड ऑफ द सर्कुलर लिंक, इस तरह से लॉजिक लगाना पड़ता है, ठीक है। अपडेट द नेक्स्ट पॉइंटर प्रोपोर्शनल टू द पॉइंट टू द न्यू नोड एंड वी गेट द लिस्ट एज बिलो। ये लिस्ट मिल जाएगी
previous node to point to the new node, and we get the list as shown below. Void insert at ending CL if
और ये
print
इसी
EF.
प्रोग्रामिंग में इसका कोड लिख दिया। प्रोग्रामिंग वो उसी लॉजिक से बननी है, मेन लॉजिक समझना होता है, और फिर बेसिक सिंटेक्स पता होना चाहिए, फिर आप कोड लिख सकते हो कैसे कैसे लिखा जाता है। और वो मेन जो है ना, ये फ्लो चार्ट, ये कॉन्सेप्ट जो है ये पता होना चाहिए कैसे काम कर रहा है, फिर उसको कन्वर्ट करना आना चाहिए सिंटेक्स के अंदर, बस वो आप प्रोग्रामिंग कर लोगे। इंसर्ट एट एंड CLL, ये ऐसा फंक्शन बनाना पड़ेगा। इसके अंदर 3 वेरिएबल डाल देंगे, जिसमें एक तो 2 वेरिएबल, एक तो CLM नोड, इसका ये स्ट्रक्चर जो बनाया था हेड का, उसके डबल पॉइंटर इसलिए डाला क्योंकि हेड के पॉइंट को, उसका एड्रेस को ले रहा है, डबल पॉइंट। और फिर इन डेटा स्ट्रक्चर CLM नोड, इसको करंट को फिर हेड को कर लेंगे, जो करंट है वेरिएबल हेड को डिक्लेयर कर दिया। और फिर इसमें न्यू नोड है, इसने एक दूसरा नोड इसलिए लिया है क्योंकि ये हमने बनाना था यहाँ पर, ये हमने लॉजिक समझा था ना कि एक न्यू नोड बनाना पड़ेगा जिसमें डेटा रहेगा कुछ अलग नया, उसको इंसर्ट करना होगा, और डेटा यहाँ हमारा आया हुआ है, इसको हमें इसमें डालना पड़ेगा, ठीक है। तो मान लो साइज स्ट्रक्चर सीरियल नोड का स्ट्रक्चर ले लिया, ठीक है, और ये साइज ले लिया, ठीक है। और फिर जब तक न्यू नोड, अगर इफ़ नॉट न्यू नोड, अगर न्यू नोड मिला ही नहीं है, हमें सपोज इसमें मेमोरी ही नहीं है, तो मेमोरी एरर डाल देंगे। न्यू नोड जो है, ये न्यू नोड है वो बना ही नहीं, ये हमने न्यू नोड बनाया ना, ये सपोज बना ही नहीं, तो फिर क्योंकि ये बनेगा नहीं तो हमारा फिर काम होगा ही नहीं। ये जो न्यू नोड हमने बनाना है ना, अगर सपोज ये बना ही नहीं तो फिर नहीं हो पाएगा, तो उसमें बोल देना कि मेमोरी एरर है, क्योंकि उसके बिना फिर ये होगा ही नहीं। तो उसमें लिख देंगे मेमोरी एरर, रिटर्न कर दो, बस खत्म। ये सबसे इजी रहेगा। अगर मेमोरी है ही नहीं, अगर सपोज मिल गया सब कुछ, तो फिर न्यू नोड के डेटा को जो डेटा वहाँ से आया है उसको डेटा में बदल, उसका डेटा को इक्वल करना है। और फिर जब तक करंट नेक्स्ट नॉट इक्वल टू हेड हो जाता है, वही कॉन्सेप्ट, तो आप हेड नहीं हो जाता है, नहीं करंट का जो नेक्स्ट है वो हेड नहीं हो जाता है, मतलब लास्ट तक, यहाँ तक करंट का नेक्स्ट जब तक हेड नहीं हो जाता है, मतलब कहना क्या चाह रहा है कि जब तक ये नहीं आ जाता है तब तक उसको ट्रावर्स करते जाएंगे, ठीक है, वो करंट करंट नेक्स्ट करते जाएंगे, और जब वो आ जाएगा तो रुक जाएगा, और फिर न्यू नोड नेक्स्ट को फिर न्यू नोड वापस कर देंगे। और ये इम्पोर्टेंट है, न्यू नोड का जो नेक्स्ट है, मतलब ये जो न्यू नोड का डेटा हो गया, न्यू नोड का नेक्स्ट जो है वो न्यू नोड हो जाएगा। इफ हेड नोड हेड इक्वल नल हो जाएगा, तो हेड जो है वो न्यू नोड के इक्वल हो गया। हाँ सिंपल, अगर हेड कुछ पूरी खाली पड़ी है तो सीधी बात है, हेड को न्यू नोड के इक्वल कर दो, सीधे उसमें जोड़ दो। एल्स इसमें इंसर्शन है ना, ये इंसर्शन है ना, हाँ इंसर्शन ठीक है। और एल्स न्यू नोड नेक्स्ट, अगर सपोज सिर्फ एक ही हेड है तो क्या कर देंगे, न्यू नोड नेक्स्ट इक्वल टू हेड, ठीक है, वो हेड के इक्वल कर दो, और करंट नेक्स्ट न्यू नोड के इक्वल कर दो। करंट का जो नेक्स्ट है वो न्यू नोड के इक्वल कर दो। सही है, सही किया। ये करंट नेक्स्ट मतलब ये जो करंट है, ये लास्ट में पहुंचे थे ना, वो न्यू नोड के इक्वल कर दो। और न्यू नोड का जो नेक्स्ट है, पहले न्यू नोड को नेक्स्ट या न्यू नोड क्यों किया है, क्योंकि ये खुद को नोट करना था, ये वाला बनाया था, ये वाला न्यू नोड का नेक्स्ट न्यू नोड को ही करना था, इसलिए यहाँ पर ऐसा बनाया था। समझे यहाँ पर ऐसा क्यों किया है। फिर यहाँ पर वो इसलिए किया क्योंकि सपोज वहाँ पर अगर नल हो गया तो फिर ये हेड को डिक्लेयर करेंगे न्यू नोड को, तो फिर वो एक ही रहा ना। और फिर सपोज वहाँ कुछ एलिमेंट है तो फिर वो क्या करना है कि वो फिर उसके नेक्स्ट को हेड को डिक्लेयर कर दो, और न्यू नोड का नेक्स्ट करंट नेक्स्ट का न्यू नोड को डिक्लेयर कर दो। ठीक है, ये ऐसे रहेगा।
Turn new node data while current next new node if head equal to new node, else new node next current next equal to new node. Time complexity O for scanning the complete list of size n. Space complexity O for temporary variable.
Okay.
Inserting a node at the front of a circular linked list. The only difference between inserting a node at the beginning and at the end is that after inserting the new node, we just need to update the pointer. The steps for doing this are given below. Create a new node and initially keep its next pointer pointing to itself. Update the next pointer of the new node with the head.
ठीक है, जैसे यहाँ पर इसको डालना है at the front of the circular linked list, तो update the next pointer of new node with head node and also traverse the list until the tail.
Head node and also traverse the list until the tail. That means in a circular list, we should stop at the node, which is its previous node in the list. New node, update the previous head node in the list to point to the new node. Make the new node as the head. Data 4.15.7 to 4,400 and one head. Void insert at begin CLL if print f return new node data.
ठीक है, पहले करंट नेक्स्ट नोट इक्वल टू हेड, नोट इक्वल टू हेड कौन नेक्स्ट फिर न्यू नोट नेक्स्ट न्यू नोट। ओके, सही है। ये मिलता जुलता ही कोड है पहले वाले जैसा ही, उसमें फ़र्क ये होगा कि एल्स के अंदर ये जो नीचे वाला एल्स है इसमें फ़र्क आएगा, न्यू नोड नेक्स्ट हेड के बराबर हो जाएगा। और हाँ, करंट जो नेक्स्ट है वो हाँ हेड न्यू नोड आ जाएगा। यहाँ पर देखो, यहाँ पर एक लाइन का फ़र्क है, ये एक लाइन का फ़र्क है, यहाँ पर ये कोड और ये कोड है, करंट नेक्स्ट न्यू नोड। फिर नीचे जो है ना, जो हेड को फिर वो जो बना देते हैं, है ना, हेड को न्यू नोड बना दिया है, बस यहीं पर फ़र्क आ गया। जैसे एक लाइन के कोड से ये पूरा चेंज हो गया, उसका वो पीछे यहाँ पर था वो आगे आ जाएगा, सबसे आगे सिर्फ एक यहाँ पर ये जो लाइन डाली है ये पूरा ऑलमोस्ट सेम ही है, आप देख सकते हैं। ठीक है ना।
Data while current, next, new node, if head equal to new node, else, new node, next head, current, next, new node, head equal to new node, return. Time complexity O for scanning the complete list of size n. Space complexity O for temporary variable. Deleting the last node in a circular linked list. The list has to be traversed to reach the last but one node. This has to be named as the tail node. Its next field has to point to the first node. Consider the following list. And to delete the last node 40, the list has to be traversed till you reach 7. The next field of 7 has to be changed to point to 60, and this node must be renamed ptail. Traverse the list and find the tail node and its previous node. Update the next pointer of tail node.
जैसे यहाँ पर क्या किया, traverse the list, find the tail node and its previous node. ठीक है, तो tail node पता की, उसके previous node को पता किया. Find the tail node and its previous nodes. Okay. And update the next pointer of tail node's node to point to head. Okay.
Node's previous node to point to head. Dispose of the tail node. Void delete last node from CLL. Struct CL node temp equal to head. Current equal to head if printf return. While temp equal to current. Current. Next.
Easy है. Current next. वो वापस वही चलना है. जब तक head नहीं आता है, चलाते जाओ. जैसे इसके head आ गया, उसी को delete मार दो. Last node को delete करना है ना. ठीक है. Temp current next वो current next वो वहीं पर आ जाएगा. तो उसमें क्या करना, टेम्प नेक्स्ट जो है उससे पहले वाले को करंट नेक्स्ट के डाल दो, वो मतलब वापस हेड को पॉइंट कर देगा. और फ्री करंट को फ्री कर दो, मतलब करंट कौन था, वही था. टेम्प नेक्स्ट को करंट नेक्स्ट कर दिया, और जो करंट है करंट नेक्स्ट को चला गया. करंट नेक्स्ट मतलब वही जो लास्ट वाला जो है उसके पास चला गया. और जो टेम्प नेक्स्ट है वो उसके पीछे वाला भाग है, वो पीछे वाला लिंक लिस्ट है, तो उसको करंट के नेक्स्ट डाल दिया, उसको मतलब हेड पर डाल दिया. ये तो करंट, ठीक है. ये करंट नेक्स्ट था, इसका जो करंट नेक्स्ट है उसको रीड मार दिया. जो टेम्परेरी जो करंट था, और फिर करंट को नेक्स्ट कर दिया. इसको कर दिया हेड. ऐसे ठीक है.
Temp next current, next, free, return. Time complexity O for scanning the complete list of size n. Space complexity O for a temporary variable. Deleting the
ठीक है. इसको scanning size of n for temporary variable. ठीक है. ओके.
first node in a circular list. The first node can be deleted by simply replacing the next field of the tail node with the next field the first node of. Find the tail node of the linked list by traversing the list. Tail node is the previous node to the head node, which we will delete. Create a temporary node, which will point to the head. Also, update the tail node's next pointer to point to next node of head. Now, move the head pointer to next node. Create a temporary node, which will point to head. Also, update the tail node's next pointer to point to next node of head. Void delete front node from CLL. Struct CLL node temp equal to head. Struct CLL node current equal to head. If printf return, while current next.
इसमें दो पॉइंटर लगाने पड़ेंगे, क्योंकि इसमें क्या करना है, एक पोजीशन पर डेट करना है. जैसे फर्स्ट नोड, डेटिंग द फर्स्ट नोड सेकंड लिस्ट, इसमें दो पॉइंटर इसलिए लगाने पड़ेंगे क्योंकि पहले वाले को रेट करना है. तो एक इसमें ऐसा रखना पड़ेगा जो आगे की तरफ रहेगा. ठीक है. नॉट टू बी रिलेटेड दिस वन. एक आगे यहाँ पे जाना पड़ेगा, इस वाले के पास में एक को जाना पड़ेगा.
Void delete front node from CLL.
जैसे नोट टू बी रिलेटेड दिस वन, प्रीवियस नोट टू बी, और फिर क्योंकि इसके पास जाके, और फिर इसका जो आगे वाला रहेगा, एक पॉइंटर यहीं पर रहेगा और एक पॉइंटर यहाँ आगे चला जाएगा, और फिर वो इसके आगे वाले इसके नेक्स्ट को इसको पॉइंट कर डालेगा और इसको फ्री कर देंगे. बस ये इसका काम है. देखो ये सिंपल सा कोड है इसका.
Struct CLL node temp equal to head. Struct CLL node current equal to head. If printf return, while current next current.
अगर हेड अगर ना खाली है तो लिस्ट एम्प्टी है, खत्म. और इसमें कोई दूसरा कोई नोड नहीं है तो कोई झंझट नहीं मेमोरी का. वो अलग से हम एक नोड बना रहे हैं उसका CLL नोड, तो उसकी ज़रूरत नहीं है. तो सीधे पॉइंटर से काम हो जाएगा. पॉइंटर एक करंट नेक्स्ट जो है वो हेड की तरफ जाएगा, और हेड की तरफ जाते हुए ज़्यादा नहीं तो नेक्स्ट करता जाएगा. ठीक है. वो करंट फिर करंट नेक्स्ट जो है वो हेड का नेक्स्ट हो जाएगा. करंट नेक्स्ट जो हेड का नेक्स्ट, देखो ना, करंट नेक्स्ट जो हेड का नेक्स्ट हो जाएगा, वो हेड जो है वो जो हेड है वो हेड का नेक्स्ट हो जाएगा. जो हेड है वो हेड का नेक्स्ट हो जाएगा. और जो करंट नेक्स्ट है, जो लास्ट वाला है उसका हेड नेक्स्ट हो जाएगा, हेड का नेक्स्ट हो जाएगा, और हेड है वो भी हेड का नेक्स्ट हो जाएगा, फिर टाइम कर देंगे और खत्म हो जाएगा.
The next, head equal to head, next, free return. Time complexity, O for scanning the complete list of size n. Space complexity, O for a temporary variable. Applications of circular list. Circular linked lists are used in managing the computing resources of a computer. We can use circular lists for implementing stacks and queues. 3.9, a memory-efficient doubly linked list. In conventional implementation, we need to keep a forward pointer to the next item on the list and a backward pointer to the previous item. That means elements in doubly linked list implementations consist of data, a pointer to the next node, and a pointer to the previous node in the list as shown below. Conventional node definition. Recently, a journal presented an alternative implementation of the doubly linked list ADT, with insertion, traversal, and deletion operations. This implementation...
Recently, a journal Sina presented an alternative implementation of the doubly linked list like ADT, doubly linked list ADT with insertion, traversal and deletion operation. The implementation based on pointer difference. Okay. New node definition. ये पहले ये definition थी और फिर ये definition आ गई in data structural linked list pointer difference के थ्रू हम फिर इसको करने लगे हैं अभी नया जो जना हुआ है उसके अकॉर्डिंग. Implement pointer difference
is based on pointer difference. Each node
और ये फिर यही कॉन्सेप्ट आता है फिर इसमें पैटर्न्स में. ये जो आता है ना इस वजह से मिनिमाइज करेंगे 2 पॉइंटर्स. ये इसमें लिंक लिस्ट का नाम क्यों नहीं दिया है, इतना इम्पोर्टेंट है वो, 2 पॉइंटर्स में है वो, उसके थ्रू करेंगे. और फिर उसी के अंदर बाइनरी सर्च में जो जाएंगे तो फिर बेसिक एरे है. डायरेक्शन
हाँ 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 जानता हूँ. हाँ ये पेंटर तो ये भी वैसे ठीक है.
uses only one pointer field to traverse the list back and forth. New node definition. The ptr-diff pointer field contains the difference between the
हाँ हाँ हाँ
pointer to the next node and the pointer to the previous node. The pointer difference is calculated by using exclusive OR operation. The ptr-diff of the start node is the of null and next node. Similarly, the ptr-diff of end node is the of previous node and null. As an example, consider the following linked list. In the example above, the next pointer of A is null B. The next pointer of B is AC. The next pointer of C is B plus D. The next pointer of D is C null. Why does it work?
Oh, that's great.
ठीक है ठीक ठीक.
गजब इंफॉर्मेशन है ये जो इंफॉर्मेशन है ये सिर्फ किताब में ही मिलेगी, ये कहीं और नहीं दी है.
वो तो है.
ये कोई नहीं बताता.
मास्टरी करना मतलब कोडिंग की मास्टरी आ गई ना.
हाँ.
लॉजिक
क्योंकि वीडियो में
तो
जनरल
नई लैंग्वेज बना सकते हैं, क्योंकि ये लैंग्वेज बनाना भी वो भी कोड ही जनरेट.
नहीं वो मुश्किल नहीं है. मैं तो प्रॉब्लम सॉल्व करने आना चाहिए, वो लैंग्वेज बनाना कोई मुश्किल काम नहीं. वो उस लैंग्वेज से वो प्रॉब्लम सॉल्व हो रही है नहीं हो रही, वो देखो. ठीक है.
To find the answer to this question, let us consider the properties of x plus x equal to 0.
और सेम देखो ये सेम उसी तरह से वर्क करता है. टू फाइंड द आंसर ऑफ दिस क्वेश्चन लेट अस कंसीडर द प्रॉपर्टी. ये वही एक्सओर है. दो सेम होंगे तो 0 होगा.
चित्र क्या है इसको क्या
ये एक्सओर होता है. ये डिजिटल लॉजिक का सिंबल है. एक एक्सओर एक्स दो सिमेट्रिक होते हैं तो 0 आता है, सिमेट्रिक डिफरेंट होते हैं तो 1 आता है. यानी वो सेम आता है. देखो x इसमें 1 नहीं है, जो वो 1 0 की बात है. 1 होता है तो 1 आ जाता है. इसमें x है तो x आ जाता है ना. जब यहाँ पर x है तो x आ जाएगा. x और y है तो y x सिमेट्रिक है. एक्स वाई जेड ये दोनों प्रॉपर्टीज को फॉलो करता है, सिमेट्रिक प्रॉपर्टी को भी और ट्रांजिस्टिव प्रॉपर्टी को भी, कि पहले एक्स वाई के साथ में एक्सोर किया, फिर जेड के साथ में किया, या फिर पहले वाई जेड के साथ में एक्सोर किया और फिर एक्स के साथ में किया, तो सेम, या पहले एक्स वाई किया या वाई एक्स के साथ में किया, सिमेट्रिक भी है, ट्रांजिस्टिव है, सिमेट्रिक है। ये जो है इसको जो पॉइंटर डिफरेंस क्या नाम है इसको, है ना, पॉइंटर डिफरेंस इसको बोलते हैं, एक्सक्लूसिव और एक्सॉर। इससे काम बहुत आसान हो जाता है। ठीक है, अब इसका कैसे यूज होगा आगे बताएंगे। देखो
x plus 0 equal to x xo,
अभी हम
y
पहुंच
o
चुके हैं
x
109 नंबर पेज पे। ठीक है,
be right z
कोशिश करते
equal
हैं
to
आज
x.
आधे खत्म कर।
For the example above, let us assume that we are at C node and want to move to B. We know that C's p-tar diff is defined as BD. If we want to move to B, performing on C's p-tar diff with D would give B. This is due to the fact that, similarly, if we want to move to D,
इसमें देखो, इसमें दो सिमिलर आ गए ना, डी एक्सॉर डी, तो ये जीरो हो जाएगा। ठीक है, डी एक्सॉर डी तो बी आ जाएगा, क्योंकि उसमें ना बी एक्सॉर जीरो या एक्स एक्सॉर जीरो क्या था, बी है, वह ऐसे कॉन्सेप्ट लगता है ना। यहाँ एक्स जीरो ये तो सेम थे, तो क्या हो गया जीरो, और उसका बी बी हो गया। ये सब लॉजिक कैसे लगता है। ठीक है, और जैसे बी एक्सॉर डी, इसमें बी और बी क्या हो जाएगा, जीरो हो जाएगा, फिर डी के साथ डी हो जाएगा ऐसे।
then we have to apply to C's p-tar diff with B to give D. From the above discussion, we can see that just by using a pointer, we can move back and forth. A memory-efficient
तो क्या पता
implementation
चला कि सिंगल पॉइंटर यूज किया है यहाँ पर एक्सक्लूसिव, और उससे हम आगे जा रहे हैं, पीछे जा रहे हैं, है ना। आगे कैसे जा रहे हैं, जैसे ये है बी और फिर उसमें जो डी है वो उसके आगे, जैसे यहाँ हमने बनाया था ना, ये देखो ये जो बनाया था ये कि जैसे ये बी और डी है। ठीक है, और फिर उसके आगे जो है वो ये है सी और नल, या फिर ये ए और सी, इस तरह से आगे पीछे पूरा ऐसे जा सकते हैं पूरा। ठीक है, पूरा ऐसे करके हम उसको इम्प्लीमेंट कर सकते हैं।
doubly linked list possible with minimal compromising of timing efficiency. 3.10 unrolled linked
ये
lists.
कहीं नहीं पढ़ाते, अनरोल लिंक्ड लिस्ट से भी वन ऑफ द बिगेस्ट एडवांटेज ऑफ लिंक्ड लिस्ट।
One of the biggest advantages of linked lists over arrays is that inserting an element at any location takes only time. However, it takes O to search for an element in a linked list. There is a simple variation of the single.
यही फ़र्क है, एरे में क्या है कि ऑर्डर ऑफ वन में हो जाता है, तो इंडेक्स बनी होती है, इंडेक्स में वो मेमोरी वो की होती है, वो पूरा उसमें जाके वो उसको डाल देता है। कंटिन्यू करते हैं।
Linked list called there is a simple variation of the singly linked list called unrolled linked lists. An unrolled linked list stores multiple elements in each node. In each block, a circular linked list is used to connect all nodes. List head blockhead 10136. Assume that there will be no more than n elements in the unrolled linked list at
जैसे यहाँ देखो, और 10 इस तरह से ब्लॉक हेड मल्टीपल एलिमेंट्स
any time. To simplify this problem, all blocks except the last one contain exactly elements. Thus, there will be no more than blocks at any time. Searching for an element in unrolled linked lists. In unrolled linked lists, we can find the KTH element in O. K1, traverse the list of blocks to the one that contains the KTH node, that is the TH block. It takes O, since we may find it by going through no more than blocks. And 2, find the since there are no more than nodes in a single block. List head. Inserting an element in unrolled linked lists. List head. When inserting a node, we have to rearrange the nodes in the unrolled linked list to maintain the properties previously mentioned, that each block contains nodes. Suppose that we insert a node X after the ITH node, and X should be placed in the JTH block. Nodes in the JTH block and in the blocks after the JTH block have to be shifted toward the tail of the list so that each of them still have n nodes. In addition, a new block needs to be added to the tail if the last block of the list is out of space, that is, it has more than nodes. Performing shift operation. Note that each shift operation, which includes removing a node from the tail of the circular linked list in a block and inserting a node to the head of the circular linked list in the block after, takes only O. The total time complexity of an insertion operation for unrolled linked lists is therefore O. There are at most O blocks and therefore at most O shift operations. 1. A temporary pointer is needed to store the tail of A. 2. In block A, move the next pointer of the head node to point to the second to last node so that the tail node of A can be removed. 3. Let the next pointer of the node which will be shifted point to the tail node of B. 4. let the next pointer of the head node
अरे बहुत ज़्यादा इसमें रोटेशन होता है.
of B point
Let the next pointer of the head B point to the okay, fine.
temp points 2. A5. Finally, set the head pointer of B to point to the node temp points 2. Now the node temp points 2 becomes the new head node of B73. 6. Temp pointer can be thrown away. We completed the shift operation to move the original tail node of A to become the new head node of B performance. With unrolled linked lists, there are a couple of advantages, one in speed and one in space. First, if the number of elements in each block is appropriately sized, we get noticeably better cache performance from the improved memory locality. Second, since we have O links, where n is the number of elements in the unrolled linked list, and m is the number of elements we can store in any block, we can also save an appreciable amount of space, which is particularly noticeable if each element is small. Comparing linked lists and unrolled linked lists. To compare the overhead for an unrolled list, elements in doubly linked list implementations consist of data, a pointer to the next node, and a pointer to the previous node in the list, as shown below. Assuming we have 4 byte pointers, each node is going to take 8 bytes. But the allocation overhead for the node could be anywhere between 8 and 16 bytes. Let's go with the best case and assume it will be 8 bytes. So, if we want to store IK items in this list, we are going to have 16 kilobytes of overhead. Now, let's think about an unrolled linked list node. It will look something like this. Therefore, allocate a single node with an array of
Structure and linked block. Structure and the node count. ओके रीलिंग ब्लॉक है, ठीक है. नेक्स्ट ब्लॉक को करेगा और उसमें हेड होगा तो नोट काउंट हो.
elements will now cost 428 bytes or 4.28 bytes per element. Thinking about our IK items from above, it would take about 4.2 bytes of overhead, which is close to 4 times better than our original list. Even if the list becomes severely fragmented and the item arrays are only 1/2 full on average, this is still an improvement. Also, note that we can tune the array size to whatever gets us the best overhead for our application. Implementation. Hashtag include dio.h, hashtag include string.h, hashtag include stddlib.h, hashtag include math.h, hashtag include time.h int block size, max number of nodes in a block, struct list node next int value, struct link block struct list node temp malloc temp next.
भागता है, ठीक है. ये नेक्स्ट को पॉइंट करेगा ब्लॉक को, और जो ब्लॉक है वो अरे भैया ठीक है. हाँ
Start shift operation from block P void shift, struct linked block B, struct list node temp, while, if this block still have to shift if A minus next, null, reach the end. A little different A minus next block, B, A minus next, temp A minus head next, A head next A minus head next, B minus head temp, temp next temp, A node count, B node count plus plus, gelsol B A minus next, temp A minus head, next A head next to head, next, temp next B minus head, next B head next temp, B head temp A node count, B node count plus plus 1 AB, 1 void add element else. int circ element, struct list node P, struct linked block Q, circ element return P value, int test enrolled linked list, int tt clock, mikx char cmd, scanf, block size equal to plus 1. For else if equal to 0, else return 0. 3.11 skip lists. Binary trees can be used for representing abstract data types such as dictionaries and ordered lists. They work well when the elements are inserted in a random order. Some sequences of operations, such as inserting the elements in order, produce degenerate data structures that give very poor performance. If it were possible to randomly permute the list of items to be inserted, trees would work well with high probability for any input sequence. In most cases, queries must be answered online, so randomly permuting the input is impractical. Balanced tree algorithms rearrange the tree as operations are performed to maintain certain balance conditions and assure good performance. Skip lists are a probabilistic alternative to balanced trees. Skip list is a data structure that can be used as an alternative to balanced binary trees. As compared to a binary tree, skip lists allow quick search, insertion, and deletion of elements. This is achieved by using probabilistic balancing rather than strictly enforced balancing. It is basically a linked list with additional pointers such that intermediate nodes can be skipped. It uses a random number generator to make some decisions. In an ordinary sorted linked list, search, insert, and delete are because the list must be scanned node by node from the head to find the relevant node. If somehow we could scan down the list in bigger steps, we would reduce the cost of scanning. This is the fundamental idea behind skip lists. Skip lists with 1 level. Skip lists with 2 levels. Skip lists with 3 levels. Performance. In a simple linked list that consists of n elements, to perform a search, n comparisons are required in the worst case. If a second pointer pointing 2 nodes ahead is added to every node, the number of comparisons goes down to n2 plus 1 in the worst case. Adding 1 more pointer to every 4th node and making them point to the 4th node ahead reduces the number of comparisons to plus 2. If this strategy is continued so that every node pointers points to 2i, 1 nodes ahead, O performance is obtained and the number of pointers has only doubled. The find, insert, and remove operations on ordinary binary search trees are efficient, O, when the input data is random, but less efficient, O, when the input data is ordered. Skip list performance for these same operations and for data set is about as good as that of randomly built binary search trees, namely O, comparing skip lists and unrolled linked lists. In simple terms, skip lists are sorted linked lists with 2 differences. The nodes in an ordinary list have 1 next reference. The nodes in a skip list have many next references. The number of forward references for a given node is determined probabilistically. We speak of a skip list node having levels, 1 level per forward reference. The number of levels in a node is called the size of the node. In an ordinary sorted list, insert, remove, and operations require sequential traversal of the list. This results in O performance per operation. Skip lists allow intermediate nodes in the list to be skipped during a traversal, resulting in an expected performance of O per operation. Implementation, #include stdo.h. #include stdlib.h greater than #define max skip level 5 struct list node, 1 int data, struct list node, next, struct skip list for update list.header, list level, new level. Make new node if plus 1 new level size eof equal to 0, printf n, exit temp data equal to data 4, update next links temp next update next, 1 update next equal to temp return, delete node containing data void delete element into I struct list node update max skip level plus 1, temp list.header for data temp next, update equal to temp next if return, adjust next pointers for if equal to temp break update next plus temp next, free. Adjust header level while and end equal to list, header, list, list level. Find node containing data, struct list node find element in I, A, maximum equal to atoy. Init list if equal to 0, insert element for return 0. 3.12 linked lists, problems and solutions. Problem. 1 implement stack using linked list. Solution. Refer to stacks chapter. Problem -2 find nth node from the end of a linked list. Solution. Brute force method. Start with the first node and
problems are in chapter के पूरी problems so you can see it here. Okay, a lot of problems are there. 123 till 163 stacks, and 170 for the stack will be over, and queues will be till 214. So my target is to complete 12 queues. Then tomorrow I will complete trees and more and more. Okay, fine. 214 till 214 I have to do. 214 to 224 I think. 224 I have to do.
count the number of nodes present at a node. If the number of nodes is n, 1 then returns saying fewer number of nodes in the list. If the number of nodes is n1, then go to next node. Continue this until the numbers of nodes after current node are n1. Time complexity, O, for scanning the remaining list for each node. Space complexity, O. Problem -3, can we improve the complexity of problem 2? Solution, yes, using hash table. As an example,
Using hash table, you can do it. Anda. एन स्क्वायर हो जाएगा ना, क्योंकि वो n-1 तक तो जाएगा ही जाएगा. Scanning the remaining list for each node. Okay. Okay.
example, consider the following list. Head. In this approach, create a hash table whose entries are of node, node address. That means key is the position of the node in the list, and value is the address of that node. By the time we traverse the complete list, we can find the list.
On address of 5 node, address of 1 node, position of list. Address of list of node 2, address of 70 node, position in list 3, address of 4 node, position in list 4.
By the time we traverse the complete list, we can find the list length. Let us say the list length is m. To find nth from the end of linked list, we can convert this to mn plus first from the beginning. Since we already know the length of the list, it is just a matter of returning mn plus first key value from the hash table. Time complexity, time for creating the hash table, t equal to O. Space complexity, since we need to create a hash table of size m, O. Problem -4, can we use the problem 3 approach for solving problem 2 without creating the hash table? Solution, yes. If we observe the problem 3 solution, what we are actually doing is finding the size of the linked list. That means we are using the hash
तभी बनाइए देखो. Address of 5 node. Okay. ये बहुत आसान होगा.
table to find the size of the linked list. We can find the length of the linked list just by starting at the head node and traversing the list. So we can find the length of the list without creating the hash table. After finding the length, compute mn plus 1, and with one more scan, we can get the mn plus first node from the beginning. This solution needs 2 scans, one for finding the length of the list and the other for finding mn plus first node from the beginning. Time complexity, time for finding the length plus time for finding the mn plus first node from the beginning. Therefore, t equal to O plus O approximately.
What is m? Almost करोगे. Okay. m minus n plus 1 डालो. उसको m वो है वो जो हमें फाइंड करना है. Okay. तो वो पता चल जाएगा. ये इसमें मैथमेटिक्स लगा के इसको सॉल्व कर सकते हैं. वो जल्दी हो जाएगा.
Equal to space complexity, O. Hence, no need to create the hash table.
Yeah.
Problem 5, can we solve problem 2 in one scan? Solution, yes. Approach, use 2 pointers pnth node and ptemp. Initially, both point to head node of the list. Pnth node starts moving only after ptemp has made n moves. From there, both move forward until ptemp reaches the end of the list. As a result, pnth node points to nth node from the end of the linked list. Note, at any point of time, both move one node at a time. Struct list node nth node from end, struct list node pnth node equal to null, ptemp equal to head, for if ptemp equal to ptemp next, while if else pnth node equal to head equal to pnth node next, ptemp equal to ptemp next, if return pnth node, return null. Time complexity, O, space complexity, O. Problem 6. Check whether the given
Okay, fine. Let's build on the next speed time. Okay. Okay, hold on to this efficient. ओके 2 पॉइंटर्स बना के कर सकते हैं, ये भी बहुत अच्छा तरीका है।
is either null terminated or ends in a cycle. Solution, brute force approach. As an example, consider the following linked list which has a loop in it. The difference between this list and the regular list is that in this list there are 2 nodes whose next pointers are the same. In regular singly linked lists, each node's next pointer is unique. That means the repetition of next pointers indicates the existence of a loop. One simple and brute force way of solving this is start with the first node and see whether there is any node whose next pointer is the current node's address. If there is a node with the same address, then that indicates that some other node is pointing to the current node, and we can say a loop exists. Continue this process for all the nodes of the linked list. Does this method work? As per the algorithm, we are checking for the next pointer addresses, but how do we find the end linked list? Note, if we start with a node in a loop, this method may work depending on the size of the loop. Hashing technique for solving problem 6? Solution, yes. Using hash tables, we can solve this problem. Algorithm. Traverse the linked list nodes one by one. Check if the address of the node is available in the hash table or not. If it is already available in the hash table, that indicates that we are visiting the node that was already visited. This is possible only if the given linked list has a loop in it. If the address of the node is not available in the hash table, insert that node's address into the hash table. Continue this process until we reach the end of the linked list or we find the loop. Time complexity, O for scanning the linked list. Note that we are doing a scan of only the input. Space complexity, O for hash table. Problem 8. Can we solve problem 6 using the sorting technique? So, no. Consider the following algorithm which is based on sorting. Then we see why this. Algorithm fails. Algorithm. Traverse the linked list nodes one by one and take all the next pointer values into an array. Sort the array that has the next node pointers. If there is a loop in the linked list, definitely 2 next node pointers will be pointing to the same node. After sorting, if there is a loop in the list, the nodes whose next pointers are the same will end up adjacent in the sorted list. If any such pair exists in the sorted list, then we say the linked list has a loop in it. Time complexity, O for sorting the next pointers array. Space complexity, O for the next pointers array. Problem with the above algorithm works only if we can find the length of the list. But if the list has a loop, then we may end up in an infinite loop. Due to this reason, the algorithm fails. Problem 9. Can we solve the problem 6? No. Solution, yes. Efficient approach. This problem was solved by Floyd. The solution is named the Floyd cycle finding algorithm. It uses 2 pointers moving at different speeds to walk the linked list. Once they enter the loop, they are expected to meet, which denotes that there is a loop. This works because the only way a faster moving pointer would point to the same location as a slower moving pointer is if somehow the entire list or a part of it is circular. Think of a tortoise and a hare running on a track. The faster running hare will catch up with the tortoise if they are running in a loop. As an example, consider the following example and trace out the Floyd. From the diagrams below, we can see that after the final step, they are meeting at some point in the loop, which may not be the starting point of the loop. Note, slow PTR moves 1 pointer at a time and fast PTR moves 2 pointers at a time. int does linked list has loop. Struct list node slope PTR equal to head. Fast PTR equal to head, while slope PTR next. Fast PTR next. Next, if return 1, return 0. Time complexity, O. Space complexity, O. Problem minus 10 are given a pointer to the first element of a linked list L. There are two possibilities for L. It either ends, or its last element points back to one of the earlier elements in the list. Give an algorithm that tests whether a given list L is a snake or a snail. Solution, it is the same as 6. Problem minus 11, check whether the given linked list is null terminated or not. If there is a cycle, find the start node of the loop. Solution, the solution is an extension to the solution in problem 9. After finding the loop in the linked list, we initialize the slope PTR to the head of the linked list. From that point onwards, both slopetr and fastPTR move only one node at a time. The point at which they meet is the start of the loop. Generally, we use this method for removing the loops. In find begin off loop, struct list node slopetr head, fastPTR equal to head, int loop exists equal to 0, while slopetr next, fastPTR next, next, if loop exists equal to 1, break if slopetr equal to head, while fastPTR next, slopetr equal to slopetr, next, return slopetr, return null. Time complexity, O. Space complexity, O. Problem minus 12.
The previous discussion and problems, we understand that the meeting of tortoise and hare concludes the existence of the loop. But how does moving the tortoise to the beginning of the linked list while keeping the hare at the meeting place, followed by moving both one step at a time, make them meet at the starting point of the cycle? Solution. This problem is at the heart of number theory. In the Floyd cycle finding algorithm, notice that the tortoise and the hare will meet when they are n times L, where L is the loop length. Furthermore, the tortoise is at the midpoint between the hare and the beginning of the sequence because they move. Therefore, the tortoise is nxl away from the beginning of the sequence as well. If we move both one step at a time, from the position of the tortoise and from the start of the sequence, we know that they will meet as soon as both are in the loop, since they are n times L, a multiple of the loop length apart. One of them is already in the loop, so we just move the other one in single step until it enters the loop, keeping the other nxl away from it at all times. Problem 13 in the Floyd cycle, finding algorithm. Does it work if we use steps 2 and 3 instead of 1 and 2? Solution, yes, but the complexity might be high. Trace out an example. Problem 14, check whether the given linked list is null terminated. If there is a cycle, find the length of the loop. Solution, this solution is also an extension of the basic detection problem. After finding the loop in the linked list, keep the slope tr as it is. The fast PTR keeps on moving until it again comes back to slope tr. While moving fast PTR, use a counter variable which increments at the rate of 1. In find loop length, struct list node slope tr head, fast PTR equal to head, bind int loop exists 0, counter equal to 0, while slope tr next, fast ptr next. Next, if loop exists equal to 1, break if fast ptr equal to fastpr next, while fast ptr next, counter plus plus, return counter, return 0, if no loops exists. Time complexity, O. Space complexity, O. Problem 15, insert a node in a sorted linked list. Solution, traverse the list and find a position for the element and insert it. Struct list node insert in sorted list. One struct list node current equal to head, temp, if return new node. Traverse the list until the item bigger than new node value, while temp equal to current. Next, insert the new node before the big item new node. Next current, temp, next new node, return head. Time complexity, O. Space complexity, O. One problem 16 solution, reverse a singly linked list. Iterative version struct, list node, reverse list, next node, head next, equal to temp, temp equal to head, head equal to next node, return temp. Time complexity, O. Space complexity, O. Recursive version, we will find it easier to start from the bottom up by asking and answering tiny questions. What is the reverse of null? Null. What is the reverse of a one-element list? The element itself. What is the reverse of an n-element list? The reverse of the second element followed by the first element. Struct list node recursive reverse, if return null, if return list. Struct list node second element, head next. Need to unlink list from the rest, or you will get a cycle head next equal to null. Reverse everything from the second element on struct list node, reverse rest equal to recursive reverse. Second element, next equal to head. Then we join the two lists, return reverse rest. Time complexity, O. Space complexity, O for recursive stack. Problem 10. Suppose there are two singly linked lists, both of which intersect at some point and become a single linked list. The head.
Okay, now going to start this problem number 18.
Solution, no. Consider the following algorithm, which is based on sorting, and see why this algorithm fails. Algorithm. Take first list node pointers and keep them in some array and sort them. Take second list node pointers and keep them in some array and sort them. After sorting, use two indexes, one for the first sorted array and the other for the second sorted array. Start comparing values at the indexes and increment the index according to whichever has the lower value. At any point, if we are able to find two indexes whose values are the same, then that indicates that those two nodes are pointing to the same node, and we return that node. Time complexity, time for sorting lists plus time for scanning equal to O plus O plus O. We need to consider the one that gives the maximum value. Space complexity, O. Any problem with the above algorithm? Yes. In the algorithm, we are storing all the node pointers of both the lists and sorting, but we are forgetting the fact that there can be many repeated elements. This is because after the merging point, all node pointers are the same for both the lists. The algorithm works fine only in one case, and it is when both lists have the ending node at their merge point. Problem -19. Can we solve problem 17 using hash tables? Solution, yes. Algorithm. Select a list which has less number of nodes. Now, traverse the other list, and for each node pointer of this list, check whether the same node pointer exists in the hash table. If there is a merge point for the given lists, then we will definitely encounter the node pointer in the hash table. Time complexity, time for creating the hash table plus time for scanning the second list equal to O plus O plus O, depending on which list we select for creating the hash table. But in both cases, the time complexity is the same. Space complexity, O or O. Problem 20, can we use stacks for solving the problem? 17, solution, yes. Algorithm. Create two stacks, one for the first list and one for the second list. Traverse the first list and push all the node addresses onto the first stack. Traverse the second list and push all the node addresses onto the second stack. Now both stacks contain the node address of the corresponding list. Now compare the top node address of both stacks. If they are the same, take the top elements from both the stacks and keep them in contemporary variables. Continue this process until the top node addresses of the stacks are not the same. This point is the one where the lists merge into a single list. Return the value of the temporary variable. Time complexity O for scanning both the lists. Space complexity O for creating two stacks for both the lists. Problem -21. Is there any other way of solving problem 17? Solution, yes. Using finding the first repeating number approach in an array. Algorithm. Create an array A and keep all the next pointers of both the lists in the array. In the array, find the first repeating element. The first repeating number indicates the merging point of both the lists. Time complexity, O. Space complexity, O. Problem -22. Can we still think of finding an alternative solution for problem 17? Solution, yes. By combining sorting and search techniques, we can reduce the complexity. Algorithm. Create an array A and keep all the next pointers of the first list in the array. Sort these array elements. Then, for each of the second list elements, search in the sorted array. Let us assume that we are using binary search, which gives O. Since we are scanning the second list one by one, the first repeating element that appears in the array is nothing but the merging point. Time complexity. Time for sorting plus time for searching equal to O. Space complexity. O. Problem -23. Can we improve the complexity for problem 17? Solution, yes. Efficient approach. Find lengths of both lists. O plus O equal to O. Take the difference D of the lengths O. Make D steps in longer lists. O. Step in both lists in parallel until links to next node match. O. Total time complexity equal to O. Space complexity equal to O. Struct list node find intersecting node else. List head equal to list diff equal to L2, L1. Head list head equal to list diff L1, L2 for heddle heddle. Next, while if equal to head, return heddle, data, head heddle, next, head next, return null. Problem -24. How will you find the middle of the linked list? Solution, brute force approach for each of the nodes. Count how many nodes are there in the, and see whether it is the middle node of the list. List. Time complexity, O. Space complexity, O. Problem -25. Can we improve the complexity of problem 24? Solution, yes. Algorithm, traverse the list and find the length of the list. After finding the length, again scan the list and locate n/2 node from the beginning. Time complexity, time for finding the length of the list plus time for locating middle node equal to O plus O, approximately equal to O. Space complexity, O. Problem -26. Can we use the hash table for solving problem 24? Solution, yes. The reasoning is the same as that of problem 3. Time complexity, time for creating the hash table. Therefore, T equal to O. Space complexity, O. Since we need to create a hash table of size n. Problem 27, can we solve problem 24 just in one scan? Solution, efficient approach, use 2 pointers. Move one pointer at twice the speed of the second. When the first pointer reaches the end of the list, the second pointer will be pointing to the middle node. Note, if the list has an even number of nodes, the middle node will be of struct list node find middle, struct list node ptrix, ptr prix equal to ptr equal to head, int I equal to 0. Keep looping until we reach the tail while if equal to ptrix ptr lx next. Increment only the first pointer I equal to 1, else if equal to ptrix ptr lx next. Increment both pointers PTR equal to PTR, I equal to 0, 1 return PTR. Now return the PTR, which points to the middle node. Time complexity, O. Space complexity, O. Problem 28. How will you display a linked list from the end? Solution. Traverse recursively till the end of the linked list. While coming back, start printing the elements. This function will print the linked list from end void print list from end if return print list from end print ef. Time complexity O. Space complexity O for stack. Problem minus 29. Check whether the given linked list length is even or odd. Solution. Use a 2 times pointer. Take a pointer that moves it 2 times. At the end, if the length is even, then the pointer will be null, otherwise it will point to the last node. Time complexity O approximately equal to O. Space complexity O. Problem 30. If the head of a linked list is pointing to kth element, then how will you get the elements before kth element? Solution. Use memory-efficient linked lists. Given 2 sorted linked lists, how to merge them into the third list in sorted problem 31 order? Solution. Assume the sizes of lists are m and n. Recursive. Time complexity O, where n and m are lengths of 2 lists. Iterative. Time complexity O, where n and m are lengths of 2 lists. Problem 32. Reverse the linked list in pairs. If you have a linked list that holds 1, 2, 3, 4x, then after the function has been called, the linked list would hold 2, 1, 4, 3, 10 solution, recursive, struct list node reverse pair recursive, struct list node temp, if else return, base case for empty or 1 element list, reverse first pair temp equal to head next, temp next equal to head equal to temp. Call the method recursively for the rest of the list, head next reverse pair recursive, return head. Iterative. Struct list node reverse pair iterative. Struct list node temp equal to null, temp null. Current equal to head, while if temple next, current next. Temple equal to current. Next, current next, temple dot next equal to current. If temp equal to temp current. Next, return temp. Time complexity, O. Space complexity, O. Problem 33. Given a binary tree, convert it to doubly linked list. Solution. Refer trees chapter. Problem 34. How do we sort the linked lists? Solution. Refer sorting chapter. Problem 35. Split a circular linked list into 2 equal parts. If the number of nodes in the list are odd, then make first list 1 node extra than second list. Solution. Algorithm. Store the mid and last pointers of the circular linked list using Floyd cycle finding algorithm. Make the second half circular. Make the first half circular. Set head pointers of the 2 linked lists. As an example, consider the following circular list. After the split, the above list will look like time complexity, O. Space complexity, O. Problem 36. If we want to concatenate 2 linked lists, which of the following gives O complexity? 1. Singly linked lists. 2. Doubly linked lists. 3. Circular doubly linked lists. Solution. Circular doubly linked lists. This is because for singly and doubly linked lists, we need to traverse the first list till the end and append the second list. But in the case of circular, doubly linked lists, we don't have to traverse the lists. Problem 37. How will you check if the linked list is palindrome or not? Solution. B. Else return. Algorithm. 1. Get the middle of the linked list. 2. Reverse the second half of the linked list. 3. Compare the first half and second half. 4. Construct the original linked list by reversing the second half again and attaching it back to the first half. Time complexity. O. Space complexity. O. Problem 38. For a given k value, reverse blocks of k nodes in a list. Example. Input 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Output for different k values for k equal to 2, 2, 14, 36, 58, 710, 9. For k equal to 3, 3, 2, 1, 6, 5, 4, 9, 8, 7, 10. For k equal to 4, 4, 3, 2, 1, 8, 7, 6, 5, 9, 10. Solution. Algorithm. This is an extension of swapping nodes in a linked list. 1. Check if remaining list has k nodes. If yes, get the pointer of k plus first node. A. Reverse first k nodes. 2. Set next of last node to k plus first node. 3. 4. Move to k plus first node. 5. Go to step 1. K. First node of first k nodes becomes the new head if available. Otherwise, we can return the head. 6. Struct list node get k plus 1th node. Struct list node kth int I equal to 0 if return head. For I++ kth equal to kth. Next, if return kth, return head. Next, int has nodes int I equal to 0 for I++ head. Next, if return 1, return 0. Struct list node reverse block of k, node is in linked list. Struct list node cur equal to head. Temp. Next, new head int I if return head. If else new head get k plus 1th node, new head, while temp equal to get k plus 1th node, I equal to 0. While next equal to cur. Next, cur next temp, temp equal to cur equal to next, I++, return new head. Problem 39, is it possible to get O access time for linked lists? Solution, yes. Create a linked list and at the same time keep it in a hash table. For n elements, we have to keep all the elements in a hash table, which gives a preprocessing time of O. Read any element, we require only constant time O, and to read n elements, we require n one unit of time equal to n units. Hence, by using amortized analysis, we can say that element access can be performed within O time. Time complexity. O space complexity. O for hash table. Problem 40, Josephus circle. N people have decided to elect a leader by arranging themselves in a circle and eliminating every MPH person around the circle, closing ranks as each person drops out. Find which person will be the last one remaining. Solution. Assume the input is a circular linked list with n nodes and each node has a number associated with it. The head node has number 1 as data. Problem 41, given a linked list consists of data, a next pointer, and also a random pointer which points to a random node of the list. Give an algorithm for cloning the list. Solution. We can use a hash table to associate newly created nodes with the instances of node in the given list. Algorithm. Scan the original list and for each node x, create a new node y with data of x, then store the pair in hash table using x as a key. Note that during this scan, set y, next and y, random to null, and we will fix them in the next scan. Now for each node x in the original list, we have a copy y stored in our hash table. We scan the original list again and set the pointers building the new list. Time complexity. O. Space complexity. O. Problem 42. Can we solve problem 41 without any extra space? Solution. Yes. Time complexity. O approximately equal to. Space complexity. O. Problem 43. We are given a pointer to a node in a singly linked list. Delete that node from the linked list. Solution. To delete a node, we have to adjust the next pointer of the previous node to point to the next node instead of the current one. Since we don't have a pointer to the previous node, we can't redirect its next pointer. So what do? We can easily get away by moving the data from the next node into the current node and then deleting the next node. Time complexity. O. Space complexity. O. Problem 44. Given a linked list with even and odd numbers, create an algorithm for making changes to the list in such a way that all even numbers appear at the beginning. Solution. To solve this problem, we can use the splitting logic. While traversing the list, split the linked list into two. One contains all even nodes and the other contains all odd nodes. Now, to get the final list, we can simply append the odd node linked list after the even node linked list. To split the linked list, traverse the original linked list and move all odd nodes to a separate linked list of all odd nodes. At the end of the loop, the original list will have all the even nodes and the odd node list will have all the odd nodes. To keep the ordering of all nodes the same, we must insert all the odd nodes at the end of the odd node list. Time complexity. O. Space complexity. O. Problem 45 in a linked list with n nodes. The time taken to insert an element after an element pointed by some pointer is 0000. Solution. A. Problem 46. Find modular node given a singly linked list. Write a function to find the last element from the beginning whose m% equal to 0, where n is the number of elements in the list and k is an integer constant. For example, if n equal to 19 and k equal to 3, then we should return 18th node. Solution. For this problem, the value of n is not known in advance. Time complexity. O. Space complexity. O. Problem 47, find modular node from the end, given a singly linked list. Write a function to find the first from the end whose m% equal to 0, where n is the number of elements in the list and k is an integer constant. If n equal to 19 and k equal to 3, then we should return 16th node. Solution. For this problem, the value of n is not known in advance, and it is the same as finding the kth element from the end of the linked list. Time complexity. O. Space complexity. O. Problem 48. Find fractional node. Given a singly linked list, write a function to find the element, where n is the number of elements in the list. Solution. For this problem, the value of n is not known in advance. Time complexity. O. Space complexity. O. Problem 49. Find node. Given a singly linked list, write a function to find the element, where n is the number of elements in the list. Assume the value of n is not known in advance. Solution. For this problem, the value of n is not known in advance. Time complexity. O. Space complexity. O. Problem 50, given two lists, list 1 equal to with data in ascending order. Merge them into the third list in ascending order so that the merged list will be. Solution. Time complexity. The while loop takes O, time as it will run for min times. The other steps run in O. Therefore, the total time complexity is O. Space complexity. O. Problem 51, median in an infinite series of integers. Solution. Median is the middle number in a sorted list of numbers. If we have an even number of elements, the median is the average of two middle numbers in a sorted list of numbers. We can solve this problem with linked lists. First, let us try with an unsorted linked list. In an unsorted linked list, we can insert the element either at the head or at the tail. The disadvantage with this approach is that finding the median takes O. Also, the insertion operation takes O. Now, let us try with a sorted linked list. We can find the median in O time if we keep track of the middle elements. Insertion to a particular location is also O in any linked list. But finding the right location to insert is not O as in a sorted array. It is instead O because we can't perform binary search in a linked list even if it is sorted. So, using a sorted linked list isn't worth the effort as insertion is O and finding median is O, the same as the sorted array. In the sorted array, the insertion is linear due to shifting, but here it's linear because we can't do a binary search in a linked list. Note, for an efficient algorithm, refer to the priority queues in Heaps chapter. Problem 52, given a linked list. How do you modify it such that all the even numbers appear before all the odd numbers in the modified linked list? Solution. Struct list node exchange even odd list. First even node even list n equal to ITR. Else 1 if odd list equal to null. First odd node odd list end equal to ITR. Else inserting the node at the end of linked list odd list end next equal to ITR odd list end equal to ITR. ITR iter. Next even list end next equal to odd list return head. Time complexity O. Space complexity O. Problem 53. Given two linked lists, each list node with one integer digit, add these two linked lists. The result should be stored in the third linked list. Also note that the head node contains the most significant digit of the number. Solution. Since the integer addition starts from the least significant digit, we first need to visit the last node of both lists and add them up. Create a new node to store the result, take care of the carry if any, and link the resulting node to the node which will be added to the second least significant node and continue. First of all, we need to take into account the difference in the number of digits in the two numbers. So before starting recursion, we need to do some calculation and move the longer list pointer to the appropriate place so that we need the last node of both lists at the same time. The other thing we need to take care of is carry. If two digits add up to more than 10, we need to forward the carry to the next node and add it. If the most significant digit addition results in a carry, we need to create an extra node to store the carry. The function below is actually a wrapper function which does all the housekeeping like calculating lengths of lists, calling recursive implementation, creating an extra node for the carry in the most significant digit, and adding any remaining nodes left in the longer list. Void addless numbers wrapper. Int list 1 length 0 list equal to 0 diff 0 struct list node current while current list while diff abs current list while current. Next, addless numbers, diff abs, add remaining numbers, if return, addless numbers, end of both lists, add them struct list node temp equal to malloc, sum equal to list data plus, store carry sum, 10, sum equal to sum %10, temp data sum, temp next, result equal to temp, return, void add remaining numbers, int sum equal to 0, if return, add remaining numbers, struct list node temp equal to malloc, sum, list data plus, carry sum, 10, sum %10, temp data sum equal to temp next, result equal to temp. Return. Time complexity, O. Space complexity, O for recursive stack. Note, it can also be solved using stacks. Problem 54, which sorting algorithm is easily adaptable to singly linked lists? Solution. Simple insertion sort is easily adaptable to singly linked lists. To insert an element, the linked list is traversed until the proper position is found, or until the end of the list is reached. It is inserted into the list by merely adjusting the pointers without shifting any elements, unlike in the array. This reduces the time required for insertion, but not the time required for searching for the proper position. Problem 55. Given a list equal to without using any extra space. Solution. Find the middle of the linked list. We can do it by slow and fast pointer approach. After finding the middle node, we reverse the right halfle, then we do a in-place merge of the two halves of the linked list. Problem 56. Given two sorted linked lists, given an algorithm for the printing common elements of them. Solution. The solution is based on merge sort logic. Assume the given two linked lists are list and list. Since the elements are in sorted order, we run a loop till we reach the end of either of the list. We compare the values of list and list. If the values are equal, we add it to the common list. We move list nodes ahead to the next pointer if the values pointed by list was less more, equal to the value pointed by list. Time complexity O, where m is the length of list and n is the length of list. Space complexity O, struct list node common element, struct list node temp malloc, struct list node head equal to temp, while equal to if head next new list node, copy common element. List listle next, list equal to list next, head next, else if list else, list data list next, 4.11 return temp out next. 4.1. What is a stack? A stack is a simple data structure used for storing data. In a stack, the order in which the data arrives is important. A pile of plates in a cafeteria is a good example of a stack. The plates are added to the stack as they are cleaned, and they're placed on the top. When a plate is required is taken from the top of the stack. The first plate placed on the stack is the last one to be used. Definition. A stack is an ordered list in which insertion and deletion are done at one end, called top. The last element inserted is the first one to be deleted. Hence, it is called the last in first out or first in last out list. Special names are given to the two changes that can be made to a stack. When an element is inserted in a stack, the concept is called push, and when an element is removed from the stack, the concept is called pop. Trying to pop out an empty stack is called underflow, and trying to push an element in a full stack is called overflow. Generally, we treat them as exceptions. As an example, consider the snapshots of the stack. 4.2 How stacks are used. Consider a working day in the office. Let us assume a developer is working on a long-term project. The manager then gives the developer a new task which is more important. The developer puts the long-term project aside and begins work on the new task. The phone rings, and this is the highest priority as it must be answered immediately. The developer pushes the present task into the pending tray and answers the phone. When the call is complete, the task that was abandoned to answer the phone is retrieved from the pending tray and work progresses. To take another call, it may have to be handled in the same manner, but eventually the new task will be finished, and the developer can draw the long-term project from the pending tray and continue with that. 4.3 Stack ADT. The following operations make a stack in ADT. For simplicity, assume the data is an integer type. Main stack operations. Push inserts data onto stack. int pop removes and returns the last inserted element from the stack. Auxiliary stack operations. int top returns the last inserted element without removing it. nt size returns the number of elements stored in the stack. int is empty stack indicates whether any elements are stored in the stack or not. int is full stack indicates whether the stack is full or not. Exceptions. Attempting the execution of an operation may sometimes cause an error condition called an exception. Exceptions are said to be thrown by an operation that cannot be executed. In the stack ADT, operations pop and top cannot be performed if the stack is empty. Attempting the execution of pop on an empty stack throws an exception. Trying to push an element in a full stack throws an exception. 4.4 Applications. Following are some of the applications in which stacks play an important role. Direct applications. Balancing of symbols. Infix to postfix conversion, evaluation of postfix expression, implementing function calls, finding of spans, page visited history in a web browser, undo sequence in a text editor, matching tags in HTML XML, indirect applications, auxiliary data structure for other algorithms, component of other data structures. 4.5% implementation. There are many ways of implementing stack ADT. Below are the commonly used methods. Simple array-based implementation, dynamic array-based implementation, linked list implementation, simple array implementation. This implementation of stack ADT uses an array. In the array, we add elements from left to right and use a variable to keep track of the index of the top element. The array storing the stack elements may become full. A push operation will then throw a full stack exception. Similarly, if we try deleting an element from an empty stack, it will throw stack empty exception. Hashtag define max size 10 struct array stack. If the condition is true, then 1 is returned, else 0 is returned, return, void push. Performance and limitations. Performance. Let n be the number of elements in the stack. The complexities of stack operations with this representation can be given as limitations. The maximum size of the stack must first be defined and it cannot be changed. Trying to push a new element into a full stack causes an implementation-specific exception, dynamic array implementation. First, let's consider how we implemented a simple array-based stack. We took one index variable top which points to the index of the most recently inserted element in the stack. To insert an element, we increment top index and then place the new element at that index. Similarly, to delete an element, we take the element at top index and then decrement the top index. We represent an empty queue with top value equal to 1. The issue that still needs to be resolved is what we do when all the slots in the fixed size array stack are occupied. First try, what if we increment the size of the array by 1 every time the stack is full? Push, increase size of S by 1. Pop, decrease size of S by 1. Problems with this approach? This way of incrementing the array size is too expensive. Let us see the reason for this. For example, at n equal to 1, to push an element, create a new array of size 2 and copy all the old array elements to the new array, and at the end, add the new element. At n equal to 2, to push an element, create a new array of size 3 and copy all the old array elements to the new array, and at the end, add the new element. Similarly, at n equal to n1, if we want to push an element, create a new array of size n and copy all the old array elements to the new array, and at the end, add the new element. After n push operations, the total time t is proportional to 1 plus 2 plus n approximately equal to O. Alternative approach, repeated doubling. Let us improve the complexity by using the array doubling technique. If the array is full, create a new array of twice the size and copy the items. With this approach, pushing n items takes time proportional to n. For simplicity, let us assume that initially we started with n equal to 1 and moved up to n equal to 32. That means we do the doubling at 124,816. The other way of analyzing the same approach is at n equal to 1. If we want to add an element, double the current size of the array and copy all the elements of the old array to the new array. At n equal to 1, we do one copy operation. At n equal to 2, we do two copy operations. And at n equal to 4, we do four copy operations, and so on. By the time we reach n equal to 32, the total number of copy operations is 1 plus 2 plus 4 plus 8 plus 16 equal to 31, which is approximately equal to 2n value. If we observe carefully, we are doing the doubling operation ln times. Now, let us generalize the discussion. For n push operations, we double the array size ln times. That means we will have ln terms in the expression below. The total time t of a series of n push operations is proportional to t is O, and the amortized time of a push operation is O. Struct dyn array stack, b1 int top, int capacity, ent array, struct dyn array stack create stack, struct dyn array stack s equal to malloc if return null, s capacity equal to 1, s top equal to -1, s array malloc. Allocate an array of size 1 initially if return null, return s int is full stack, s capacity equal to 2, s array realloc, void push if return int min, return s array int pop if return int min, return s array, void delete stack if free. Performance. Let n be the number of elements in the stack. The complexities for operations with this representation can be given as linked list implementation, the other way of implementing. Stacks is by using linked lists. Push operation is implemented by inserting element at the beginning of the list. Pop operation is implemented by deleting the node from the beginning. Struct list node. 111 int data, struct list node next, struct stack create stack, return null, void push, struct stack temp malloc if return null, temp data equal to data, temp next equal to top equal to temp, int is empty stack, return top equal to null, int pop, int data, struct stack temp if return int min, temp equal to top next, data equal to temp data, free, return data, int top if return int min, return top next data, void delete stack, struct stack temp, p equal to top, while temp equal to p next temp, next, free. Performance. Let n be the number of elements in the stack. The complexities for operations with this representation can be given as 4.6% comparison of implementations. Comparing incremental strategy and doubling strategy. We compare the incremental strategy and doubling strategy by analyzing the total time t needed to perform a series of n push operations. We start with an empty stack represented by an array of size 1. We call amortized time of a push operation is the average time taken by a push over the series of operations, that is, Tn. Incremental strategy. The amortized time of a push operation is O, doubling strategy. In this method, the amortized time of a push operation is O. Note, for analysis, refer to the implementation section. Comparing array implementation and linked list implementation. Array implementation. Operations take constant time. Expensive doubling operation every once in a while. Any sequence of n operations, amortized bound takes time proportional to n. Linked list implementation grows and shrinks gracefully. Every operation takes constant time O. Every operation uses extra space and time to deal with references. 4.7 Stacks, Problems and Solutions. Problem 1, discuss how stacks can be used for checking balancing of symbols. Solution, stacks can be used to check whether the given expression has balanced symbols. This algorithm is very useful in compilers. Each time the parser reads one character at a time. If the character is an opening delimiter, such as the stack is popped, the opening and closing delimiters are then compared. If they match, the parsing of the string continues. If they do not match, the parser indicates that there is an error on the line. A linear time O algorithm based on stack can be given as algorithm A, create a stack, B, while 1, if the character read is not a symbol to be balanced, ignore it. 2, if the character is an opening symbol like, push it onto the stack. A closing symbol like, then if the stack is empty, report an error, otherwise pop the stack. 4, if the symbol popped is not the corresponding opening symbol, report an error. C, at end of input, if the stack is not empty, report an error. Examples. For tracing the algorithm, let us assume that the input is time complexity, O. since we are scanning the input only once. Space complexity O. Problem 2, discuss infix to postfix conversion algorithm using stack. Solution, before discussing the algorithm, first let us see the definitions of infix, prefix, and postfix expressions. Infix, an infix expression is a single letter or an operator preceded by one infix string and followed by another infix string. Prefix, a prefix expression is a single letter or an operator followed by two prefix strings. Every prefix string longer than a single variable contains an operator, first operand and second operand. Postfix, a postfix expression is a single letter or an operator preceded by two postfix strings. Every postfix string longer than a single variable contains first and second operands followed by an operator. Prefix and postfix notions are methods of writing mathematical expressions without parenthesis. Time to evaluate a postfix and prefix expression is O, where n is the number of elements in the array, unless we use parentheses. Therefore, for the infix to postfix conversion algorithm, we have to define the operator precedence inside the algorithm. The table shows the precedence and their associativity among operators. Important properties. Let us consider the infix expression 2 plus 3 times 4 and its postfix equivalent 234 plus. Notice that between infix and postfix, the order of the numbers is unchanged. It is 2, 3, 4 in both cases. But the order of the operators and plus is affected in the two expressions. Only one stack is enough to convert an infix expression to postfix expression. The stack that we use in the algorithm will be used to change the order of operators from infix to postfix. The stack we use will only contain operators and the open parentheses symbol. Postfix expressions do not contain parentheses. We shall not output the parentheses in the postfix output. Algorithm. A. Create a stack. B. For each character T in the input stream. C. Pop and output tokens until the stack is empty. For better understanding, let us trace out an example, a B minus plus E. Problem 3, discuss postfix evaluation using stacks. Solution. Algorithm. 1. Scan the postfix string from left to right. 2. Initialize an empty stack. 3. Repeat steps 4 and 5 till all the characters are scanned. 4. If the scanned character is an operand, push it onto the stack. 5. If the scanned character is an operator, and if the operator is a unary operator, then pop an element from the stack. If the operator is a binary operator, then pop 2 elements from the stack. After popping the elements, apply the operator to those popped elements. Let the result of this operation be retvol onto the stack. 6. After all characters are scanned, we will have only one element in the stack. Return top of the stack as result. Example, let us see how the above-mentioned algorithm works using an example. Assume that the postfix string is 123 plus 5L. Initially, the stack is empty. Now, the first 3 characters scanned are 1, 2, and 3, which are operands. They will be pushed into the stack in that order. The next character scanned which is an operator. Thus, we pop the top 2 elements from the stack and perform the operation with the 2 operands. The second operand will be the first element that is popped. The value of the expression that has been evaluated is pushed into the stack. The next character scanned is plus, which is an operator. Thus, we pop the top 2 elements from the stack and perform the plus operation with the 2 operands. The second operand will be the first element that is popped. The value of the expression that has been evaluated is pushed into the stack. The next character scanned is 5, which is added to the stack. The next character scanned which is an operator. Thus, we pop the top 2 elements from the stack and perform the operation with the 2 operands. The second operand will be the first element that is popped. The value of the expression that has been evaluated is pushed into the stack. Now, since all the characters are scanned, the remaining element in the stack will be returned. End result, postfix string, 123 plus 5, result, 2. Problem 4. Can we evaluate the infix expression with stacks in one pass? Solution. Using 2 stacks, we can evaluate an infix expression in one pass without converting to postfix. Algorithm. 1. Create an empty operator stack. 2. Create an empty operand stack. 3. For each token in the input string. A. Get the next token in the infix string. B. If next token is an operand, place it on the operand stack. C. If next token is an operator. I. Evaluate the operator. 4. While operator stack is not empty, pop operator and operands, evaluate left operator right, push result onto operand stack. 5. Pop result from operator stack. Problem 5. How to design a stack such that get minimum should be O. Solution. Take an auxiliary stack that maintains the minimum of all values in the stack. Also, assume that each element of the stack is less than its below elements. For simplicity, let us call the auxiliary stack min stack. When we pop the main stack, pop the min stack too. When we push the main stack, push either the new element or the current minimum, whichever is lower. At any point, if we want to get the minimum, then we just need to return the top element from the min stack. Let us take an example and trace it out. Initially, let us assume that we have pushed 2, 6, 4, 1, and 5. Based on the above-mentioned algorithm, the min stack will look like After popping twice, we get time complexity, O, space complexity, O. This algorithm has much better space usage if we rarely get a new minimum or equal. Problem 6 for problem 5, is it possible to improve the space complexity? Solution, yes. The main problem of the previous approach is for each push operation, we are pushing the element on to min stack also. That means we are pushing the duplicate minimum elements onto the stack. Now, let us change the algorithm to improve the space complexity. We still have the min stack, but we only pop from it when the value we pop from the main stack is equal to the one on the min stack. We only push to the min stack when the value being pushed onto the main stack is less than or equal to the current min value. In this modified algorithm also, if we want to get the minimum, then we just need to return the top element from the min stack. For example, taking the original version and pushing 1 again, we'd get popping from the above pops from both stacks because 1 equal to 1, leaving. Popping again only pops from the main stack because 5 greater than 1. Popping again pops both stacks because 1 equal to 1. Time complexity, O. Space complexity, O. But this algorithm has much better space usage if we rarely get a new minimum or equal. Problem 7, for a given array with n symbols, how many stack permutations are possible? Solution. The number of stack permutations with n symbols is represented by Catalan number, and we will discuss this in the dynamic programming chapter. Problem 8, given an array of characters formed with A's and B's. The string is marked with special character X, which represents the middle of the list. Check whether the string is palindrome. Solution. This is one of the simplest algorithms. What we do is start 2 indexes, one at the beginning of the string and the other at the end of the string. Each time compare whether the values at both the indexes are the same or not. If the values are not the same, then we say that the given string is not a palindrome. If the values are the same, then increment the left index and decrement the right index. Continue this process until both the indexes meet at the middle, or if the string is not palindrome. Time complexity, O. Space complexity, O. Problem 9 for problem 8. If the input is in singly linked list, then how do we check whether the list elements form a palindrome? Solution. Refer linked list chapter. Problem 10. Can we solve problem 8 using stacks? Solution. Yes. Algorithm. Traverse the list till we encounter X as input element. For the second half of the list, compare each element's content with top of the stack. During the traversal, push all the elements onto the stack. If they are the same, then pop the stack and go to the next element in the input list. If they are not the same, then the given string is not a palindrome. Continue this process until the stack is empty, or the string is not a palindrome. Time complexity, O. Space complexity, O. Approximately equal to O. Problem 11, given a stack, how to reverse the elements of the stack using only stack operations. Solution. Algorithm. First, pop all the elements of the stack till it becomes empty. For each upward step in recursion, insert the element at the bottom of the stack. Problem 14. How do we implement 2 stacks using only 1 array? Our stack routine should not indicate an exception unless every slot in the array is used. Time complexity, O. Space complexity, O, for recursive stack. Problem 12, show how to implement 1 queue efficiently using 2 stacks. Analyze the running time of the queue operations. Solution, refer queues chapter. Problem 13, show how to implement 1 stack efficiently using 2 queues. Analyze the running time of the stack operations. Solution, refer queues chapter. Algorithm. Start 2 indexes, one at the left end and the other at the right end. The left index simulates the first stack and the right index simulates the second stack. If we want to push an element into the first stack, then put the element at the left index. Similarly, if we want to push an element to the second stack, then put the element at the right index. The first stack grows towards the right, and the second stack grows towards the left. Time complexity of push and pop for both stacks is O. Space complexity is O. Problem 15, 3 stacks in 1 array. How to implement 3 stacks in 1 array. Solution, for this problem, there could be other ways of solving it. Given below is one possibility, and it works as long as there is an empty space in the array. To implement 3 stacks, we keep the following information. The index of the first stack, this indicates the size of the first stack. The index of the second stack, this indicates the size of the second stack. Starting index of the third stack, top index of the third stack. Now, let us define the push and pop operations for this implementation. Pushing. For pushing onto the first stack, we need to see if adding a new element causes it to move into the third stack. If so, try to shift the third stack upwards. Insert the new element at. For pushing to the second stack, we need to see if adding a new element causes it to bump into the third stack. If so, try to shift the third stack downward. When pushing to the third stack, see if it bumps into the second stack. If so, try to shift the third stack downward and try pushing again. Insert the new element at. Time complexity O, since we may need to adjust the third stack. Space complexity O. Popping for popping. We don't need to. Time complexity O. Space complexity. Oh, problem 16 for problem 15. Is there any other way implementing the middle stack? Solution, yes. When either the left stack or the right stack bumps into the middle stack, we need to shift the entire middle stack to make growth. The same happens if a push on the middle stack causes it to bump into the right stack. To solve the above-mentioned problem, what we can do is alternating pushes can be added at alternating sides of the middle list. This would keep the middle stack balanced in the center of the array, but it would still need to be shifted when it bumps into the left or right stack, whether by growing on its own or by the growth of a neighboring stack. We can optimize the initial locations of the three stacks if they grow shrink at different rates and if they have different average sizes. For example, suppose one stack doesn't change much. If we put it at the left, then the middle stack will eventually get pushed against it and leave a gap between the middle and right stacks, which grow toward each other. If they collide, then it's likely we've run out of space in the array. There is no change in the time complexity, but the average number of shifts will get reduced. Problem 17, multiple stacks in one array. Similar to problem 15, what if we want to implement m stacks in one array? Solution, let us assume that array indexes are from 1 to n, similar to the discussion. In problem to implement m stacks in one array, we divide the array into m parts. The size of each part is, from the above representation, we can see that first stack is starting at index 1, second stack is starting at index, third stack is starting at index, and so on. Similar to base array, let us assume that top array stores the top indexes for each of the stack. Consider the following terminology for the discussion. Top, for 1 less than or equal to I less than or equal to m, will point to the topmost element of the stack I. If base equal to top, then we can say the stack I is empty. If top equal to base, then we can say the stack I is full. For 1 less than or equal to I less than or equal to m, initially base equal to top equal to. The ith stack grows from base plus 1 to base. Pushing on to ith stack. 1. For pushing onto the ith stack, we check whether the top element stack is pointing to base. That means we need to see if adding a new element causes it to bump into the I plus first stack. If so, try to shift the stacks from I plus first stack to mth stack toward the right. Insert the new element at plus top. 2. If right shifting is not possible, then try shifting the stacks from 1 to I first stack toward the left. 3. If both of them are not possible, then we can say that all stacks are full. Time complexity, O, since we may need to adjust the stacks. Space complexity, O. Popping from I stack. For popping, we don't need to shift, just decrement the size of the appropriate stack. The only case to check is stack case. Time complexity, O. Space complexity, O. Problem 18, consider an empty stack of integers. Let the numbers 1, 2, 3, 4, 5, 6 be pushed onto this stack in the order they appear from left to right. Let 5 indicate a push and x indicate a pop operation. Can they be commuted in order 3, 2, 5, 6, 41 and order 1, 5, 4, 6, 40 order? 3, 6, 641 and order 1, 641, 125,641. We discussed that for dynamic array implementation of stacks, the repeated doubling approach is used. For the same problem, what is the complexity if we create a new array whose size is n plus if instead of doubling? Solution, let us assume that the initial stack size is 0. For simplicity, let us assume that k equal to 10. For inserting the element, we create a new array whose size is 0 plus 10 equal to 10. Similarly, after 10 elements, we again create a new array whose size is 10 plus 10 equal to 20, and this process continues at values 3040. That means for a given n value, we are creating the new arrays at the total number of copy operations is. If we are performing n push operations, the cost per operation is O. Problem 20, given a string containing n s's and n x's where 5 indicates a push operation and x indicates a pop operation, and with the stack initially empty, formulate a rule to check whether a given string 5% of operations is admissible or not. Solution, given a string of length 2n, we wish to check whether the given string of operations is permissible or not with respect to its functioning on a stack. The only restricted operations pop whose prior requirement is that the stack should not be empty. So while the the stack shouldn't be empty, which means the number of s's is always greater than or equal to that of x's. Hence, the condition is at any stage of processing of the string, the number of push operations should be greater than the number of pop operations. Problem 21. Suppose there are two singly linked lists which intersect at some point and become a single linked list. The head or start pointers of both the lists, but the intersection is not. Also, the number of nodes in each of the lists before they intersect, and both lists may have a different number. List may have n nodes before it reaches the intersection point, and list may have m nodes before it reaches the intersection point where m and n may be m equal to an mn or mn. Can we find the merging point using stacks? Solution, yes. For algorithm, refer to linked list chapter. Problem 22. Finding spans. Given an array A, the span S of A is the maximum number of consecutive elements A immediately preceding A and such that AA. Other way of asking, given an array A of integers, find the maximum of J. I subjected to the constraint of A. Solution: this is a very common problem in stock markets to find the peaks. Spans are used in financial. This is a very common problem in stock markets to find the peaks. Spans are used in financial analysis. The span of a stock price on a certain day, I, is the maximum number of consecutive days the price of the stock has been less than or equal to its price on I. As an example, let us consider the table in the corresponding spans diagram. In the figure, the arrows indicate the length of the spans. Now, let us concentrate on the algorithm for finding the spans. One simple way is each day, check how many contiguous days have a stock price that is less than the current price. Time complexity O, space complexity O. Problem 23. Can we improve the complexity of problem 22? Solution. From the example above, we can see that span S on day I can be easily calculated if we know the closest day preceding I, such that the price is greater on that day than the price on day I. Let us call such a day as P. If such a day exists, then the span is now defined as S equal to I, P. Time complexity. Each index of the array is pushed into the stack exactly once, and also popped from the stack at most once. The statements in the while loop are executed at most n times. Even though the algorithm has nested loops, the complexity is O, as the inner loop is executing only n times during the course of the algorithm. Space complexity O. Problem 24. Largest rectangle under histogram. A histogram is a polygon composed of a sequence of rectangles aligned at a common baseline. For simplicity, assume that the rectangles have equal widths but may have different heights. For example, the figure on the left shows a histogram that consists of rectangles with the heights 3, 2, 5, 6, 1, 4, 4, measured in units where 1 is the width of the rectangles. Here our problem is, given an array with heights of rectangles, we need to find the largest rectangle possible. For the given example, the largest rectangle is the shared part. Solution: a straightforward answer is to go to each bar in the histogram and find the maximum possible area in the histogram for it. Finally, find the maximum of these values. This will require, problem 25 for problem 24, can we improve the time complexity? Solution: linear search. Using a stack of incomplete subproblems, there are many ways of solving this problem. Judge is given a nice algorithm for this problem which is based on stack. Process the elements in left to right order and maintain a stack of information about started but yet unfinished sub-histograms. If the stack is empty, open a new subproblem by pushing the element onto the stack. Otherwise, compare it to the element on top of the stack. If the new one is greater, we again push it. If the new one is equal, we skip it. In all these cases, we continue with the next new element. If the new one is less, we finish the topmost subproblem by updating the maximum area with respect to the element at the top of the stack. Then, we discard the element at the top and repeat the procedure keeping the current new element. This way, all subproblems are finished when the stack becomes empty, or its top element is less than or equal to the new element, leading to the actions described above. If all elements have been processed and the stack is not yet empty, we finish the remaining subproblems by updating the maximum area with respect to the elements at the top. At the first impression, this solution seems to be having O complexity. But if we look carefully, every element is pushed and popped at most once, and in every step of the function, at least one element is pushed or popped. Since the amount of work for the decisions and the update is constant, the complexity of the algorithm is O by amortized analysis. Space complexity, O. Problem 26 on a given machine, how do you check whether the stack grows up or down? Solution, try noting down the address of a local variable. Call another function with a local variable declared in it and check the address of that local variable and compare. Time complexity, O. Space complexity, O. Problem 27. Given a stack of integers, how do you check whether each successive pair of numbers in the stack is consecutive or not? The pairs can be increasing or decreasing, and if the stack has an odd number of elements, the element at the top is left out of a pair. For example, if the stack of elements are, then the output should be true because each of the pairs, and consists of consecutive numbers. Solution. Refer to Q's chapter. Problem 28. Recursively remove all adjacent duplicates. Given a string of characters, recursively remove adjacent duplicate characters from string. The output string should not have any adjacent duplicates. Solution. This solution runs with the concept of in-place stack. When element on stack doesn't match the current character, we add it to stack. When it matches to stack top, we skip characters until the element matches the top of stack and remove the element from stack. Time complexity, O. Space complexity, O, as the stack simulation is done in place. Problem 29. Given an array of elements, replace every element with nearest greater element on the right of that element. Solution. One simple approach would involve scanning the array elements, and for each of the elements, scan the remaining elements and find the nearest greater element. Time complexity, O. Space complexity, O. Problem 30 for problem 29. can we improve the complexity? Solution. The approach is pretty much similar to problem 22. Create a stack and push the first element. For the rest of the elements, mark the current element as next nearest greater. If stack is not empty, then pop an element from stack and compare it with next nearest greater. If next nearest greater is greater than the popped element, then next nearest greater is the next greater element for the popped element. Keep. If next nearest greater is greater than the popped element, then next nearest greater is the next greater element for the popped element. Keep popping from the stack while the popped element is smaller than next nearest greater. Next nearest greater becomes the next greater element for all such popped elements. If next nearest greater is smaller than the popped element, then push the popped element back. Problem 31, how to implement a stack which will support following operations in O time complexity, O space complexity, O, push which adds an element to the top of stack. Pop, which removes an element from top of stack. Find middle, which will return middle element of the stack. Delete middle, which will delete the middle element. Solution, we can use a linked list data structure with an extra pointer to the middle element. Also, we need another variable to store whether the linked list has an even or odd number of elements. Push. Add the element to the head of the linked list. Update the pointer to the middle element according to variable. Pop. Remove the head of the linked list. Update the pointer to the middle element according to variable. Find middle, which will return middle element of the stack. Delete middle, which will delete the middle element. Use the logic of problem 43 from linked lists chapter. 5.1. What is a queue? A queue is a data structure used for storing data. In queue, the order in which data arrives is important. In general, a queue is a line of people or things waiting to be served in sequential order, starting at the beginning of the line or sequence. Definition. A queue is an ordered list in which insertions are done at one end and deletions are done at other end. The first element to be inserted is the first one to be deleted. Hence, it is called first in first out or last in last out list. Similar to stacks, special names are given to the two changes that can be made to a queue. When an element is inserted in a queue, the concept is called onQueue, and when an element is removed from the queue, the concept is called dequeue. Dequeuing an empty queue is called underflow, and enqueuing an element in a full queue is called overflow. Generally, we treat them as exceptions. As an example, consider the snapshot of the queue. int is empty queue indicates whether no elements are stored in the queue or not. 5.2. How are queues used? The concept of a queue can be explained by observing a line at a reservation counter. When we enter the line, we stand at the end of the line, and the person who is at the front of the line is the one who will be served next. He will exit the queue and be served. As this happens, the next person will come at the head of the line, will exit the queue, and will be served. As each person at the head of the line keeps exiting the queue, we move towards the head of the line. Finally, we will reach the head of the line, and we will exit the queue and be served. This behavior is very useful in cases where there is a need to maintain the order of arrival. 5.3 QADT. The following operations make a queue in ADT. Insertions and deletions in the queue must follow the FIFO scheme. For simplicity, we assume the elements are integers. Main queue operations. onQueue inserts an element at the end of the queue. Int dequeue removes and returns the element at the front of the queue. Auxiliary queue operations. Int front returns the element at the front without removing it. In queue size returns the number of elements stored in the queue. 5.4 exceptions. Similar to other ADTs, executing dequeue on an empty queue throws an empty queue exception, and executing enqueue on a full queue throws full queue exception. 5.5 applications. Following are some of the applications that use queues. Direct applications. Operating systems schedule jobs in the order of arrival. Multiprogramming. Asynchronous data transfer. Determining number of cashiers to have at a supermarket. Simulation of real-world queues, such as lines at a ticket counter or any other first-come, first-served scenario, requires a queue. Waiting times of customers at call center, indirect applications, auxiliary data structure for algorithms, component of other data structures. 5.6% implementation. There are many ways of implementing queue operations, and some of the commonly used methods are listed below. Simple circular array-based implementation. Dynamic circular array-based implementation. Linked list implementation. Why circular arrays? First, let us see whether we can use simple arrays for implementing queues as we have done for stacks. We know that, in queues, the insertions are performed at one end and deletions are performed at the other end. After performing some insertions and deletions, the process becomes easy to understand. In the example shown below, it can be seen clearly that the initial slots of the array are getting wasted, so simple array implementation for queue is not efficient. To solve this problem, we assume the arrays as circular arrays. That means we treat the last element and the first array elements as contiguous. With this representation, if there are any free slots at the beginning, the rear pointer can easily go to its next free slot. Note, the simple circular array and dynamic circular array implementations are very similar to stack array implementations. Refer to Stack's chapter for analysis of these implementations. Simple circular array implementation. This simple implementation of QADT uses an array. In the array, we add elements circularly and use two variables to keep track of the start element and end element. Generally, front is used to indicate the start element and rear is used to indicate the end element in the queue. The array storing the queue elements may become full. An enqueue operation will then throw a full queue exception. Similarly, if we try deleting an element from an empty queue, it will throw empty queue exception. Note, initially, both front and rear points to -1, which indicates that the queue is empty. 1 struct array queue int dequeue. Int data equal to 0. Or element which does not exist in queue if else empty queue, return 0. Data queue array if queue front, queue rear equal to -1, else queue front % queue capacity, return data, void delete queue, if free, free. Performance and limitations. Performance, let n be the number of elements in the queue. Limitations, the maximum size of the queue must be defined as prior and cannot be changed. Trying to enqueue a new element into a full queue causes an implementation-specific exception. Dynamic circular array implementation. Struct dinArray queue return null. Queue capacity e queue front rear equal to -1. Array malacto capacity size offend. Array return null. Return queue int is empty queue. IP array. Print memory error. Return iq front queue rear. In queue if queue array free. Array free 3. Performance. Let n be the number of elements in the queue. Linked list implementation. Another way of implementing queues is by using linked lists. Enqueue operation is implemented by inserting an element at the end of the list. Dequeue operation is implemented by deleting an element from the beginning of the list. Struct queue, create queue, queue front, queue rear, int dequeue temp equal to queue front, equal to data, queue front, next. Free temp, return data, void delete queue free. Performance. Let n be the number of elements in the queue then. Comparison of implementations. Note, comparison is very similar to stack implementations and Stack's chapter. 5.7 queues, problems and solutions. Problem -1 give an algorithm for reversing a queue. To access the queue, we are only allowed to use the methods of QADT. Solution. Time complexity, O. Problem 2. How can you implement a queue using two stacks? Solution. Let psi and S2 be the two stacks to be used in the implementation of queue. All we have to do is to define the onQueue and dequeue operations for the queue. And queue algorithm. Just push on to stack S1. Time complexity, O, dequeue algorithm. If stack S2 is not empty, then pop from S2 and return that element. If stack is empty, then transfer all elements from psi to S2 and pop the top element from S2 and return that popped element. If stack S1 is also empty, then throw error. Time complexity from the algorithm. If the stack S2 is not empty, then the complexity is O. If the stack S2 is empty, then we need to transfer the elements from Si to S2. But if we carefully observe, the number of transferred elements and the number of popped elements from S2 are equal. Due to this, the average complexity of pop operation in this case is O. Amortized complexity of pop operation is O. Problem 3 show how you can efficiently implement one stack using two queues. Analyze the running time of the stack operations. Solution, yes, it is possible to implement the stack ADT using two implementations of the queue ADT. One of the queues will be used to store the elements and the other to hold them temporarily during the pop and top methods. The push method would enqueue the given element onto the storage queue. The top method would transfer all but the last element from the storage queue onto the temporary queue, save the front element of the storage queue to be returned, transfer the last element to the temporary queue, then transfer all elements back to the storage queue. The pop method would do the same as top, except instead of transferring the last element onto the temporary queue after saving it for return, that last element would be discarded. Let first quarter and second quarter be the two queues to be used in the implementation of stack. All we have to do is to define the push and pop operations for the stack. In the algorithms below, we make sure that one queue is always empty. Push operation algorithm, insert the element in whichever queue is not empty. Check whether queue first quarter is empty or not. If first quarter is empty, then enqueue the element to second quarter. Otherwise, on-queue the element into first quarter. Time complexity. pop operation algorithm. Transfer n1 elements to the other queue and delete last from queue for performing pop operation. If queue first quarter is not empty, then transfer n1 elements from first quarter to second quarter, and then dequeue the last element of first quarter and return it. If queue second quarter is not empty, then transfer n1 elements from second quarter to first quarter, and then dequeue the last element of second quarter and return it. Time complexity. Running time of pop operation is O, as each time pop is called, we are transferring all the elements from one queue to the other. Problem 4. Maximum sum in sliding window given array A, with sliding window of size W, which is moving from the very left of the array to the very right. Assume that we can only see the W numbers in the window. Each time the sliding window moves rightwards by one position. For example, the array is, and W is 3. Input, along array A, and a window width W. Output, an array B. B is the maximum value from A to A. Requirement, find a good optimal way to get B. Solution, this problem can be solved with doubly ended queue. Refer priority queues chapter for algorithms. Problem 5, given a queue containing n elements, transfer these items onto a stack S so that front element of queue appears at the top of the stack and the order of all other items is preserved. Using enqueue and dequeue operations for the queue and push and pop operations for the stack, outline an efficient O algorithm to accomplish the above task using only a constant amount of additional storage. Solution, assume the elements of QQ are A, N. Dequeuing all elements and pushing them onto the stack will result in a stack with an at the top and A at the bottom. This is done in no time as dequeue, and each push requires constant time per operation. The queue is now empty. By popping all elements and pushing them on the queue, we will get A at the top of the stack. This is done again in O time. As in big O arithmetic, we can ignore constant factors. The process is carried out in O time. The amount of additional storage needed here has to be big enough to temporarily hold one item. Problem 6, a queue is set up in a circular array A with front and rear defined as usual. Assume that n1 locations in the array are available for storing the elements. Give a formula for the number of elements in the queue in terms of rear, front, and n. Solution, consider the following figure to get a clear idea of the queue. Rear of the queue is somewhere clockwise from the front. To enqueue an element, we move rear 1 position clockwise and write the element in that position. To dequeue, we simply move front 1 position clockwise. Queue migrates in a clockwise direction as we enqueue and dequeue. Emptiness and fullness to be checked carefully. Analyze the possible situations. We will get this. What is the most appropriate data structure to print elements of queue in reverse problem 7 order? Solution, stack. Problem 8, implement doubly ended queues. A double-ended queue is an abstract data structure that implements a queue for which elements can only be added to or removed from the front or back. It is also often called a head-tail linked list. Solution, void pushback deck struct list node new node equal to malloc, new node data equal to data, if head equal to new node, next head, prev equal to head, else, new node prev, new node, next equal to head, prev next equal to new node, prev new node, void push front deck, pushback deck, head prev, in popback dequeue, 1 into data, if prev head, data equal to data, free, head equal to null, else, struct list node new tail equal to prev, data, new tail next head, free prev, new tail, return data, int pop front, int data, head next, data popback dequeue, return data. Problem 9. Given a stack of integers, how do you check whether each successive pair of numbers in the stack is consecutive or not? The pairs can be increasing or decreasing, and if the stack has an odd number of elements, the element at the top is left out of a pair. For example, if the stack of elements are, then the output should be true because each of the pairs and consists of consecutive numbers. Solution. Time complexity O, space complexity O. Problem 10, given a queue of integers, rearrange the elements by interleaving the first half of the list with the second half of the list. For example, suppose a queue stores the following sequence of values. Consider the two halves of this list, first half, second half. These are combined in an alternating fashion to form a sequence of interleaved pairs, the first values from each half, then the second values from each half, then the third values from each half, and so on. In each pair, the value from the first half appears before the value from the second half. Thus, after the call, the queue stores the following values. Solution. Time complexity O, space complexity O. Problem 11. Given an integer k and a queue of integers, how do you reverse the order of the first k elements of the queue, leaving the other elements in the same relative order? For example, if k equal to 4 and q has the elements, the output should be. Solution. Void reverse a queue first k elements. Time complexity O, space complexity O. 6.1. What is a tree? A tree is a data structure similar to a linked list, but instead of each node pointing simply to the next node in a linear fashion, each node points to a number of nodes. Tree is an example of a nonlinear data structure. A tree structure is a way of representing the hierarchical nature of a structure in a graphical form. In trees ADT, the order of the elements is not important. If we need ordering information, linear data structures like linked lists, stacks, queues, etc. can be used. 6.2 Glossary. The root of a tree is the node with no parents. There can be at most one root node in a tree. An edge refers to the link from parent to child. A node with no children is called leaf node. Children of same parent are called siblings. A node P is an ancestor of node Q if there exists a path from root to Q and P appears on the path. The node Q is called a descendant of P. For example, A, C, and G are the ancestors of if. The set of all nodes at a given depth is called the level of the tree. The root node is at level 0. The depth of a node is the length of the path from the root to the node. The height of a node is the length of the path from that node to the deepest node. The height of a tree is the length of the path from the root to the deepest node in the tree. A tree with only one node has a height of 0. In the previous example, the height of B is 2. Height of the tree is the maximum height among all the nodes in the tree, and depth of the tree is the maximum depth among all the nodes in the tree. For a given tree, depth and height returns the same value. But for individual nodes, we may get different results. The size of a node is the number of descendants it has including itself. If every node in a tree has only one child, then we call such trees skew trees. If every node has only left child, then we call them left skew trees. Similarly, if every node has only right child, then we call them right skew trees. 6.3 Binary trees. A tree is called binary tree if each node has 0 child, 1 child, or 2 children. Empty tree is also a valid binary tree. We can visualize a binary tree as consisting of a root and 2 disjoint binary trees called the left and right subtrees of the root. Generic binary tree. 6.4 Types of binary trees. Strict binary tree. A binary tree is called strict binary tree if each node has exactly 2 children or no children. Full binary tree. A binary tree is called full binary tree if each node has exactly 2 children, and all leaf nodes are at the same level. Complete binary tree. Before defining the complete binary tree, let us assume that the height of the binary tree is h. In complete binary trees, if we give numbering for the nodes by starting at the root, then we get a complete sequence from 1 to the number of nodes in the tree. While traversing, we should give numbering for null pointers also. A binary tree is called complete binary tree if all leaf nodes are at height h or h, 1, and also without any missing number in the sequence. 6.5 Properties of binary trees. For the following properties, let us assume that the height of the tree is h. Also assume that root node is at height 0. From the diagram, we can infer the following properties. The number of nodes n in a full binary tree is 2 hours 1 to 1. Since there are h levels, we need to add all nodes at each level. The number of nodes n in a complete binary tree is between 2 hours and 2 hours 1 to 1. For more information on this, refer to Priority Queues chapter. The number of leaf nodes in a full binary tree is 2 hours. The number of null links in a complete binary tree of n nodes is n plus 1. Structure of binary trees. Now let us define structure of the binary tree. For simplicity, assume that the data of the nodes are integers. One way to represent a node is to have 2 links which point to left and right children along with data fields as shown below. Note, in trees, the default flow is from parent to children, and it is not mandatory to show directed branches. For our discussion, we assume both the representations shown below are the same. Operations on binary trees. Basic operations. Inserting an element into a tree. Deleting an element from a tree. Searching for an element. Traversing the tree. Auxiliary operations. Finding the size of the tree. Finding the height of the tree. Finding the level which has maximum sum. Finding the least common ancestor for a given pair of nodes, and many more. Applications of binary trees. Following are the sum of the applications where binary trees play an important role. Expression trees are used in compilers. Huffman coding trees that are used in data compression algorithms. Binary search tree, which supports search, insertion, and deletion on a collection of items in O. Priority queue, which supports search and deletion of minimum on a collection of items in logarithmic time. 6.6 Binary tree traversals. In order to process trees, we need a mechanism for traversing them, and that forms the subject of this section. The process of visiting all nodes of a tree is called tree traversal. Each node is processed only once, but it may be visited more than once. As we have already seen in linear data structures, the elements are visited in sequential order. But in tree structures, there are many different ways. Tree traversal is like searching the tree, except that in traversal, the goal is to move through the tree in a particular order. In addition, all nodes are processed in the traversal, but searching stops when the required node is found. Traversal possibilities. Starting at the root of a binary tree, there are 3 main steps that can be performed, and the order in which they are performed defines the traversal type. These steps are performing an action on the current node, traversing to the left child node, and traversing to the right child node. This process can be easily described through recursion. Based on the above definition, there are 6 possibilities. 1. LDR, process left subtree, process the current node data, and then process right subtree. 2. LRD, process left subtree, process right subtree, and then process the current node data. 3. DLR, process the current node data, process left subtree, and then process right subtree. 4. DRL, process the current node data, process right subtree, and then process left subtree. 5. RDL, process right subtree, process the current node data, and then process left subtree. 6. RLD, process right subtree, process left subtree, and then process the current node data. Classifying the traversals. The sequence in which these entities are processed defines a particular traversal method. The classification is based on the order in which current node is processed. That means if we are classifying based on current node, and if D comes in the middle, then it does not matter whether L is on left side of D or R is on left side of D. Similarly, it does not matter whether L is on right side of D or R is on right side of D. Due to this, the total 6 possibilities are reduced to 3, and these are pre-order traversal, in-order traversal, post-order traversal. There is another traversal method which does not depend on the above orders, and it is level order traversal. This method is inspired from breadth first traversal. Let us use the diagram below for the remaining discussion. Pre-order traversal. In pre-order traversal, each node is processed before either of its subtrees. This is the simplest traversal to understand. However, even though each node is processed before the subtrees, it still requires that some information must be maintained while moving down the tree. In the example above, one is processed first, then the left subtree, and this is followed by the right subtree. Therefore, processing must return to the right subtree after finishing the processing of the left subtree. To move to the right subtree after processing the left subtree, we must maintain the root. Information. The obvious ADT for such information is a stack. Because of its LIFO structure, it is possible to get the information about the right subtrees back in the reverse order. Pre-order traversal is defined as follows. Visit the root. Traverse the left subtree in pre-order. Traverse the right subtree in pre-order. The nodes of tree would be visited in the order 1, 2, 4, 5, 3, 6, 7. Time complexity O. Space complexity O. Non-recursive pre-order traversal. In the recursive version, a stack is required as we need to remember the current node so that after completing the left subtree, we can go to the right subtree. To simulate the same, first we process the current node, and before going to the left subtree, we store the current node on stack. After completing the left subtree processing, pop the element and go to its right subtree. Continue this process until stack is non-empty. Traverse the right subtree in order. Time complexity O. Space complexity O. In order traversal. In order traversal, the root is visited between the subtrees. In order traversal is defined as follows. Traverse the left subtree in order. Visit the root. In the order. Time complexity O. Space complexity O. Non-recursive in-order traversal. The non-recursive version of in-order traversal is similar to pre-order. The only change is, instead of processing the node before going to left subtree, process it after popping. Time complexity O. Space complexity O. Post-order traversal. In post-order traversal, the root is visited after both subtrees. Post-order traversal is defined as follows. Traverse the left subtree in post-order. Traverse the right subtree in post-order. Visit the root. The nodes of the tree would be visited in the order 4, 5, 2, 6, 7, 3, 1. Time complexity O. Space complexity O. Non-recursive post-order traversal. In pre-order and in-order traversals, after popping the stack element, we do not need to visit the same vertex again. But in post-order traversal, each node is visited twice. That means, after processing the left subtree, we will visit the current node, and after processing the right subtree, we will visit the same current node. But we should be processing the node during the second visit. Here, the problem is how to differentiate whether we are returning from the left subtree or the right subtree. We use a previous variable to keep track of the earlier traversed node. Let's assume current is the current node that is on top of the stack. When previous is current's parent, we are traversing down the tree. In this case, we try to traverse to current's left child if available. If it is not available, we look at current's right child. If both left and right child do not exist, we print current's value and pop it off the stack. If prev is current's left child, we are traversing up the tree from the left. We look at current's right child. If it is available, then traverse down the right child, otherwise print current's value and pop it off the stack. If previous is current's right child, we are traversing up the tree from the right. In this case, we print current's value and pop it off the stack. Time complexity O. Space complexity O. Level order traversal. Level order traversal is defined as follows. Visit the root. While traversing level, keep all the elements at level plus 1 in queue. Go to the next level and visit all the nodes at that level. Repeat this until all levels are completed. The nodes of the tree are visited in the order 1, 2, 3, 4, 5, 6, 7. Time complexity O. Space complexity O. Since, in the worst case, all the nodes on the entire last level could be in the queue simultaneously. Binary trees, problems, and solutions. Problem 1, give an algorithm for finding maximum element in binary tree. Solution, one simple way of solving this problem is, find the maximum element in left subtree, find the maximum element in right subtree, compare them with root data, and select the one which is giving the maximum value. This approach can be easily implemented with recursion. Time complexity, O. Space complexity, O. Problem 2, give an algorithm for finding the maximum element in binary tree without recursion. Solution, using level order traversal, just observe the element's data while deleting. Time complexity, O. Space complexity, O. Problem 3, give an algorithm for searching an element in binary tree. Solution, given a binary tree, return true if a node with data is found in the tree. Recurse down the tree, choose the left or right branch by comparing data with each node's data. Time complexity O. Space complexity O. Problem 4, give an algorithm for searching an element in binary tree without recursion. Solution, we can use level order traversal for solving this problem. The only change required in level order traversal is, instead of printing the data, we just need to check whether the root data is equal to the element we want to search. Time complexity O. Space complexity O. Problem 5, give an algorithm for inserting an element into binary tree. Solution, since the given tree is a binary tree, we can insert the element wherever we want. To insert an element, we can use the level order traversal and insert the element wherever we find the node whose left or right child is null. Void insert in binary tree q equal to create q on q, while temp equal to dq if nq, else temp left new node, delete q, return if else on q, temp right new node, delete q, return delete q. Time complexity O. Space complexity O. Problem 6, give an algorithm for finding the size of binary tree. Solution, calculate the size of left and right subtrees recursively, add 1, and return to its parent. Time complexity O. Space complexity O. Problem 7, can we solve problem 6 without recursion? Solution, yes, using level order traversal. Time complexity O. Space complexity O. Problem 8, give an algorithm for printing the level order data in reverse order. For example, the output for the below tree should be 4, 5, 6, 7, 2, 3, 1. Solution, time complexity O. Space complexity O. Problem 9, give an algorithm for deleting the tree. Solution, to delete a tree, we must traverse all the nodes of the tree and delete them one by one. So which traversal should we use? In order, pre-order, post-order, or level order traversal? Before deleting the parent node, we should delete its children nodes first. We can use post-order traversal as it does the work without storing anything. We can delete tree with other traversals also with extra space complexity. For the following, tree nodes are deleted in order 4, 5, 2, 3, 1. Time complexity O. Space complexity O. Problem 10, give an algorithm for finding the height of the binary tree. Solution, recursively calculate height of left and right subtrees of a node and assign height to the node as max of the heights of two children plus 1. This is similar to pre-order tree traversal. Time complexity O. Space complexity O. Problem 11, can we solve problem 10 without recursion? Solution, yes, using level order traversal. This is similar to BFS of graph algorithms. End of level is identified with null. Time complexity O. Space complexity O. Problem 12, give an algorithm for finding the deepest node of the binary tree. Solution, time complexity O. Space complexity O. Give an algorithm for deleting an element from binary problem 13 tree. Solution, the deletion of a node in binary tree can be implemented as: starting at root, find the node which we want to delete. Find the deepest node in the tree. Replace the deepest node's data with node to be deleted. Then delete the deepest node. Problem 14, give an algorithm for finding the number of leaves in the binary tree without using recursion. Solution, the set of nodes whose both left and right children are null layer called leaf nodes. Time complexity O. Space complexity O. Problem 15, give an algorithm for finding the number of full nodes in the binary tree without using recursion. Solution, the set of all nodes with both left and right children are called full nodes. Time complexity O. Space complexity O. Problem 16, give an algorithm for finding the number of half nodes in the binary tree without using recursion. Solution, the set of all nodes with either left or right child are called half nodes. Time complexity O. Space complexity, O. Problem 17, given two binary trees, return true if they are structurally identical. Solution. Algorithm. If both trees are null, then return true. If both trees are not null, then compare data and recursively check left and right subtree structures. Time complexity, O. Space complexity, O for recursive stack. Problem 18, give an algorithm for finding the diameter of the binary tree. The diameter of a tree is the number of nodes on the longest path between two leaves in the tree. Solution. To find the diameter of a tree, first calculate the diameter of left subtree and right subtrees recursively. Among these two values, we need to send maximum value along with current level. There is another solution, and the complexity is O. The main idea of this approach is that the node stores its left child's and right child's maximum diameter if the node's child is the root. Therefore, there is no need to recursively call the height method. The drawback is we need to add two extra variables in the node structure. Give an algorithm for finding the level that has the maximum sum in the binary problem 19 tree. Time complexity O. Space complexity O. Solution. The logic is very much similar finding the number of levels. The only change is we n eedtok e t tar ac kof that's e s swell. In find level with maxsum, else current sum equal to temp data if in q, one return max level. Time complexity O. Space complexity O. Problem 20, given a binary tree, print out all its root to leaf paths. Solution. Refer to comments and functions. Time complexity O. Space complexity O for recursive stack. Problem 21, give an algorithm for checking the existence of path with given sum. That means, given a sum, check whether there exists a path from root to any of the nodes. Solution for this problem, the strategy is subtract the node value from the sum before calling its children recursively and check to see if the sum is 0 when we run out of tree. Solution, recursively, call left subtree sum, right subtree sum, and add their values to current node's data. Time complexity O. Space complexity O. Problem 22. Give an algorithm for finding the sum of all elements in binary tree. Time complexity O. Space complexity O. Problem 23. Can we solve problem 22 without recursion? Solution. We can use level order traversal with simple change. Every time after deleting an element from Q, add the node's data value to some variable. Time complexity O. Space complexity O. Problem 24. Give an algorithm for converting a tree to its mirror. Mirror of a tree is another tree with left and right children of all non-leaf nodes interchanged. The trees below are mirrors to each other. Root SL3. Solution. Struct binary tree node mirror of binary tree. Struct binary tree node temp. If mirror of binary tree, swap the pointers in this node. Temp equal to root left, root right equal to temp, return root. Time complexity O. Space complexity O. Problem 25. Given two trees, give an algorithm for checking whether they are mirrors of each other. Solution. Problem 27. Give an algorithm for constructing binary tree from given in-order and pre-order traversals. Time complexity O. Space complexity O. Problem 26. Give an algorithm for finding LCA of two nodes in a binary tree. Solution. Time complexity O. Space complexity O for recursion. Solution. Let us consider the traversals below. In order sequence, DBE AFC preorder sequence, a BDE CF2, create a new tree node from heap with the data as selected element. In a preorder sequence, leftmost element denotes the root of the tree. So we know A is the root for given sequences. By searching A in order sequence, we can find out all elements on the left side of A, which come under the left subtree, and elements on the right side of A, which come under the right subtree. So we get the structure as seen below. We recursively follow the above steps and get the following tree. Algorithm build tree. 1. Select an element from preorder. Increment a preorder index variable to pick next element in next recursive call. 3. Find the selected element's index in order. Let the index be in order index. 4. Call build binary tree for elements before in order index and make the built tree as left subtree of new node. 5. Call build binary tree for elements after in order index and make the built tree as right subtree of new node. 6. Return new node. Time complexity O. Space complexity O. Problem 28. If we are given two traversal sequences, can we construct the binary tree uniquely? Solution. It depends on what traversals are given. If one of the traversal methods is in order, then the tree can be constructed uniquely, otherwise not. Therefore, the following combinations can uniquely identify a tree: in order and pre-order, in order and post-order, in order and level order. The following combinations do not uniquely identify a tree: post-order and pre-order, pre-order and level order, post-order and level order. For example, pre-order, level order, and post-order traversals are the same for the above trees. So, even if 3 of them are given, the tree cannot be constructed uniquely. Problem 29. Give an algorithm for printing all the ancestors of a node in a binary tree. For the tree below, for 7 the ancestors are 1, 3, 7. Solution. Apart from the depth-first search of this tree, we can use the following recursive way to print the ancestors. Time complexity, O. Space complexity, O for recursion. Problem 30. Zigzag tree traversal. Give an algorithm to traverse a binary tree in zigzag order. For example, the output for the tree below should be 1, 3, 2, 4, 5, 67. Solution. This problem can be solved easily using 2 stacks. Assume the 2 stacks are current level and next level. We would also need a variable to keep track of the current level order. We pop from current level stack and print the node's value. Whenever the current level order is from left to right, push the node's left child, then its right child, to stack next level. Since a stack is a last in first out structure, the next time that nodes are popped off next level, it will be in the reverse order. On the other hand, when the current level order is from right to left, we would push the node's right child first, then its left child. Finally, don't forget to swap those 2 stacks at the end of each level. Void zigzag traversal else if push, if left to right, 1 left to right, swap. Time complexity, O. Space complexity, space for 2 stacks equal to O plus O equal to O. Problem minus 31. Give an algorithm for finding the vertical sum of a binary tree. For example, the tree has 5 vertical lines. Vertical own, nodes minus 4 equal to vertical sum is 4 vertical 2, nodes 2 equal to vertical sum is 2 vertical 3, nodes 1, 5, 6 equal to vertical sum is 1 plus 5 plus 6 equal to 12 vertical minus 4, nodes 3 equal to vertical sum is 3 vertical 5, nodes 7 equal to vertical sum is 7. We need to output 42, 12, 37. Solution. We can do an in-order traversal and hash the column. We call vertical sum on binary tree fruit 0, which means the root is at column 0. While doing the traversal, hash the column and increase its value by root data. Void vertical sum in binary. If return vertical sum in binary tree, refer hashing chapter for implementation of hash table hash column, plus root data, vertical sum in binary tree, vertical sum in binary tree, print hash. Problem 32. How many different binary trees are possible with n nodes? Solution, for example, consider a tree with 3 nodes. It will have the maximum combination of 5 different trees. In general, if there are n nodes, there exist 2n different trees. Problem minus 33. Given a tree with a special property where leaves are represented with L and internal node with I. Also, assume that each node has either 0 or 2 children. Given pre-order traversal of this tree, construct the tree. Example, given pre-order string equal to illil. Solution. First, we should see how pre-order traversal is arranged. Pre-order traversal means first put root node, then pre-order traversal of left subtree, and then pre-order traversal of right subtree. In a normal scenario, it's not possible to detect where left subtree ends and right subtree starts using only pre-order traversal. Since every node has either 2 children or no child, we can surely say that if a node exists, then its sibling also exists. So every time when we are computing a subtree, we need to compute its sibling subtree as well. Secondly, whenever we get L in the input string, that is a leaf, and we can stop for a particular subtree at that point. After this L node, its sibling starts. If L node is right child of its parent, then we need to go up in the hierarchy to find the next subtree to compute. Keeping the above invariant in mind, we can easily determine when a subtree ends and the next one starts. It means that we can give any start node to our method, and it can easily complete the subtree it generates going outside of its nodes. We just need to take care of passing the correct start nodes to different subtrees. Struct binary tree node build tree from pre-order if equal to L. On reaching leaf node, return new node, +1. Populate left subtree equal to +1. New node left build tree from pre-order equal to new node right build tree from pre-order. Return new node. Populate right subtree. Time complexity, O. Problem minus 34. Given a binary tree with 3 pointers, give an algorithm for filling the next sibling pointers assuming they are null initially. Solution, we can use simple Q. Let us assume that the structure of binary tree is struct binary tree node left, struct binary tree node right, struct binary tree node next sibling, infill next siblings else, temp next sibling Q front, equal to if in Q, time complexity, O. Space complexity, O. Problem minus 35. Is there any other way of solving problem 34? Solution. The trick is to reuse the populated next sibling pointers. As mentioned earlier, we just need one more step for it to work. Before we pass the left and right to the recursion function itself, we connect the right child's next sibling to the current node's next sibling left child. In order for this to work, the current node next sibling pointer must be populated, which is true in this case. 6.7 Generic trees. Time complexity. O. In the previous section, we discussed binary trees where each node can have a maximum of 2 children, and these are represented easily with 2 pointers. But suppose if we have a tree with many children at every node, and also if we do not know how many children a node can have, how do we represent them? For example, consider the tree shown below. How do we represent the tree? In the above tree, there are nodes with 6 children, with 3 children, with 2 children, with 1 child, and with 0 children. To present this tree, we have to consider the worst case and allocate that many child pointers for each node. Based on this, the node representation can be given as struct tree node int data, struct tree node first child, struct tree node second child, struct tree node third child, struct tree node fourth child, struct tree node fifth child, struct tree node sixth child. Since we are not using all the pointers in all the cases, there is a lot of memory wastage. Another problem is that we do not know the number of children for each node in advance. In order to solve this problem, we need a representation that minimizes the wastage and also accepts nodes with any number of children. Representation of generic trees. Since our objective is to reach all nodes of the tree, a possible solution to this is as follows. At each node, link children of same parent from left to right. Remove the links from parent to all children except the first child. What these above statements say is, if we have a link between children, then we do not need extra links from parent to all children. This is because we can traverse all the elements by starting at the first child of the parent. So if we have a link between parent and first child and also links between all children of same parent, then it solves our problem. This representation is sometimes called first child next sibling representation. First child next sibling representation of the generic tree is shown above. The actual representation for this tree is, based on this discussion, the tree node declaration for general tree can be given as struct tree node int data, struct tree node first child, struct tree node next sibling. Note: since we are able to convert any generic tree to binary representation, in practice we use binary trees. We can treat all generic trees with a first child next sibling representation as binary trees. Generic trees, problems and solutions. Problem 36, given a tree, give an algorithm for finding the sum of all the elements of the tree. Solution: the solution is similar to what we have done for simple binary trees. That means traverse the complete list and keep on adding the values. We can either use level order traversal or simple recursion. In find sum, if return 0, return root data plus find sum. Time complexity, O. Space complexity, O. Otherwise O. Note: all problems which we have discussed for binary trees are applicable for generic trees also. Instead of left and right pointers, we just need to use first child and next sibling. Problem -37 for a 4-array tree. What is the maximum possible height with 100 nodes? Assume height of a single node is 0. Solution: in 4-array tree, each node can contain 0 to 4 children. And to get maximum height, we need to keep only 1 child for each parent. With 100 nodes, the maximum possible height we can get is 99%. If we have a restriction that at least one node has 4 children, then we keep one node with 4 children and the remaining nodes with 1 child. In this case, the maximum possible height is 96. Similarly, with n nodes, the maximum possible height is n4. Problem -38 for a 4-array tree. What is the minimum possible height with n nodes? Solution: similar to the above discussion, if we want to get minimum height, then we need to fill all nodes with maximum children. Now let's see the following table, which indicates the maximum number of nodes for a given height. H plus 1 for a given height. H, the maximum possible nodes are, to get minimum height, take logarithm on both sides. Problem -39, given a parent array P, where P indicates the parent of th node in the tree. Give an algorithm for finding the height or depth of the tree. Solution: for example, if the P is, its corresponding tree is. From the problem definition, the given array represents the parent array. That means we need to consider the tree for that array and find the depth of the tree. The depth of this given tree is 4. If we carefully observe, we just need to start at every node and keep going to its parent until we reach -1 and also keep track of the maximum depth among all nodes. In find depth in generic tree, int n, current depth equal to 0, j equal to I, while equal to -1, current depth plus, j equal to p. If max depth current depth, return max depth. Time complexity, O. For skew trees, we will be recalculating the same values. Space complexity, O. Note: we can optimize the code by storing the previous calculated node's depth in some hash table or other array. This reduces the time complexity but uses extra space. Problem -40, given a node in the generic tree, give an algorithm for counting the number of siblings for that node. Solution: since tree is represented with the first child next sibling method, the tree structure can be given as struct tree node int data, struct tree node first child, struct tree node next sibling. For a given node in the tree, we just need to traverse all its next siblings. In siblings count, int count equal to 0, while count plus plus current equal to current next sibling, Return count. Time complexity, O, space complexity, O. Problem 41. Given a node in the generic tree, give an algorithm for counting the number of children for that node. Solution. Since the tree is represented as first child next sibling method, the tree structure can be given as struct tree node int data, struct tree node first child, struct tree node next sibling. For a given node in the tree, we just need to point to its first child and keep traversing all its next siblings. In child count, int count equal to 0, current first child, while count plus plus current next sibling, Return count. Time complexity, O, space complexity, O. Problem minus 42. Given two trees. How do we check whether the trees are isomorphic to each other or not? Solution. Two binary trees, root and root, are isomorphic if they have the same structure. The values of the nodes does not affect whether two trees are isomorphic or not. In the diagram below, the tree in the middle is not isomorphic to the other trees, but the tree on the right is isomorphic to the tree on the left. Int isomorphic andand. Root return 1 if andand root or are andand. Root return 0, return andand isomorphic. Time complexity, O, space complexity, O. Problem minus 43. Given two trees. How do we check whether they are quasi-isomorphic to each other or not? Solution. Two trees, root and root, are quasi-isomorphic if root can be transformed into root by swapping the left and right children of some of the nodes of root. Data in the nodes are not important in determining quasi-isomorphism, only the shape is important. The trees below are quasi-isomorphic because if the children of the nodes on the left are swapped, the tree on the right is obtained. Int quasi-isomorphic if or return 0. Return and quasi-isomorphic or quasi-isomorphic and quasi-isomorphic. Time complexity, O. Space complexity, O. Problem minus 44. A full k-array tree is a tree where each node has either 0 or k children. Given an array which contains the pre-order traversal of full k-array tree, give an algorithm for constructing the full k-array tree. Solution. In k, array tree. For a node at ith position, its children will be at ki plus 1 to ki plus k. For example, the example below is for full 3 array tree. As we have seen, in pre-order traversal first left subtree is processed, then followed by root node and right subtree. Because of this, to construct a full k array, we just need to keep on creating the nodes without bothering about the previous constructed nodes. We can use this trick to build the tree recursively by using one global index. The declaration for k-array tree can be given as struct k-array tree node, struct k-array tree node child, int ind equal to 0, struct k-array tree node build k-array tree, int n, int k if in plus plus equal to new node child build k-array tree, else new node child equal to null, return new node. Time complexity, O, where n is the size of the pre-order array. This is because we are moving sequentially and not visiting the already constructed nodes. 6.8 Threaded binary tree traversals. In earlier sections, we have seen that pre-order, in-order, and post-order binary tree traversals use stacks and level order traversals used queues as an auxiliary data structure. In this section, we will discuss new traversal algorithms which do not need both stacks and queues. Such traversal algorithms are called threaded binary tree traversals or stack queue, less traversals. Issues with regular binary tree traversals. The storage space required for the stack and queue is large. The majority of pointers in any binary tree are null. For example, a binary tree with n nodes has n plus 1 null pointers, and these were wasted. It is difficult to find successor node for a given node. Motivation for threaded binary trees. To solve these problems, one idea is to store some useful information in null pointers. If we observe the previous traversals carefully, stack queue is required because we have to record the current position in order to move to the right subtree after processing the left subtree. If we store the useful information in null pointers, then we don't have to store such information in stack queue. The binary trees which store such information in null pointers are called threaded binary trees. From the above discussion, let us assume that we want to store some useful information in null pointers. The next question is what to store. The common convention is to put predecessor-successor information. That means if we are dealing with pre-order traversals, then for a given node, null left pointer will contain pre-order predecessor information, and null right pointer will contain pre-order successor information. These special pointers are called threads. Classifying threaded binary trees. The classification is based on whether we are storing useful information in both null pointers or only in one of them. If we store predecessor information in null left pointers only, then we can call such binary trees left-threaded binary trees. If we store successor information in null right pointers only, then we can call such binary trees right-threaded binary trees. If we store predecessor information in null left pointers and successor information in null right pointers, then we can call such binary trees fully threaded binary trees or simply threaded binary trees. Note: for the remaining discussion, we consider only threaded binary trees. Types of threaded binary trees. Based on above discussion, we get 3 representations for threaded binary trees. Pre-order threaded binary trees: null left pointer will contain pre-order predecessor information, and null right pointer will contain pre-order successor information. In-order threaded binary trees: null left pointer will contain in-order predecessor information, and null right pointer will contain in-order successor information. Post-order threaded binary trees: null left pointer will contain post-order predecessor information, and null right pointer will contain post-order successor information. Note: as the representations are similar, for the remaining discussion we will use in-order threaded binary trees. Threaded binary tree structure. Any program examining the tree must be able to differentiate between a regular left-right pointer and a thread. To do this, we use 2 additional fields in each node, giving us, for threaded trees, nodes of the following form: difference between binary tree and threaded binary tree structures. Note: similarly, we can define pre-order post-order differences as well. As an example, let us try representing a tree in in-order threaded binary tree form. The tree below shows what an in-order threaded binary tree will look like. The dotted arrows indicate the threads. If we observe, the left pointer of leftmost node and right pointer of rightmost node are hanging. What should leftmost and rightmost pointers point to? In the representation of a threaded binary tree, it is convenient to use a special node dummy which is always present even for an empty tree. Note that right tag of dummy node is 1 and its right child points to itself. With this convention, the above tree can be represented as dummy node. Finding in-order successor in in-order threaded binary tree. To find in-order successor of a given node without using a stack, assume that the node for which we want to find the in-order successor is P. Strategy: if P has a no right subtree, then return the right child of P. If P has right subtree, then return the left of the nearest node whose left subtree contains P. Struct threaded binary tree node in order successor. Struct threaded binary tree node position. If return P right, else equal to position P right, while position left, return position. Time complexity O, space complexity O, in order traversal in in-order threaded binary tree. We can start with dummy node and call in-order successor to visit each node until we reach dummy node. Void in-order traversal, struct threaded binary tree node P equal to in-order successor, while P in-order successor, printf. Alternative coding, void in-order traversal, struct threaded binary tree node P equal to root, while P in-order successor, if returned, printf. Time complexity O, space complexity O, finding pre-order successor in in-order threaded binary tree. Strategy: if P has a left subtree, then return the left child of P. If P has no left subtree, then return the right child of the nearest node whose right subtree contains P. Struct threaded binary tree node pre-order successor. Struct threaded binary tree node position. If else, return P left, position equal to P, while position equal to position right, return position right. Time complexity O, space complexity O, pre-order traversal of in-order threaded binary tree. As in in-order traversal, start with dummy node and call pre-order successor to visit each node until we get dummy node again. Void pre-order traversal, struct threaded binary tree node P equal to P pre-order successor, while P equal to pre-order successor, printf. Alternative coding. Void pre-order traversal, struct threaded binary tree node P equal to root, while P equal to pre-order successor, if return, printf. Time complexity O, space complexity O. Note: from the above discussion, it should be clear that in-order and pre-order successor finding is easy with threaded binary trees. But finding post-order successor is very difficult if we do not use stack. Insertion of nodes in in-order threaded binary trees. For simplicity, let us assume that there are 2 nodes P and Q, and we want to attach Q to right of P. For this, we will have 2 cases. Node P does not have right child. In this case, we just need to attach Q to P and change its left and right pointers. Node P has right child. In this case, we need to traverse R's left subtree and find the leftmost node and then update the left and right pointer of that node. Void insert right in order, TBT, temp equal to Q right, while temp equal to temp left equal to Q. Case 2. Time complexity O, space complexity O, threaded binary trees, problems and solutions. Problem 45 for a given binary tree. How do we find the pre-order successor? Solution: for solving this problem, we need to use an auxiliary stack S. On the first call, the parameter node is a pointer to the head of the tree, and thereafter its value is null. Since we are simply asking for the successor of the node we got the last time we called the function, it is necessary that the contents of the stack S and the pointer P to the last node visited are preserved from one call of the function to the next. They are defined as static variables. Or preorder successor for an unthreaded binary tree, struct binary tree node, preorder successor, else, while P equal to pop, P equal to P right, return P. Problem -46 for a given binary tree. How do we find the in-order successor? Solution: similar to the above discussion, we can find the in-order successor of a node as in-order successor for an unthreaded binary tree, struct binary tree node, in-order successor, static struct binary tree node P, static stack S equal to if P equal to node, create stack if else, P equal to pop, P equal to P right, while push, P equal to P left, return P. 6.9 Expression trees. A tree representing an expression is called an expression tree. In expression trees, leaf nodes are operands and non-leaf nodes are operators. That means an expression tree is a binary tree where internal nodes are operators and leaves are operands. An expression tree consists of binary expression. But for a unary operator, one subtree will be empty. The figure below shows a simple expression tree for D. Algorithm for building expression tree from postfix expression. Struct binary tree node build XBR tree, int C size, struct binary tree node new node equal to malloc, if else new node data equal to postfix XBR, new node left equal to T1, new node right equal to T2, push, return S. Example: assume that one symbol is read at a time. If the symbol is an operand, we create a tree node and push a pointer to it onto a stack. If the symbol is an operator, pop pointers to two trees T1 and T2 from the stack and form a new tree whose root is the operator and whose left and right children point to T2 and T1 respectively. A pointer to this new tree is then pushed onto the stack. As an example, assume the input is ABC plus D. The first three symbols are operands, so create tree nodes and push pointers to them onto a stack as shown below. Next, an operator is read, so two pointers to trees are popped, a new tree is formed and a pointer to it is pushed onto the stack. Next, an operator plus is read, so two pointers to trees are popped, a new tree is formed and a pointer to it is pushed onto the stack. Next, an operand D is read, a one-node tree is created and a pointer to the corresponding tree is pushed onto the stack. Finally, the last symbol is read. Two trees are merged and a pointer to the final tree is left on the stack. 6.10 XOR trees. This concept is similar to memory-efficient, doubly linked lists of linked list chapter. Also, like threaded binary trees, this representation does not need stacks or queues for traversing the trees. This representation is used for traversing back and forth using operation. To represent the same in XOR trees, for each node below are the rules used for representation. Each node's left will have the of its parent and its left children. Each node's right will have the of its parent and its right children. The root node's parent is null and also leaf node's children are null nodes. Based on the above rules and discussion, the tree can be represented as the major objective of this presentation is the ability to move to parent as well to children. Now, let us see how to use this representation for traversing the tree. For example, if we are at node B and want to move to its parent node A, then we just need to perform on its left content with its left child address. Similarly, if we want to move to its child, then we have to perform on its left content with its parent node address. One important point that we need to understand about this representation is, when we are at node B, how do we know the address of its children D? Since the traversal starts at node root node, we can apply on root's left content with null. As a result, we get its left child, B. When we are at B, we can apply on its left content with A address. 6.11 Binary search trees. Why binary search trees? In previous sections, we have discussed different tree representations, and in all of them, we did not impose any restriction on the node's data. As a result, to search for an element, we need to check both in left subtree and in right subtree. Due to this, the worst-case complexity of search operation is O. In this section, we will discuss another variant of binary trees, binary search trees. As the name suggests, the main use of this representation is for searching. In this representation, we impose restriction on the kind of data a node can contain. As a result, it reduces the worst-case average search operation to O binary search tree property. In binary search trees, all the left subtree elements should be less than root data, and all the right subtree elements should be greater than root data. This is called binary search tree property. Note that this property should be satisfied at every node in the tree. The left subtree of a node contains only nodes with keys less than the node's key. The right subtree of a node contains only nodes with keys greater than the node's key. Both the left and right subtrees must also be binary search trees. Example, the left tree is a binary search tree and the right tree is not a binary search tree. Binary search tree declaration. There is no difference between regular binary tree declaration and binary search tree declaration. The difference is only in data but not in structure, but for our convenience we change the structure name as operations on binary search trees, main. Operations following are the main operations that are supported by binary search trees. Find minimum, find maximum element in binary search trees, inserting an element in binary search trees, deleting an element from binary search trees, auxiliary operations, checking whether the given tree is a binary search tree or not, finding KTH smallest element in tree, sorting the elements of binary search tree, and many more. Important notes on binary search trees. Since root data is always between left subtree data and right subtree data, performing in-order traversal on binary search tree produces a sorted list. While solving problems on binary search trees, first we process left subtree, then root data, and finally we process right subtree. This means, depending on the problem, only the intermediate step changes and we do not touch the first and third steps. If we are searching for an element, and if the left subtree root data is less than the element we want to search, then skip it. The same is the case with the right subtree. Because of this, binary search trees take less time for searching an element than regular binary trees. In other words, the binary search trees consider either left or right subtrees for searching an element, but not both. The basic operations that can be performed on binary search tree are insertion of element, deletion of element, and searching for an element. While performing these operations on BST, the height of the tree gets changed each time. Hence, there exists variations in time complexities of best case, average case, and worst case. The basic operations on a binary search tree take time proportional to the height of the tree. For a complete binary tree with node n, such operations runs in O worst case time. If the tree is a linear chain of n nodes, however, the same operations takes O worst case time. Finding an element in binary search trees. Find operation is straightforward in a BST. Start with the root and keep moving left or right using the BST property. If the data we are searching is same as node's data, then we return current node. If the data we are searching is less than node's data, then search left subtree of current node, otherwise search right subtree of current node. If the data is not present, we end up in a null. Link. Struct binary search tree node find if return null, if return find, else if return root. Time complexity, O in worst case. Space complexity, O for recursive stack. Non-recursive version of the above algorithm can be given as struct binary search tree node find return null, while if return root, else if root equal to root right, else root equal to root left, one return null. Time complexity, O. Space complexity, O. Finding minimum element in binary search trees. In BSTs, the minimum element is the leftmost node, which does not has left child. In the BST below, the minimum element is 4. Struct binary search tree, node find min, if return null, else if else return root, return find min. Time complexity, O in worst case. Space complexity, O for recursive stack. Non-recursive version of the above algorithm can be given as struct binary search tree node find min if return null, while root equal to root left, return root. Time complexity, O. Space complexity, O. Finding maximum element in binary search trees. In BSTs, the maximum element is the rightmost node, which does not have right child. In the BST below, the maximum element is 16. Struct binary search tree node find max if return null, else if return root, else return find max. Time complexity, O in worst case. Space complexity, O for recursive stack. Struct binary search tree node find max if return null, while root equal to root right, return root. Time complexity, O. Space complexity, O. Where is in-order predecessor and successor? Where is the in-order predecessor and successor of node X in a binary search tree, assuming all keys are distinct? If X has 2 children, then its in-order predecessor is the maximum value in its left subtree and its in-order successor the minimum value in its right subtree. Predecessor. If it does not have a left child, then a node's in-order predecessor is its first left ancestor. Inserting an element from binary search tree. To insert data into binary search tree, first we need to find the location for that element. We can find the location of insertion by following the same mechanism as that of find operation. While finding the location, if the data is already there, then we can simply neglect and come out. Otherwise, insert data at the last location on the path traversed. As an example, let us consider the following tree. The dotted node indicates the element to be inserted. To insert 5, traverse the tree using find function. At node with key 4, we need to go right, but there is no subtree, so 5 is not in the tree, and this is the correct location for insertion. Struct binary search tree node insert return root. Note, in the above code, after inserting an element in subtrees, the tree is returned to its parent. As a result, the complete tree will get updated. Time complexity, O. Space complexity, O for recursive stack. For iterative version, space complexity is O, deleting an element from binary search tree. The delete operation is more complicated than other operations. This is because the element to be deleted may not be the leaf node. In this operation also, first we need to find the location of the element which we want to delete. Once we have found the node to be deleted, consider the following cases. If the element to be deleted is a leaf node, return null to its parent. That means make the corresponding child pointer null. In the tree below, to delete 5, set null to its parent node 2. If the element to be deleted has one child, in this case, we just need to send the current node's child to its parent. In the tree below, to delete 4, left subtree is set to its parent node 2. If the element to be deleted has both children, the general strategy is to replace the key of this node with the largest element of the left subtree and recursively delete that node. The largest node in the left subtree cannot have a right child, so the second delete is an easy one. As an example, let us consider the following tree. In the tree below, to delete 8, it is the right child of the root. The key value is 8. It is replaced with the largest key in its left subtree, and then that node is deleted as before. Note, we can replace with minimum element in right subtree also. Struct binary search tree node delete, found element if return root, time complexity, O, space complexity, O for recursive stack. For iterative version, space complexity is O. Binary search trees, problems, and solutions. Note, for ordering related problems with binary search trees and balanced binary search trees, in-order traversal has advantages over others as it gives the sorted order. Problem -47, given pointers to 2 nodes in a binary search tree, find the lowest common ancestor. Assume that both values already exist in the tree. Solution. The main idea of the solution is while traversing BST from root to bottom, the first node we encounter with value between A and SS, that is a node data less than SS, is the least common ancestor of A and SS. So just traverse the BST in preorder, and if we find a node with value in between A and SS, then that node is the LCA. If its value is greater than both A and SS, then the LCA lies on the left side of the node. And if its value is smaller than both A and SS, then the LCA lies on the right side. Struct binary search tree node find LCA. While if or return root, if root left equal to else root equal to root right, A data root data and B data root data. Time complexity, O. Space complexity, O for skew trees. Problem -48, give an algorithm for finding the shortest path between 2 nodes in a BST. Solution, it's nothing but finding the LCA of 2 nodes in BST. Problem -49, give an algorithm for counting the number of BSTs possible with n nodes. Solution, this is a DP problem. Refer to chapter on dynamic programming for the algorithm. Give an algorithm to check whether the given binary tree is a BST or not. Problem -50 solution, consider the following simple program. For each node, check if the node on its left is smaller and check if the node on its right is greater. This approach is wrong as this will return true for binary tree below. Checking only at current node is not enough. Int is BST if return 1, false if left is then root if return 0, false if right is then root if return 0, or false if recursively the left or right is not a BST if or ASBST return 0. Passing all that, it's a BST return 1. Problem 51. Can we think of getting the correct algorithm? Solution. For each node, check if max value in left subtree is smaller than the current node data and min value in right subtree greater than the node data. It is assumed that we have helper functions find min and find max that return the min or max integer value from a non-empty tree. Returns true if a binary tree is a binary search tree, int ESP if return 1. False if the max of the left is then root. If root data return 0. False if the min of the right is less than equal to than root. If root data return 0. False if recursively the left or right is not a BST. If or ISBST return 0. Passing all that, it's a BST return 1. Time complexity O. Space complexity O. Problem 52. Can we improve the complexity of problem 51%? Solution, yes. A better solution is to look at each node only once. The trick is to write a utility helper function isutil that traverses down the tree, keeping track of the narrowing min and max allowed values as it goes, looking at each node only once. The initial values for min and max should be int min and int max. They narrow from there. Initial call ISBST int ISBST if return 1, return and ISBST util. Time complexity O. Space complexity O for stack space. Problem -53. Can we further improve the complexity of problem 51? Solution, yes, by using in-order traversal. The idea behind this solution is that in-order traversal of BST produces sorted lists. While traversing the BST in order, at each node check the condition that its key value should be greater than the key value of its previous visited node. Also, we need to initialize the prev with possible minimum integer value. Int prev equal to int min, int ISBST, if return 1, if return 0, if return 0, prev equal to root data, return ISBST. Time complexity, O. Space complexity, O for stack space. Problem 54, give an algorithm for converting BST to circular DL with space complexity O. Solution, convert left and right subtrees to DLS and maintain end of those lists. Then, adjust the pointers. Struct binary search tree node BST2 DLL, struct binary search tree node left, ITail right RTail, if ITail equal to null, return null, left BS2 DLL equal to right BS2 DLL, root left equal to ITail, root right equal to right if else, ITail equal to root, right left equal to root, ITail equal to RTail if return root, else ITail right equal to root, return left. Time complexity, O. Problem 55. For problem 54, is there any other way of solving it? Solution, yes. There is an alternative solution based on the divide and conquer method, which is quite neat. Struct binary search tree, node append, return B. If return A last, A left, blast, B left, A last, right equal to B. B left equal to A last, blast right equal to A left equal to blast, return A. Struct binary search tree node tree to list, struct binary search tree node A list, B list, if return null, A list tree to list, equal to B list tree to list, root left equal to root right equal to A list append, equal to A list append, return, tree node B. Time complexity, O. Problem 56. Given a sorted doubly linked list, give an algorithm for converting it into balanced binary search tree. Solution, find the middle node and adjust the pointers. Struct DL node DL balanced BST, struct DL node temp, P, Q, if return head, temp equal to find middle node, P equal to head, while P equal to P next, P next equal to null, Q equal to temp next equal to null, temp prev equal to DL balanced BST, temp next equal to DL balanced BST, return temp. Time complexity, 2 trillions plus O equal to O. Note, for find middle node function, refer linked lists chapter. Problem minus 57, given a sorted array, give an algorithm for converting the array to BST. Solution, if we have to choose an array element to be the root of a balanced BST, which element should we pick? The root of a balanced BST should be the middle element from the sorted array. We would pick the middle element from the sorted array in each iteration. We then create a node in the tree initialized with this element. After the element is chosen, what is left? Could you identify the subproblems within the problem? There are 2 arrays left, the one on its left and the one on its right. These 2 arrays are the subproblems of the original problem, since both of them are sorted. Furthermore, they are subtrees of the current node's left and right child. The code below creates a balanced BST from the sorted array in O time. Compare how similar the code is to a binary search algorithm. Both are using the divide and conquer methodology. Struct binary tree node build BST, int left, int right. Struct binary tree node new node, int mid. If return null, new node malloc. If printf return, if new node data equal to A, new node left, new node right equal to null, else mid left plus 2, new node data equal to A, new node left build BST equal to new node right build BST, return new node. Time complexity, O. Space complexity, O for stack space. Problem 58. Given a singly linked list where elements are sorted in ascending order, convert it to a height-balanced BST. Solution. A naive way is to apply the problem 56 solution directly. In each recursive call, we would have to traverse half of the list's length to find the middle element. The runtime complexity is clearly O, where n is the total number of elements in the list. This is because each level of recursive call requires a total of n/2 traversal steps in the list, and there are a total of ln number of levels. Problem 59 for problem 58, can we improve the complexity? Solution, hint, how about inserting nodes following the list order? If we can achieve this, we no longer need to find the middle element as we are able to traverse the list while inserting nodes to the tree. Best solution, as usual, the best solution requires us to think from another perspective. In other words, we no longer create nodes in the tree using the top-down approach. Create nodes bottom-up and assign them to their parents. The bottom-up approach enables us to access the list in its order while creating nodes. Isn't the bottom-up approach precise? Anytime we're stuck with the top-down approach, we can give bottom-up a try. Although the bottom-up approach is not the most natural way we think, it is helpful in some cases. However, we should prefer top-down instead of bottom-up in general, since the latter is more difficult to verify. Below is the code for converting a singly linked list to a balanced BST. Please note that the algorithm requires the list length to be passed in as the function parameters. The list length can be found in O time by traversing the entire list once. The recursive calls traverse the list and create tree nodes by the list order, which also takes O time. Therefore, the overall runtime complexity is still O. Struct binary tree node sorted list to BST if return null, same as /2, avoids overflow into mid-start plus 2, struct binary tree node left child sorted list to BST, struct binary tree node parent, parent malloc if, printf return, parent data list data, parent left equal to left child, list next equal to parent right sorted list to BST, return parent, struct binary tree node sorted list to BST, return sorted list to BST. Problem 60, give an algorithm for finding the kth smallest element in BST. Solution. The idea behind the solution is that in-order traversal of BST produces sorted lists. While traversing the BST in order, keep track of the number of elements visited. Struct binary search tree node key a smallest in BST if return null. Struct binary search tree node left equal to kth smallest in BST if return left, if return root, return kth smallest in BST. Time complexity O. Space complexity O. Problem -61 floor and ceiling. If a given key is less than the key at the root of a BST, then the floor of the key must be in the left subtree. If the key is greater than the key at the root, then the floor of the key could be in the right subtree, but only if there is a key smaller than or equal to the key in the right subtree. If not, then the key at the root is the floor of the key. Finding the ceiling is similar, with interchanging right and left. For example, if the sorted with input array is, then for x equal to 0, floor doesn't exist in array, ceil equal to 1, for x equal to 1, floor equal to 1, ceil equal to 1 for x equal to 5, floor equal to 2, ceil equal to 8, for x equal to 20, floor equal to 19, ceil doesn't exist in array. Solution. The idea behind the solution is that in-order traversal of BST produces sorted lists. While traversing the BST in order, keep track of the values being visited. If the roots data is greater than the given value, then return the previous value which we have maintained during traversal. If the roots data is equal to the given data, then return root data. Struct binary tree node floor in BST, struct binary tree node prev equal to null, return floor in BST util, struct binary tree node floor in BST util, return null, struct binary tree node prev int data. If return 0, if return root, if return prev equal to root, return floor in BST util. Time complexity O. Space complexity O for stack space. For ceiling, we just need to call the right subtree first, followed by left subtree. Struct binary tree node ceiling in BST, struct binary tree node prev equal to null, return ceiling in BST util. Struct binary tree node ceiling in BST util, struct binary tree node prev, int data, return null, if return 0, if return root, if return prev equal to root, return ceiling in BST util. Time complexity O. Space complexity O for stack space. Problem 62. Give an algorithm for finding the union and intersection of BSTs. Assume parent pointers are available. Also, assume the lengths of two BSTs are m and n respectively. Solution. If parent pointers are available, then the problem is same as merging of two sorted lists. This is because if we call in-order successor each time we get the next highest element, it's just a matter of which in-order successor to call. Time complexity O. Space complexity O. Problem 63 for problem 62. What if parent pointers are not available? Solution. If parent pointers are not available, the BSTs can be converted to linked lists and then merged. 1. Convert both the BSTs into sorted doubly linked lists in O-time. This produces two sorted lists. 2. Merge the two double linked lists into one and also maintain the count of total elements in O-time. 3. Convert the sorted doubly linked list into height balanced tree in O-time. Problem 64. For problem 62, is there any alternative way of solving the problem? Solution, yes, by using in-order traversal. Perform in-order traversal on one of the BSTs. While performing the traversal, store them in table. After completion of the traversal of first BST, start traversal of second BST, and compare them with hash table contents. Time complexity O. Space complexity O. Problem -65. Given a BST and two numbers K1 and K2, give an algorithm for printing all the elements of BST in the range K1 and K2. Solution. Void range printer, if return, if range printer, if printf, if range printer. Time complexity O. Space complexity O for stack space. Problem 66 for problem 65, is there any alternative way of solving the problem? Solution, we can use level order traversal while adding the elements to queuecheck for the range. Void range, seach level order, struct binary search tree node temp, struct q create q if return null, q equal to on q, while temp to q if printf if in q, delete q, return null. Time complexity O. Space complexity O for q. Problem -67 for problem 65, can we still think of an alternative way to solve the problem? Solution. First locate K1 with normal binary search, and after that use in-order successor until we encounter K2. For algorithm, refer to problem section of threaded binary trees. Problem 68, given root of a binary search tree, trim the tree so that all elements returned in the new tree are between the inputs A and B. Solution. It's just another way of asking problem 65. Problem minus 69, given two BSTs, check whether the elements of them are the same or not. For example, two BSTs with data 105 2015 30 and 10 2015 35 should return true, and the dataset with 105 2015 35 130 and 10 2015 35 and the data 15 and in any order. Note, an in-order traversal on first tree and storing its data in hash table. As a second step, perform an order traversal on second tree and check whether that data is already there in hash table or not. During the traversal of second tree, if we find any mismatch, return false. After traversal of second tree, check whether it has all 1s in the hash table or not. Time complexity, O, where M and N are the number of elements in first and second BST. Space complexity, O. This depends on the size of the first tree. Problem minus 70 for problem minus 69. Can we reduce the time complexity? Solution. Instead of performing the traversals one after the other, we can perform in-order traversal of both the trees in parallel. Since the in-order traversal gives the sorted list, we can check whether both the trees are generating the same sequence or not. Time complexity, O. Space complexity, O. This depends on the size of the first tree. Problem 71 for the key values. 1. N. How many structurally unique BSTs are possible that store those keys? Solution. Strategy. Consider that each value could be the root. Recursively find the size of the left and right subtrees. In count trees, if return 1, else, there will be one value at the root with whatever remains on the left and right, each forming their own subtrees. Iterate through all the values that could be the root, in sum equal to 0, into left, right root for left count trees equal to right count trees, number of possible trees with this root equal to left, right sum plus equal to left, right return. Problem 72, given a BST of size n, in which each node R has an additional field R size, the number of the keys in the subtree rooted at R. Given O algorithm greater than constant to find the number of keys that are strictly greater than K. Solution. Int greater than constant if return keys count. The suggested algorithm works well if the key is a unique value for each node. Otherwise, when reaching K equal to R data, we should start a process of moving to the right until reaching a node Y with a key that is bigger than K, and then we should return keys count plus Y size. Time complexity, O where H equal to O in the worst case and O in the average case. 6.12 Balanced binary search trees. In earlier sections, we have seen different trees whose worst case complexity is O, where n is the number of nodes in the tree. This happens when the trees are skew trees. In this section, we will try to reduce this worst case complexity to O by imposing restrictions on the heights. In general, the height balanced trees are represented with HB, where K is the difference between left subtree height and right subtree height. Sometimes K is called balance factor. Full balanced binary search trees. In HB, if K equal to 0, then we call such binary search trees as full balanced binary search trees. That means, in HB binary search tree, the difference between left subtree height and right subtree height should be at most 0. This ensures that the tree is a full binary tree. For example, note, for constructing HB tree, refer to problem section, 6.13 AVL trees. In HB, if K equal to 1, such a binary search tree is called an AVL tree. That means an AVL tree is a binary search tree with a balanced condition. The difference between left subtree height and right subtree height is at most 1. Properties of AVL trees. A binary tree is said to be an AVL tree if it is a binary search tree and for any node X, the height of left subtree of X and height of right subtree of X differ by at most 1. As an example, among the above binary search trees, the left one is not an AVL tree, whereas the right binary search tree is an AVL tree. Minimum maximum number of nodes in AVL tree. For simplicity, let us assume that the height of an AVL tree is H, and N indicates the number of nodes in AVL tree with height H. To get the minimum number of nodes with height H, we should fill the tree with the minimum number of nodes possible. That means if we fill the left subtree with height H, 1, then we should fill the right subtree with height H2. As a result, the minimum number of nodes with height H is, in the above equation, N indicates the minimum number of nodes with height H1, N indicates the minimum number of nodes with height H2. In the above expression, 1 indicates the current node. We can give N either for left subtree or right subtree. Solving the above recurrence gives, where N is the number of nodes in AVL tree. Also, the above derivation says that the maximum height in AVL trees is O. Similarly, to get maximum number of nodes, we need to fill both left and right subtrees with height H1. As a result, we get The above expression defines the case of full binary tree. Solving the recurrence we get. In both the cases, AVL tree property is ensuring that the height of an AVL tree with n nodes is O, AVL tree declaration. Since AVL tree is a BST, the declaration of AVL is similar to that of BST. But just to simplify the operations, we also include the height as part of the declaration. Struct AVL tree node, struct AVL tree node left, int data, struct AVL tree node right, int height, finding the height of an AVL tree. Int height, if else return -1, return root, height. Time complexity, O, rotations. When the tree structure changes, we need to modify the tree to restore the AVL tree property. This can be done using single rotations or double rotations. Since an insertion deletion involves deleting a single node, this can only decrease the height of a subtree by 1. So, if the AVL tree property is violated at a node X, it means that the heights of left and right differ by exactly 2. This is because if we balance the AVL tree every time, then at any point the difference in heights of left and right differ by exactly 2. Rotations is the technique used for restoring the AVL tree property. This means we need to apply the rotations for the node 10th observation. One important observation is that after an insertion, only nodes that are on the path from the insertion point to the root might have their balances altered, because only those nodes have their subtrees altered. To restore the AVL tree property, we start at the insertion point and keep going to the root to the tree. While moving to the root, we need to consider the first node that is not satisfying the AVL property. From that node onwards, every node on the path to the root will have the issue. Also, if we fix the issue for that first node, then all other nodes on the path to the root will automatically satisfy the AVL tree property. That means we always need to care for the first node that is not satisfying the AVL property on the path from the insertion point to the root and fix it. Types of violations. Let us assume the node that must be rebalanced is 10th, since any node has at most 2 children, and a height imbalance requires that X's 2 subtree heights differ by 2. We can observe that a violation might occur in 4 cases. 1. An insertion into the left subtree of the left child of 10th 2, an insertion into the right subtree of the left child of 10th 3, an insertion into the left subtree of the right child of 10th 4, an insertion into the right subtree of the right child of 10th. Cases 1 and 4 are symmetric and easily solved with single rotations. Similarly, cases 2 and 3 are also symmetric and can be solved with double rotations. Single rotations. Left-left rotation. In the case below, node X is not satisfying the AVL tree property. As discussed earlier, the rotation does not have to be done at the root of a tree. In general, we start at the node inserted and travel up the tree, updating the balance information at every node on the path. For example, in the figure above, after the insertion of 7 in the original AVL tree on the left, node 9 becomes unbalanced. So, we do a single left-left rotation at 9. As a result, we get the tree on the right. Struct AVL tree node single rotate left, struct AVL tree node W equal to X left equal to W right equal to X height equal to max, height plus 1 W height equal to max, X height plus 1, return W, new root, O, space complexity, O, right rotation. In this case, node X is not satisfying the AVL tree property. For example, in the figure after the insertion of 29 in the original AVL tree on the left, node 15 becomes unbalanced. So, we do a single right rotation at 15. As a result, we get the tree on the right. Struct AVL tree node single rotate right, struct AVL tree node X equal to W right equal to X left equal to W height equal to max, height plus 1, X height max, W height plus 1, return X. O, space complexity, O, double rotations. Left-right rotation. For case 2 and case 3, single rotation does not fix the problem. We need to perform 2 rotations. As an example, let us consider the following tree. The insertion of 7 is creating the case 2 scenario, and the right side tree is the one after the double rotation. Code for left-right double rotation can be given as struct AVL tree node double rotate with left, Z left single rotate right, return single rotate left, right-left rotation. Similar to case 2, we need to perform 2 rotations to fix this scenario. As an example, let us consider the following tree. The insertion of 6 is creating the case 3 scenario, and the right side tree is the one after the double rotation. AVL tree is similar to a BST insertion. After inserting the element, we just need to check whether there is any height imbalance. If there is an imbalance, call the appropriate rotation functions. Struct AVL tree node insert, root malloc, if, 1printf return null, else, root data equal to data, root height equal to 0, root left, root right equal to null, else if, root left insert, if height equal to 2, if else equal to root single rotate left, root double rotate left, else if, root right insert, if height equal to 2, if equal to root single rotate right, else root double rotate right. else data is in the tree already. We'll do nothing. Root height max height plus 1. Return root complexity. O. Space complexity. O. Int data. Time. AVL trees, problems, and solutions. Problem 73. Given a height h. Give an algorithm for generating the HB. Solution, as we have discussed, HB is nothing but generating full binary tree. In full binary tree, the number of nodes with height h is 2 hours 1 to 1. As a result, the nodes can be numbered as 1 to 2 hours plus 1 to 1. Struct binary search tree node build HBO return null equal to temp malloc equal to temp left build HB0 equal to temp data count plus plus. Assume count is a global variable temp right build HB0 return temp equal to. Time complexity O. Space complexity O, where alone it indicates the maximum stack size, which is equal to height of tree. Problem minus 74. Is there any alternative way of solving problem 73? Solution. Yes, we can solve it following merge sort logic. That means, instead of working with height, we can take the range. With this approach, we do not need any global counter to be maintained. Struct binary search tree node build HB0 return null, temp malloc, temp data equal to mid, temp left build HB0 equal to temp right build HB0 return temp. The initial call to the build HBO function could be build HB0. 1h does the shift operation for calculating the 2 hours plus 1 to 1. Time complexity O, space complexity O, where lone indicates maximum stack size, which is equal to the height of the tree. Problem 75. Construct minimal AVL trees of height 0, 1, 2, 3, 4, and 5. What is the number of nodes in a minimal AVL tree of height 6? Solution. Let n be the number of nodes in a minimal AVL tree with height h. N equal to 2, n equal to 1n plus n equal to 1n plus n equal to 1 plus 2 plus 1 equal to 4. N equal to 1 plus n and 1 plus 4 plus 2 equal to 7. N plus n equal to 1 plus 7 plus 4 equal to 12. 0. N equal to 1n plus n equal to 1 plus 12 plus 7 equal to 20. Problem 76. For problem 73, how many different shapes can there be of a minimal AVL tree? Of height h, solution. Let ns be the number of different shapes of a minimal AVL tree of height h. ns equal to 2. ns equal to 2 nanoseconds, ns equal to 2 times 2, 1 equal to 4. 0. ns 2 nanoseconds, ns equal to 2, 4, 1 equal to 8. ns equal to 2 nanoseconds ns. Problem 77. Given a binary search tree, check whether it is an AVL tree or not. Solution. Let us assume that isAVL is the function which checks whether the given binary search tree is an AVL tree or not. IsAVL returns -1 if the tree is not an AVL tree. During the checks, each node sends its height to its parent. Int is AVL, int left, right, if return 0, left equal to isAVL, if return left equal to right is AVL, if return right. If 1, return -1, return max plus 1. O, space complexity. O, problem 78. Given a height h, give an algorithm to generate an AVL tree with minimum number of nodes. Solution. To get minimum number of nodes, fill one level with h1 and the other with h2. Struct AVL tree node generate AVL tree return null, temp malloc equal to temp left generate AVL tree equal to temp data count plus plus, assume count is a global variable equal to temp right generate AVL tree, temp left height plus 1, or temp height equal to h, return temp. Problem -79. Given an AVL tree with n integer items and 2 integers a and b, where a and b can be any integers with a less than equal to b. Implement an algorithm to count the number of nodes in the range. Solution. The idea is to make use of the recursive property of binary search trees. There are 3 cases to consider: whether the current node is in the range, on the left side of the range, or on the right side of the range. Only subtrees that possibly contain the nodes will be processed under each of the 3 cases. Int range count if return 0, else if return range count, else if return range count, else if return range count plus range count plus 1. The complexity is similar to an order traversal of the tree, but skipping left or right subtrees when they do not contain any answers. So in the worst case, if the range covers all the nodes in the tree, we need to traverse all the n nodes to get the answer. The worst time complexity is therefore O. If the range is small, which only covers a few elements in a small subtree at the bottom of the tree, the time complexity will be O equal to O, where h is the height of the tree. This is because only a single path is traversed to reach the small subtree at the bottom, and many higher level subtrees have been pruned along the way. Note, refer similar problem in BST. Problem -80 given a BST where each node contains 2 data elements as shown below. Convert the tree to another BST by replacing the second data element with previous node data in order traversal. Note that each node is merged with in order previous node data. Also make sure that conversion happens in place. Solution: the simplest way is to use level order traversal. If the number of elements in the left subtree is greater than the number of elements in the right subtree, find the maximum element in the left subtree and replace the current node's second data element with it. Similarly, if the number of elements in the left subtree is less than the number of elements in the right subtree, find the minimum element in the right subtree and replace the current node's second data element with it. Struct BST tree compression, struct BST temp struct q equal to create q if return on q, while temp equal to dq if temp equal to find max, else temp find min, temp data temp. Process current node, remember to delete this node. Delete node in BST if in Q, delete Q. Time complexity O on average, since BST takes O on average to find the maximum or minimum element. Space complexity O, since in the worst case, all the nodes on the entire last level could be in the queue simultaneously. Problem -81. Can we reduce time complexity for the previous problem? Solution: let us try using an approach that is similar to what we followed in problem 60. The idea behind this solution is that in-order traversal of BST produces sorted lists. While traversing the BST in order, keep track of the elements visited and merge them. Struct binary search tree node tree compression return null into previous node data, return tree compression. Time complexity O, space complexity O. Note that we are still having recursive stack space for in-order traversal. Problem -82 key. Given a BST and a key, find the element in the BST which is closest to the given. Solution: as a simple solution, we can use level order traversal, and for every element compute the difference between the given key and the element's value. If that difference is less than the previous maintained difference, then update the difference with this new minimum value. With this approach, at the end of the traversal we will get the element which is closest to the given key. int closest in BST, difference abs, element equal to temp, 1 if on q, delete q, return element, data. Time complexity O. Space complexity O. Problem 83 for problem 82. Can we solve it using the recursive approach? Solution: the approach is similar to problem 18. Following is a simple algorithm for finding the closest value in BST. 1. If the root is null, then the closest value is 0. 2. If the root's data matches the given key, then the closest is the root. 3. Else, consider the root as the closest and do the following. A. If the key is smaller than the root data, find the closest on the left side tree of the root recursively and call it temp. 4. B. If the key is larger than the root data, find the closest on the right side tree of the root recursively and call it temp. Return the root or temp depending on whichever is nearer to the given key. Struct binary tree node closest in BST, else, if return root, temp equal to closest in BST, return abs. Root temp return null. Time complexity O in worst case, and in average case it is O. Space complexity O in worst case, and in average case it is O. Problem -84 median in an infinite series of integers. Solution: median is the middle number in a sorted list of numbers. If we have even number of elements, median is the average of two middle numbers in a sorted list of numbers. For solving this problem, we can use a binary search tree with additional information at each node, and the number of children on the left and right subtrees. We also keep the number of total nodes in the tree. Using this additional information, we can find the median in O time, taking the appropriate branch in the tree based on the number of children on the left and right of the current node. But the insertion complexity is O, because a standard binary search tree can degenerate into a linked list if we happen to receive the numbers in sorted order. So, let's use a balanced binary search tree to avoid worst-case behavior of standard binary search trees. For this problem, the balance factor is the number of nodes in the left subtree minus the number of nodes in the right subtree, and only the nodes with a balance factor of +1 or 0 are considered to be balanced. So, the number of nodes on the left subtree is either equal to or one more than the number of nodes on the right subtree, but not less. If we ensure this balance factor on every node in the tree, then the root of the tree is the median. If the number of elements is odd, in the number of elements is even, the median is the average of the root and its in-order successor, which is the leftmost descendant of its right subtree. So, the complexity of insertion maintaining a balance condition is O, and finding a median operation is O, assuming we calculate the in-order successor of the root at every insertion if the number of nodes is even. Insertion and balancing is very similar to AVL trees. Instead of updating the heights, we update the number of nodes information. Balanced binary search trees seem to be the most optimal solution. Insertion is O, and find median is O. Note, for an efficient algorithm, refer to the priority queues and heaps chapter. Problem 85, given a binary tree, how do you remove all the half nodes? Note that we should not touch leaves. Solution: by using post-order traversal, we can solve this problem efficiently. We first process the left children, then the right children, and finally the node itself. So we form the new tree bottom up, starting from the leaves towards the root. By the time we process the current node, both its left and right subtrees have already been processed. Struct binary tree node remove half nodes. If return null, root left remove half nodes, root right remove half nodes. If return root right, if return root left, return root. Time complexity, O. Problem -86. Given a binary tree, how do you remove its leaves? Solution: by using post-order traversal, we can solve this problem. Struct binary tree node remove leaves else equal to root left remove leaves, root right remove leaves, return root. Time complexity, O. Problem 87. Given a BST and two integers as parameters, how do you remove elements that are not within that range? 2525. Solution: observation. Since we need to check each and every element in the tree, and the subtree changes should be reflected in the parent, we can think about using post-order traversal. So we process the nodes starting from the leaves towards the root. As a result, while processing the node itself, both its left and right subtrees are valid pruned BSTs. At each node, we will return a pointer based on its value, which will then be assigned to its parent's left or right child pointer, depending on whether the current node is the left or right child of the parent. If the current node's value is between A and B, then no action needs to be taken, so we return the reference to the node itself. If the current node's value is less than A, then we return the reference to its right subtree and discard the left subtree. Because if a node's value is less than A, then its left children are definitely less than A since this is a binary search tree, but its right children may or may not be less than A. We can't be sure, so we return the reference to it. Since we're performing bottom-up post-order traversal, its right subtree is already a trimmed valid binary search tree, and its left subtree is definitely null because those nodes were surely less than A and they were eliminated during the post-order traversal. A similar situation occurs when the node's value is greater than B, so we now return the reference to its left subtree. Because if a node's value is greater than B, then its right children are definitely greater than B. But its left children may or may not be greater than B, so we discard the right subtree and return the reference to the already valid left subtree. Struct binary search tree node prune BST. If return null, root left prune BST. Root right prune BST. If return root right, if return root left. Time complexity, O in worst case and in average case it is O. Note, if the given BST is an AVL tree, then O is the average time complexity. Problem -88. Given a binary tree, how do you connect all the adjacent nodes at the same level? Assume that given binary tree has next pointer along with left and right pointers as shown below. Struct binary tree node int data, struct binary tree node left, struct binary tree node right, struct binary tree node next. Solution: one simple approach is to use level order traversal and keep updating the next pointers. While traversing, we will link the nodes on the next level. If the node has left and right node, we will link left to right. If node has next node, then link rightmost child of current node to leftmost child of next node. Void linking node dsof same level, struct QQ equal to create Q, struct binary tree node prev, pointer to the previous node of the current level struct binary tree node temp in current level node account, next level node account if return, on Q, current level node account equal to 1, next level node account equal to 0, prev equal to null, while temp equal to DQ, if, on Q, next level node account plus plus, if, on Q, next level node account plus plus, link the previous node of the current level to this node if prev next equal to temp, set the previous node to the current prev equal to temp, current level node account. If this is the last node of the current level node account equal to next level node account equal to 0, prev equal to null. Time complexity, O. Space complexity, O. Problem -89. Can we improve space complexity for problem 88? Solution: we can process the tree level by level, but without a queue. The logical part is that when we process the nodes of the next level, we make sure that the current level has already been linked. Void linking node to soft semi-level. If return, struct binary tree node rightmost node equal to null. Next head equal to null, temp equal to root. Connect next level of current root node level, while if rightmost node temp left, next head temp left, else rightmost node next equal to temp, left rightmost node equal to rightmost node. Next, if rightmost node temp right, next head temp right, else rightmost node. Next, temp right rightmost node equal to rightmost node. Next, temp temp. Next, linking nodes of same level. Time complexity, O. Space complexity, O for stack space. Problem 90%. Assume that a set S of n numbers are stored in some form of balanced binary search tree, that is the depth of the tree is O. In addition to the key value and the pointers to children, assume that every node contains the number of nodes in its subtree. Specify a reason why a balanced binary tree can be a better option than a complete binary tree for storing the set S. Solution. Implementation of a balanced binary tree requires less RAM space as we do not need to keep the complete tree in RAM. Problem 91 for the problem 90. Specify a reason why a complete binary tree can be a better option than a balanced binary tree for storing the set S. Solution. A complete binary tree is more space efficient as we do not need any extra flags. A balanced binary tree usually takes more space since we need to store some flags. For example, in a red-black tree, we need to store a bit for the color. Also, a complete binary tree can be stored in a RAM as an array without using pointers. Problem 92. Given a binary tree, find the maximum path sum. The path may start and end at any node in the tree. Solution. Int max path sum if return 0, int left sum equal to max path sumrec, int right sum, max path sumrec if max value equal to max, return root data, if max value equal to max value up equal to max plus root data, max value equal to max, return max value up. Problem minus 93. Let T be a proper binary tree with root R. Consider the following algorithm. Algorithm tree traversal. If return 1, else A equal to tree traversal, B equal to tree traversal, return A plus B. What does the algorithm do? A. It always returns the value 1. B. It computes the number of nodes in the tree. C. It computes the depth of the nodes. D. It computes the height of the tree. E. It computes the number of leaves in the tree. Solution. E. 6.14 other variations on trees. In this section, let us enumerate the other possible representations of trees. In the earlier sections, we have looked at AVL trees, which is a binary search tree with balancing property. Now, let us look at a few more balanced binary search trees, red-black trees, and splay trees. Six point 14.1 red-black trees. In red-black trees, each node is associated with an extra attribute, the color, which is either red or black. To get logarithmic complexity, we impose the following restrictions. Definition. A red-black tree is a binary search tree that satisfies the following properties. Root property, the root is black. External property, every leaf is black. Internal property, the children of a red node are black. Depth property, all the leaves have the same black. Similar to AVL trees, if the red-black tree becomes imbalanced, then we perform rotations to reinforce the balancing property. With red-black trees, we can perform the following operations in O in worst case, where n is the number of nodes in the trees. Insertion, deletion, finding predecessor, successor. Finding minimum, maximum. 6.14.2 splay trees. Splay trees are BSTs with a self-adjusting property. Another interesting property of splay trees is, starting with an empty tree, any sequence of k operations with maximum of n nodes takes O time complexity in worst case. Splay trees are easier to program and also ensure faster access to recently accessed items. Similar to AVL and red-black trees, at any point that the splay tree becomes imbalanced, we can perform rotations to reinforce the balancing property. Splay trees cannot guarantee the O complexity in worst case, but it gives amortized O complexity. Even though individual operations can be expensive, any sequence of operations gets the complexity of logarithmic behavior. One operation may take more time, A. Single operation may take O time, but the subsequent operations may not take worst case complexity, and on the average per operation complexity is O, lone. 6.14.3 billion trees. B tree is like other self-balancing trees such as AVL and red-black tree, such that it maintains its balance of nodes while operations are performed against it. B tree has the following properties. Minimum degree pound, where except root node, all other nodes must have no less than T1 keys. Each node with n keys has n plus 1 children. Keys in each node are lined up where K1K, Kn. Each node cannot have more than 2 T to 1 keys, thus 2 trillions children. Root node at least must contain 1 key. There is no root node if the tree is empty. Tree grows in depth only when root node is split. Unlike a binary tree, each node of a B tree may have a variable number of keys and children. The keys are stored in non-decreasing order. Each key has an associated child that is the root of a subtree containing all nodes with keys less than or equal to the key but greater than the preceding key. A node also has an additional rightmost child that is the root for a subtree containing all keys greater than any keys in the node. A B tree has a minimum number of allowable children for each node known as the minimization factor. If T is this minimization factor, every node must have at least T 1 keys. Under certain circumstances, the root node is allowed to violate this property by having fewer than T 1 keys. Every node may have at most 2 T to 1 keys, or equivalently, 2 trillions children. Since each node tends to have a large branching factor, it is typically necessary to traverse relatively few nodes before locating the desired key. If access to each node requires a disk access, then a B tree will minimize the number of disk accesses required. The minimization factor is usually chosen so that the total size of each node corresponds to a multiple of the block size of the underlying storage device. This choice simplifies and optimizes disk access. Consequently, a B tree is an ideal data structure for situations where all data cannot reside in primary storage, and accesses to secondary storage are comparatively expensive. Search the tree. It is similar to binary tree, except that the key is compared multiple times in a given node because the node contains more than one key. If the key is found in the node, the search terminates. Otherwise, it moves down where at child pointed by CI where key KK. Key insertions of a B tree happens from the bottom phasian. This means that it walked down the tree from root to the target child node first. If the child is not full, the key is simply inserted. If it is full, the child node is split in the middle, the median key moves up to the parent, then the new key. is inserted. When inserting and walking down the tree, if the root node is found to be full, it's split first and we have a new root node. Then the normal insertion operation is performed. Key deletion is more complicated as it needs to maintain the number of keys in each node to meet the constraint. If a key is found in leaf node and deleting it still keeps the number of keys in the nodes not too low, it's simply done right away. If it's done to the inner node, the predecessor of the key in the corresponding child node is moved to replace the key in the inner node. If moving the predecessor will cause the child node to violate the node count constraint, the sibling child nodes are combined, and the key in the inner node is deleted. Augmented trees. In earlier sections, we have seen various problems like finding the KTH, smallest element in the tree, and other similar ones. Of all the problems, the worst complexity is O, where n is the number of nodes in the tree. To perform such operations in O, augmented trees are useful. In these trees, extra information is added to each node, and that extra data depends on the problem we are trying to solve. For example, to find the KTH element in a binary search tree, let us see how augmented trees solve the problem. Let us assume that we are using red-black trees as balanced BST and augmenting the size information in the nodes data. For a given node X in red-black tree with a field size equal to the number of nodes in the subtree and can be calculated as KTH smallest operation can be defined as a struct binary circ tree node KTH smallest, int r equal to size plus 1, if return x, if return KTH smallest, if return KTH smallest. Time complexity, O. Space complexity, O. Example, with the extra size information, the augmented tree will look like 6.14½ interval trees. We often face questions that involve queries made in an array based on range. For example, for a given array of integers, what is the maximum number in the range A to SS, where A and SS are of course within array limits? To iterate over those entries with intervals containing a particular value, we can use a simple array. But if we need more efficient access, we need a more sophisticated data structure. An array-based storage scheme and a brute force search through the entire array is acceptable only if a single search is to be performed, or if the number of elements is small. For example, if you know all the array values of interest in advance, you need to make only one pass through the array. However, if you can interactively specify different search operations at different times, the brute force search becomes impractical because every element in the array must be examined during each search operation. If you sort the array in ascending order of the array values, you can terminate the sequential search when you reach the object whose low value is greater than the element we are searching. Unfortunately, this technique becomes increasingly ineffective as the low value increases, because fewer search operations are eliminated. That means, what if we have to answer a large number of queries like this? Is brute force still a good option? Another example is when we need to return a sum in a given range. We can brute force this too, but the problem for a large number of queries still remains. So, what can we do? With a bit of thinking, we can come up with an approach like maintaining a separate array of n elements where n is the size of the original array, where each index stores the sum of all elements from 0 to that index. So essentially, we have with a bit of preprocessing brought down the query time from a worst case O to O. Now, this is great as far as static arrays are concerned, but what if we are required to perform updates on the array too? The first approach gives us an O query time, but an O update time. The second approach, on the other hand, gives us O query time, but an O update time. So, which one do we choose? Interval trees are also binary search trees, and they store interval information in the node structure. That means we maintain a set of n intervals such that one of the intervals containing a query point q can be found efficiently. Interval trees are used for performing range queries efficiently. A segment tree is a heap-like data structure that can be used for making update query operations upon array intervals in logarithmical time. We define the segment tree for the interval in the following recursive manner. The root node will hold the information for the interval. If IY, the left and right children will hold the information for the intervals. Segment trees is a cool data structure primarily used for range queries. It is a height-balanced binary tree with a static structure. The nodes of a segment tree correspond to various intervals and can be augmented with appropriate information pertaining to those intervals. It is somewhat less powerful than a balanced binary tree because of its static structure, but due to the recursive nature of operations on the seg tree, it is incredibly easy to think about in code. We can use segment trees to solve range minimum maximum query problems. The time complexity is t, where O is the time required to build the tree, and each query takes O time. Example, given a set of intervals s equal to, a query with q equal to 9 returns, or a query with q equal to 23 returns. Construction of interval trees, let us assume that we are given a set S of n intervals. These n intervals will have two n endpoints. Now, let us see how to construct the interval tree. Algorithm. Recursively build tree on interval set 5 as follows. Sort the two n endpoints. Let xmid be the median point. Time complexity for building interval trees O. Since we are choosing the median, interval trees will be approximately balanced. This ensures that we split the set of endpoints up in half each time. The depth of the tree is O. To simplify the search process, generally xmid is stored with each node. Intervals that are completely to the left of xmid and n left. 6.14.6 Scapegoat trees. Scapegoat tree is a self-balancing binary search tree discovered by Arne Anderson. It provides worst-case O search time and O amortized insertion and deletion time. AVL trees rebalance whenever the height of two sibling subtrees differ by more than 1. Scapegoat trees rebalance whenever the size of a child exceeds a certain ratio of its parents, a ratio known as A. After inserting the element, we traverse back up the tree. If we find an imbalance where a child's size exceeds the parent's size times alpha, we must rebuild the subtree at the parent, the scapegoat. There might be more than one possible scapegoat, but we only have to pick one. The most optimal scapegoat is actually determined by height balance. When removing it, we see if the total size of the tree is less than alpha of the largest size since the last rebuilding of the tree. If so, we rebuild the entire tree. The alpha for a scapegoat tree can be any number between 0.5 and 1. The value 0.5 will force perfect balance, while 1 will cause rebalancing to never occur, effectively turning it into a BST. Chapter Priority Queue 7 and Heaps. 7.1. What is a priority queue? In some situations, we may need to find the minimum maximum element among a collection of elements. We can do this with the help of priority queue ADT. A priority queue ADT is a data structure that supports the operations insert and delete min or delete max. These operations are equivalent to onQ and DQ operation of a queue. The difference is that in priority queues, the order in which you'll enter to may not be the same in which they're processed. An example application of priority queue is job scheduling, which is prioritized instead of serving in first come first serve. A priority queue is called an ascending priority queue if the item with the smallest key has the highest priority. Similarly, a priority queue is said to be a descending priority queue if the item with the largest key has the highest priority. Since these two types are symmetric, we will be concentrating on one of them, ascending priority queue. 7.2 Priority Queue ADT. The following operations make priority queues in ADT. Main priority queues operations. A priority queue is a container of elements, each having an associated key. Insert inserts data with key to the priority queue. Elements are ordered based on key. Delete min, delete max, remove and return the element with the smallest largest key. Get minimum, get maximum, return the element with the smallest largest key without deleting it. Auxiliary priority queues operations. KTH, smallest KTH, largest, returns the KT, smallest KTH, largest key in priority queue. In priority queue. Heap sort sorts the elements in the priority queue based on priority. 7.3 Priority queue applications. Priority queues have many applications. A few of them are listed below. Data compression, Huffman coding algorithm, shortest path algorithms, Dijkstra's algorithm, minimum spanning tree algorithms, Prim's algorithm, event-driven simulation, customers in a line, selection problem, finding KTH smallest element, 7.4 priority queue implementations. Before discussing the actual implementation, let us enumerate the possible options. Unordered array implementation. Elements are inserted into the array without bothering about the order. Deletions are performed by searching the key and then deleting. Insertions complexity, O delete min complexity, O unordered list implementation. It is very similar to array implementation, but instead of using arrays, linked lists are used. Insertions complexity, O delete min complexity, O ordered array implementation. Elements are inserted into the array in sorted order based on key field. Deletions are performed at only one end. Insertions complexity, O delete min complexity, O ordered list implementation. Elements are inserted into the list in sorted order based on key field. Deletions are performed at only one end, hence preserving the status of the priority queue. All other functionalities associated with a linked list ADT are performed without modification. Insertions complexity, O, delete min complexity, O, binary search trees implementation. Both insertions and deletions take O on average if insertions are random. Balanced binary search trees implementation, both insertions and deletion take O in the worst case. Binary heap implementation. In subsequent sections, we will discuss this in full detail. For now, assume that binary heap implementation gives O complexity for search, insertions, and deletions, and O for finding the maximum or minimum element. Comparing implementations. 7.5 heaps and binary heaps. What is a heap? A heap is a tree with some special properties. The basic requirement of a heap is that the value of a node must be greater than or equal to than the values of its children. This is called heap property. A heap also has the additional property that all leaves should be at h or h, 1 levels for some h greater than 0. That means heap should form a complete binary tree. In the examples below, the left tree is a heap and the right tree is not a heap. Types of heaps? Based on the property of a heap, we can classify heaps into two types. Min heap, the value of a node must be less than or equal to the values of its children. Max heap, the value of a node must be greater than or equal to the values of its children. 7.6 binary heaps. In binary heap, each node may have up to 2 children. In practice, binary heaps are enough, and we concentrate on binary min heaps and binary max heaps for the remaining discussion. Representing heaps. Before looking at heap operations, let us see how heaps can be represented. One possibility is using arrays. Since heaps are forming complete binary trees, there will not be any wastage of locations. For the discussion below, let us assume that elements are stored in arrays which starts at index 0. The previous max heap can be represented as declaration of heap, creating heap, struct heap, create heap, printf, return, h heap underscore type, h count equal to 0, h capacity equal to capacity, h array malloc, h capacity, if. Printf, return h. Time complexity, O, parent of a node. 2. For a node at ith location, its parent is at 1-to-1 location. In the previous example, the element 6 is at second location, and its parent is at 0th location. I int parent, if return -1, return I at 1/2. Time complexity, O. Children of a node. Similar to the above discussion, for a node at ith location, its children are at 2i+1 and 2i+. 2 locations. For example, in the above tree, the element 6 is at second location, and its children 2 and 5 are at 5 and 6 locations. Int left child, int left equal to 2+1, if return -1, return left, time complexity. O. Int right child, int right equal to 2 times 1 plus 2, if return -1, return right, time complexity. O. Getting the maximum element. Since the maximum element in max heap is always at root, it will be stored at h. Array. Int get maximum, if return -1, return h array. Time complexity, O, heapifying an element. After inserting an element into heap, it may not satisfy the heap property. In that case, we need to adjust the locations of the heap to make it heap again. This process is called heapifying. In max heap, to heapify an element, we have to find the maximum of its children and swap it with the current element and continue this process until the heap property is satisfied at every node. Observation. One important property of heap is that if an element is not satisfying the heap property, then all the elements from that element to the root will have the same problem. In the example below, element 1 is not satisfying the heap property and its parent 31 is also having the issue. Similarly, if we heapify an element, then all the elements from that element to the root will also satisfy the heap property automatically. Let us go through an example. In the above heap, the element 1 is not satisfying the heap property. Let us try hepifying this element. To hepify 1, find the maximum of its children and swap with that. We need to continue this process until the element satisfies the heap properties. Now, swap 1 with 8. Now the tree is satisfying the heap property. In the above hepifying process, since we are moving from top to bottom, this process is sometimes called percolate down. Similarly, if we start hepifying from any other node to root, we can that process percolate up as move from bottom to top. Hepifying the element at location 1. Void percolate down 1 equal to left child, r equal to right child if h array, else max equal to 1, max equal to I if h array, max equal to r if, swap h array and h array, temp equal to h array, Harry h array equal to temp, percolate down. Time complexity, O. Heap is a complete binary tree, and in the worst case, we start at the root and come down to the leaf. This is equal to the height of the complete binary tree. Space complexity, O. Deleting an element. To delete an element from heap, we just need to delete the element from the root. This is the only operation supported by standard heap. After deleting the root element, copy the last element of the heap and delete that last element. After replacing the last element, the tree may not satisfy the heap property. To make a heap again, the percolate down function. Call. Copy the first element into some variable. Copy the last element into first element location, percolate down the first element. Int delete max, int data, if return -1, data equal to h array, h count. Reducing the heap size, percolate down. Return data. Note, deleting an element uses percolate down, and inserting an element uses percolate up. Time complexity, same as heapify function, and it is O, inserting an element. Insertion of an element is similar to the hepify and deletion process. Increase the heap size. Keep the new element at the end of the heap tree. Hepify the element from bottom to top. Before going through code, let us look at an example. We have inserted the element 19 at the end of the heap, and this is not satisfying the heap property. In order to hepify this element, we need to compare it with its parent and adjust them. Swapping 19 and 14 gives, now the tree is satisfying the heap property. Since we are following the bottom-up approach, we sometimes call this process percolate up. Insert int array underscore old equal to h array malloc h capacity 2, if printf return, for h array equal to array underscore old, h capacity equal to 2, free. Time complexity, O. The explanation is the same as that of the heapify function. Destroying heap, void destroy heap if return free h equal to null. Heapifying the array. One simple approach for building the heap is take n input items and place them into an empty heap. This can be done with n successive inserts and takes O in the worst case. This is due to the fact that each insert operation takes O. To finish our discussion of binary heaps, we will look at a method to build an entire heap from a list of keys. The first method you might think of may be like the following. Given a list of keys, you could easily build a heap by inserting each key one at a time. Since you are starting with a list of one item, the list is sorted, and you could use binary search to find the right position to insert the next key at a cost of approximately O operations. However, remember that inserting an item in the middle of the list may require O operations to shift the rest of the list over to make room for the new key. Therefore, to insert n keys into the heap would require a total of O operations. However, if we start with an entire list, then we can build the whole heap in O operations. Observation. Leaf nodes always satisfy the heap property and do not need to care for them. The leaf elements are always at the end, and to hepify the given array, it should be enough if we hepify the non-leaf nodes. Now, let us concentrate on finding the first non-leaf node. The last element of the heap is at location h, count 1, and to find the first non-leaf node is enough to find the parent of the last element. Void build heap int n if return, while resize heap for h array equal to a, h count equal to n for /2, I greater than equal to 0, I. Percolate down. Time complexity. The linear time bound of building heap can be shown by computing the sum of the heights of all the nodes. For a complete binary tree of height h containing n equal to 2 hours plus 1 nodes, the sum of the heights of the nodes is nh, 1 equal to n, lone 1. That means building the heap operation can be done in linear time by applying a percolate down function to the nodes in reverse level order. 7.7 Heap sort. One main application of heap ADT is sorting. The heap sort algorithm inserts all elements into a heap, then removes them from the root of a heap until the heap is empty. Note that heap sort can be done in place with the array to be sorted. Instead of deleting an element, exchange the first element with the last element and reduce the heap size. Then, we hepify the first element. Continue this process until the number of remaining elements is 1. Void heap sort in n, struct heap h equal to create heap, int old underscore size, I, temp, build heap, old underscore size equal to h, count 4, h array is the largest element, temp equal to h array, h array, h array, h array equal to temp, h count, percolate down, h count equal to old underscore size. Time complexity. As we remove the elements from the heap, the values become sorted. Since the time complexity of both the insertion algorithm and deletion algorithm is O, the time complexity of the heap sort algorithm is O. 7.8 Priority queues, problems and solutions. Problem -1. What are the minimum and maximum number of elements in a heap of height? H. Solution. Since heap is a complete binary tree, it has at most 2 hours plus 1-to-1 elements. This is because, to get maximum nodes, we need to fill all the h levels completely, and the maximum number of nodes is nothing but the sum of all nodes at all h levels. To get minimum nodes, we should fill the h1 levels fully, and the last level with only one element. As a result, the minimum number of nodes is nothing but the sum of all nodes from h1 levels plus 1, and we get 2 to 1 plus 1 equal to 2 hours elements. Problem 2, is there a min heap with 7 distinct elements so that the pre-order traversal of it gives the elements in sorted order? Solution, yes. For the tree below, pre-order traversal produces ascending order. Problem -3, is there a max heap with 7 distinct elements so that the pre-order traversal of it gives the elements in sorted order? Solution, yes. For the tree below, pre-order traversal produces descending order. Problem -4, is there a min heap max heap with 7 distinct elements so that the in-order traversal of it gives the elements in sorted order? Solution, no. Since a heap must be either a min heap or a max heap, the root will hold the smallest element or the largest. An in-order traversal will visit the root of the tree as its second step, which is not the appropriate place if the tree's root contains the smallest or largest element. Problem 5, is there a min heap max heap with 7 distinct elements so that the post-order traversal of it gives the elements in sorted order? Solution, yes, if the tree is a max heap and we want descending order, or if the tree is a min heap and we want ascending order. Show that the height of a heap with n elements is ln. Problem -6. Solution, a heap is a complete binary tree. All the levels, except the lowest, are completely full. A heap has at least 2 hours elements, and at most elements 2 hours less than or equal to n less than or equal to 2 hours plus 1-to-1. This implies h ln h plus 1. Since h is an integer, h equal to ln. Problem -7, given a min heap, give an algorithm for finding the maximum element. Solution, for a given min heap, the maximum element will always be at leaf only. Now the next question is how to find the leaf nodes in the tree. If we carefully observe, the next node of the last element's parent is the first leaf node. Since the last element is always at the h count, first location, the next node of its parent at can be calculated as h count 1 location 2. Now, the only step remaining is scanning the leaf nodes and finding the maximum among them. In find max in min heap, int max equal to -1 for /2 ih, count I++ if max equal to h array. Time complexity, O approximately equal to O. Problem -8, give an algorithm for deleting an arbitrary element from min heap. Solution, to delete an element, first we need to search for an element. Let us assume that we are using level order traversal for finding the element. After finding the element, we need to follow the delete min process. Time complexity equal the time for finding the element plus time for deleting an element equal to O plus O approximately equal to O. Time for searching dominated. Problem -9, give an algorithm for deleting the ith indexed element in a given min heap. Solution is int delete return key equal to h array, h array, h array, h count. Percolate down, return key, time complexity equal to O. Problem -10, prove that for a complete binary tree of height h, the sum of the height of all nodes is O. Solution, a complete binary tree has 2 to the power of 1 nodes on level. Also, a node on level I has depth y and height h, I. Let us assume that S denotes the sum of the heights of all these nodes, and S can be calculated as multiplying with 2 on both sides gives 2 seconds equal to 2 hours plus 4 plus 8 plus 2 hours, 1. Now subtract S from 2 seconds S equal to H plus 2 plus 4 plus 2 hours S equal to. But we already know that the total number of nodes n in a complete binary tree with height h is n equal to 2 hours plus 1-to-1. This gives us h equal to log. Finally, replacing 2 hours plus 1-to-1 with n gives S equal to n equal to O equal to O. Problem -11, give an algorithm to find all elements less than some value of k in a binary heap. Solution, start from the root of the heap. If the value of the root is smaller than k, then print its value and call recursively once for its left child and once for its right child. If the value of a node is greater or equal than k, then the function stops without printing that value. The complexity of this algorithm is O, where n is the total number of nodes in the heap. This bound takes place in the worst case, where the value of every node in the heap will be smaller than k, so the function has to call each node of the heap. Problem -12 give an algorithm for merging two binary max heaps. Let us assume that the size of the first heap is m plus n, and the size of the second heap is n. Solution: one simple way of solving this problem is: assume that the elements of the first array are at the beginning. That means first m cells are filled and remaining n cells are empty. Without changing the first heap, just append the second heap and heapify the array. Since the total number of elements in the new array is m plus n, each heapify operation takes O. The complexity of this algorithm is O log. Problem -13, can we improve the complexity of problem 12? Solution: instead of heapifying all the elements of the m plus n array, we can use the technique of building heap with an array of elements. We can start with non-leaf nodes and heapify them. The algorithm can be given A's. Without changing the first heap, just append the second heap. Assume that the elements of the first array are at the beginning. That means the first m cells are filled and the remaining n cells are empty. Now, find the first non-leaf node and start heapifying from that element. In the theory section, we've already seen that building a heap with n elements takes O complexity. The complexity of merging with this technique is O. Problem -14, is there an efficient algorithm for merging two max heaps? Assume both arrays have n elements. Solution: the alternative solution for this problem depends on what type of heap it is. If it's a standard heap where every node has up to 2 children and which gets filled up so that the leaves are on a maximum of 2 different rows, we cannot get better than O for the merge. There is an O algorithm for merging two binary heaps with sizes m and n. For m equal to n, this algorithm takes O time complexity. We will be skipping it due to its difficulty and scope. For better merging performance, we can use another variant of binary heap like a Fibonacci heap, which can merge in O on average. Problem -15, give an algorithm for finding the kth smallest element in min heap. Solution: one simple solution to this problem is perform deletion k times from min heap. Return pq.min. Just delete first k1 elements and return the kth element. For delete min, return delete min. Time complexity O. Since we are performing deletion operation k times and each deletion takes O. Problem -16 for problem 15, can we improve the time complexity? Solution: assume that the original min heap is called horig and the auxiliary min heap is named ho. Initially, the element at the top of horig, the minimum one, is inserted into ho. Here we don't do the operation of delete min with horig, heap ho, and find k largest L else. Insert the left and right children in ho into the ha-ho.insert, hos.insert. Every while loop iteration gives the kth smallest element, and we need k loops to get the kth smallest elements. Because the size of the auxiliary heap is always less than k, every while loop iteration the size of the auxiliary heap increases by 1, and the original heap horig has no operation during the finding. The running time is O. Note, the above algorithm is useful if the k value is too small compared to n. If the k value is approximately equal to n, then we can simply sort the array and return kth smallest element from the sorted array. This gives O solution. Problem -17, find k max elements from max heap. Solution: one simple solution to this problem is build max heap and perform deletion k times. Problem 18 for problem 17, is there any alternative solution? Solution: we can use the problem 16 solution. At the end, the auxiliary heap contains the largest elements. Without deleting the elements, we should keep on adding elements to ho. Problem -19. How do we implement stack using heap? Solution: to implement a stack using a priority QPQ, let us assume that we are using one extra integer variable c. Also assume that c is initialized equal to any known value. The implementation of the stack ADT is given below. Here, c is used as the priority while deleting the elements from PQ. Void push 1 and pop in size int is empty, return pq.isEmpty. We could also increment c back when popping. Observation: we could use the negative of the current system time instead of c. The implementation based on this can be given as void push pq.insert element. Problem 20. How do we implement q using heap? Solution: to implement a queue using a priority queue PQ, as similar to stack simulation, let us assume that we are using one extra integer variable, c. Also, assume that c is initialized equal to any known value. The implementation of the queue ADT is given below. Here, the c is used as the priority, while deleting the elements from PQ. One void push c++ int pop return pq.deletemin, int top, return pq.min, int size, return pq.size, int is empty, return pq is empty. Note, we could also decrement c when popping. Observation, we could use just the negative of the current system time instead of c. The implementation based on this can be given as void push pq.insert element. Note, the only change is that we need to take a positive c value instead of negative. Problem 21. Given a big file containing billions of numbers, how can you find the 10 maximum numbers from that file? Solution. Always remember that when you need to find max n elements, the best data structure to use is priority queues. One solution for this problem is to divide the data in sets of 1,000 elements and make a heap of them, and then take 10 elements from each heap one by one. Finally, heap sort all the sets of 10 elements and take the top 10 among those. But the problem in this approach is where to store 10 elements from each heap. That may require a large amount of memory as we have billions of numbers. Reusing the top 10 elements in subsequent elements can solve this problem. That means take the first block of 1,000 elements and subsequent blocks of 990 elements each. Initially, heap sort the first set of 1,000 numbers, take max 10 elements and mix them with 990 elements of the second set. Again, heap sort these 1,000 numbers, take 10 max elements, and mix them with 990 elements of the third set. Repeat to the last set of 990 elements and take max 10 elements from the final heap. These 10 elements will be your answer. Time complexity, O equal to n. 1,000 times, since complexity of heap sorting 1,000 elements will be a constant, so the O equal to n, that is linear complexity. Problem -22 merge k-sorted lists with total of n elements. We are given k-sorted lists with total n inputs in all the lists. Give an algorithm to merge them into one single sorted list. Solution. Since there are k equal size lists with a total of n elements, the size of each list is, or one simple way of solving this problem is, take the first list and merge it with the second list. Since the size of each list is h, this step produces a sorted list with size. This is similar to merge sort logic. The 2n time complexity of this step is 2nkk. This is because we need to scan all the elements of both the lists. Then, merge the second list output with the third list. As a result, this step produces a sorted list with size. The time complexity of this step is, this is because we 3nk need to scan all the elements of both lists. Continue this process until all the lists are merged to one list. Total. Space complexity. O. Complexity. Problem 23 for problem 22. Can we improve the time complexity? Solution. 1. Divide the lists into pairs and merge them. That means, first take 2 lists at a time and merge them so that the total elements parsed for all lists is O. This operation gives k2 lists. 2. Repeat step -1 until the number of lists becomes 1. Time complexity, step 1 executes lock times, and each operation parses all n elements in all the lists for making k2 lists. For example, if we have 8 lists, then the first pass would make 4 lists by parsing all n elements. The second pass would make 2 lists by again parsing n elements, and the third pass would give 1 list by again parsing n elements. As a result, the total time complexity is O. Space complexity, O. Problem 24 for problem 23. Can we improve the space complexity? Solution. Let us use heaps for reducing the space complexity. 1. Build the max heap with all the first elements from each list in O. 2. In each step, extract the maximum element of the heap and add it at the end of the output. 3. Add the next element from the list of the one extracted. That means we need to select the next element of the list, which contains the extracted element of the previous step. 4. Repeat step 2 and step -3 until all the elements are completed from all the lists. Time complexity equal to O. At a time, we have k elements max heap, and for all n elements, we have to read just the heap in lock time, so total time equal to O. Space complexity, O. Problem 25, given 2 arrays A and B each with n elements. Give an algorithm for finding largest n pairs, B. Solution. Algorithm. Heapify A and B. This step takes O approximately equal to O. Then keep on deleting the elements from both the heaps. Each step takes OO. Total time complexity, O. Problem 26, min-max heap. Give an algorithm that supports min and max in O time. Insert delete min and delete max in O time. That means design a data structure which supports the following operations. Solution. This problem can be solved using 2 heaps. Let us say 2 heaps are minimum heap min and maximum heap hmax. Also, assume that elements in both the arrays have mutual pointers. That means an element hmin will have a pointer to the same element in hmax, and an element in hmax will have a pointer to the same element in hmin. Problem 27, median. Dynamic median finding. Design a heap data structure that supports finding they. Solution: in a set of n elements, median is the middle element, such that the number of elements lesser than the median is equal to the number of elements larger than the median. If n is odd, we can find the median by sorting the set and taking the middle element. If n is even, the median is usually defined as the average of the two middle elements. This algorithm works even when some of the elements in the list are equal. For example, the median of the multiset is 2, and the median of the multiset is 2.5. Median heaps are the variant of heaps that give access to the median element. A median heap can be implemented using two heaps, each containing half the elements. One is a max heap, containing the smallest elements. The other is a min heap, containing the largest elements. The size of the max heap may be equal to the size of the min heap if the total number of elements is even. In this case, the median is the average of the maximum element of the max heap and the minimum element of the min heap. If there is an odd number of elements, the max heap will contain one more element than the min heap. The median in this case is simply the maximum element of the max heap. Problem 28, maximum sum in sliding window, given array A with sliding window of size W, which is moving from the very left of the array to the very right. Assume that we can only see the W numbers in the window, each time the sliding window moves rightwards by one position. For example, the array is, and W is 3. Input, a long array A, and a window width W output, an array B. B is the maximum value of from A to A. Requirement, find a good optimal way to get B. Solution, brute force solution is, every time the window is moved, we can search for a total of W elements in the window. Time complexity, O. Problem minus 29 for problem 28, can we reduce the complexity? Solution, yes, we can use heap data structure. This reduces the time complexity to O. Insert operation takes O time, where W is the size of the heap. However, getting the maximum value is cheap. It merely takes constant time as the maximum value is always kept in the root of the heap. As the window slides to the right, some elements in the heap might not be valid anymore. How should we remove them? We would need to be somewhat careful here. Since we only remove elements that are out of the window's range, we would need to keep track of the elements' indices too. Problem 30 for problem 28. Can we further reduce the complexity? Solution, yes, the double-ended queue is the perfect data structure for this problem. It supports insertion deletion from the front and back. The trick is to find a way such that the largest element in the window would always appear in the front of the queue. How would you maintain this requirement as you push and pop elements in and out of the queue? Besides, you will notice that there are some redundant elements in the queue that we shouldn't even consider. For example, if the current queue has the elements, and a new element in the window has the element 11, now we could have emptied the queue without considering elements 10, 5, and 3, and insert only element 11 into the queue. Typically, most people try to maintain the queue size the same as the window size. Try to break away from this thought and think out of the box. Removing redundant elements and storing only elements that need to be considered in the queue is the key to achieving the efficient O solution below. This is because each element in the list is being inserted and removed at most once. Therefore, the total number of insert plus delete operations is 2n. Void max sliding window, int n, int w, int b. Struct double end q, q equal to create double end q. For, while andand a greater than equal to a. Popback pushback for b equal to a, while andand a greater than equal to a. Popback, while andand q front less than equal to iw pop front pushback b equal to a. Problem minus 31. A priority queue is a list of items in which each item has associated with it a priority. Items are withdrawn from a priority queue in order of their priorities, starting with the highest priority item first. If the maximum priority item is required, then a heap is constructed such that priority of every node is greater than the priority of its children. Design such a heap where the item with the middle priority is withdrawn first. If there are n items in the heap, then the number of items with the priority smaller than the middle priority is if n is odd, else equal to +1 + 1. n2, n2. Explain how withdraw and insert operations work, calculate their complexity, and how the data structure is constructed. Solution, we can use one min heap and one max heap such that root of the min heap is larger than the root of the max heap. The size of the min heap should be equal or one less than the size of the max heap. So the middle element is always the root of the max heap. For the insert operation, if the new item is less than the root of max heap, then insert it into the max heap, else insert it into the min heap. After the withdraw or insert operation, if the size of heaps are not as specified above, then transfer the root element of the max heap to min heap or vice versa. With this implementation, insert and withdraw operation will be in O time. Problem 32, given two heaps, how do you merge them? Solution: binary heap supports various operations quickly. Find, min, insert, decrease key. If we have two min heaps, h1 and h2, there is no efficient way to combine them into a single min heap. For solving this problem efficiently, we can use mergeable heaps. Mergeable heaps support efficient union operation. It is a data structure that supports the following operations. Create heap creates an empty heap. Insert an item x with key k into a heap h. Find min. Return item with min key. Delete min. Return and remove. Union merge heaps h1 and h2. Examples of mergeable heaps are binomial heaps, Fibonacci heaps. Both heaps also support decrease key, assign item y with a smaller key k, delete, remove item 10th binomial heaps. Unlike binary heap, which consists of a single tree, a binomial heap consists of a small set of component trees, and no need to rebuild everything when union is performed. Each component tree is in a special format called a binomial tree. A binomial tree of order k, denoted by bk, is defined recursively as follows. Bo is a tree with a single node. For k greater than or equal to 1, bk is formed by joining 2b minus 1, such that the root of one tree becomes the leftmost child of the root of the other. Example: Fibonacci heaps. Fibonacci heap is another example of mergeable heap. It has no good worst-case guarantee for any operation. Fibonacci heaps have excellent amortized cost to perform each operation. Like binomial heap, Fibonacci heap consists of a set of min-heap ordered component trees. However, unlike binomial heap, it has no limit on number of trees and no limit on height of a tree. Also, find min, delete min, union, decrease key, delete all have worst-case O running time. However, in the amortized sense, each operation performs very quickly. Problem -33, median in an infinite series of integers. Solution: median is the middle number in a sorted list of numbers. If we have even number of elements, median is the average of two middle numbers in a sorted list of numbers. We can solve this problem efficiently by using two heaps, one max heap and one min heap. 1. Max heap contains the smallest half of the received integers. 2. Min heap contains the largest half of the received integers. The integers in max heap are always less than or equal to the integers in min heap. Also, the number of elements in max heap is either equal to or one more than the number of elements in the min heap. In the stream, if we get 2n elements, max heap and min heap will both contain equal number of elements. Otherwise, if we have received 2n plus 1 elements, max heap will contain n plus 1 and min heap n. Let us find the median. If we have 2n plus 1 elements, the median of received elements will be the largest element in the max heap. Otherwise, the median of received elements will be the average of largest element in the max heap and smallest element in the min heap. This can be calculated in O. Inserting an element into heap can be done in O. Note that any heap containing n plus 1 elements might need one delete operation as well. Example: insert 1, insert to max heap, min heap, insert 9, insert to min heap. Since 9 is greater than 1 and min heap maintains the maximum elements, max heap, min heap, insert 2, insert min heap. Since 2 is less than all elements of min heap, max heap, min heap, insert 0. Since max heap already has more than half, we have to drop the max element from max heap and insert it to min heap. So, we have to remove 2 and insert into min heap. With that, it becomes max heap, min heap, now insert 0 to max heap. Total time complexity, O. Problem -34. Suppose the elements 7, 2, 10, and 4 are inserted, in that order, into the valid 3 array max heap found in the above question. Which one of the following is the sequence of items in the array representing the resultant heap? 10, 7, 9, 8, 3, 1, 5, 2, 6, 4, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 5, 4, 10, 3, 6, 4, 10, 9. 10, 8, insertion of 7, after insertion of 2, after insertion of 10, after insertion of. Problem 35. A complete binary min heap is made by including each integer in exactly once. The depth of a node in the heap is the length of the path from the root of the heap to that node. Thus, the root is at depth 0. The maximum depth at which integer 9 can appear is. Solution. As shown in the figure below, for a given number 1, we can fix the element I at each level and arrange the numbers 1 to I, 1 to the levels above. Since the root is at depth 0, the maximum depth of the ith element in a min heap is I1. Hence, the maximum depth at which integer 9 can appear is 8. Problem -36. A d-array heap is like a binary heap, but instead of 2 children, nodes have d children. How would you represent a d-array heap with n elements in an array? What are the expressions for determining the parent of a given element, parent, and a JTH child of a given element? Child where 1 less than or equal to j less than or equal Todd. Solution: the following expressions determine the parent and JTH child of element odd. Child equal to .d plus j plus 1. Disjoint sets ADT, Chapter 8. 8.1 Introduction. In this chapter, we will represent an important mathematics concept, sets. This means how to represent a group of elements which do not need any order. The disjoint sets ADT is the one used for this purpose. It is used for solving the equivalence problem. It is very simple to implement. A simple array can be used for the implementation, and each function takes only a few lines of code. Disjoint sets ADT acts as an auxiliary data structure for many other algorithms.